columns might be those chosen from a bell curve of possible values, or they might simply be ones and minus one. The top right and bottom left halves of the matrix might be mirror images of one another or not. Pattern again, regardless of their specific characteristics, the random matrices are found to exhibit that same chaotic or regular pattern in the distribution of their eigenvalues. That's why mathematicians call the phenomenon universality. Okay, so that was an interesting discovery. Now this is the part about the chicken eyes. This is very interesting. 70 years ago, Gil Corvo stared into the eye of a chicken and saw something astonishing. The color-sensitive cone cells that carpeted the retina appeared as polka dots of 5 different colors and sizes. Corvo observed that unlike the randomly dispersed cones in human eyes, or the neat rows of cones in the eyes of many fish, the chicken's cones had a haphazard and yet remarkable uniform distribution. The dots' locations followed no discernible rule, and yet dots never appeared too close together or too far apart. Each of the 5 interspersed sets of cones, and all of them together, exhibited the same arresting mix of randomness and regularity. Corvo, who runs a biology lab at Washington University in St. Louis, was hooked. Extremely beautiful, just look at these patterns. We were kind of captured by the beauty, and then purely out of curiosity and desire to understand the patterns better. Also, I had to figure out the pattern's function and how they were generated. He didn't know then that these same questions were being asked in numerous other contexts, or that he had found the first biological manifestation of a type of disorder that has also turned up all over mathematics and physics. Corvo did know that whatever bird retinas are doing is probably the thing to do. Avian vision works spectacularly well, enabling eagles, for instance, to spot mice from a mile high, and the lab studies the evolutionary adaptations that make this so. Many of these attributes are believed to have been passed down to birds from a lizard-like creature that 300 million years ago gave rise to both dinosaurs and proto-mammals. While birds' ancestors, the dinosaurs, ruled the planetary roost, mammalian scurried around in the dark, fearfully nocturnal and gradually losing color discrimination. Mammals' cones dropped to 2, a nadir from which we are still clambering back. About 30 million years ago, one of our primate ancestors' cones split into 2, red and green detecting, which together with the existing blue detecting cones gave us trichromatic vision. But our cones, particularly the newer red and green ones, have a clumpy scattershot distribution and sample light unevenly. Birds' eyes have had eons longer to optimize. Along with their higher cone count, they achieved a far more regular spacing of the cells. But why Corvo and colleagues wondered had evolution not opted for the perfect regularity of a grid or a T distribution of cones. The strange, uncharacterizable pattern they observed for the retinas was in all likelihood optimizing some unknown set of constraints. What these were, what the pattern was, and how the avian visual system achieved it remained unclear. The biologists did their best to quantify the regularity in the retinas, but this was unfamiliar terrain and they needed help. In 2012, Corvo contacted Salvador Picado, a professor of theoretical chemistry at Princeton and a renowned expert in the discipline known as packing. Packing problems ask about the densest way to pack objects such as cone cells of 5 different sizes in a given number of dimensions, in the case of a retina 2. I wanted to get at this question of whether such a system was optimally packed. Corvo said. Intrigued, Mercado ran some algorithms on digital images of the retinal patterns and was astounded. Wilbur recalled to see the same phenomenon occurring in these systems as they've seen in a lot of inorganic or physical systems. Hyperuniformity in chicken eyes. Apparent disorder. The colored dots below correspond to the arrangement of green, blue, red, violet, and double-type black cone receptors, photoreceptors in a chicken's retina. Each cone is a different size. At first glance, the distribution appears to be disordered. Order revealed. By considering the cone types separately, we can see that each cone is surrounded by an exclusion region that cones of other types can enter, but cones of the same type avoid. Each set of cones, although not perfectly uniform, is as uniform as it can be given the packing constraints of 5 different cone sizes. Turcado had been studying the same order since the early 2000s when he dubbed it hyperuniformity. This term has largely won out over superhomogeneity, coined around the same time by Joe Lebowitz of Rutgers. Since then, it has turned up in a number of rapidly expanding family of systems. Beyond bird eyes, however, uniformities found in materials called quasi-crystals, as well as in mathematical matrices for random numbers, a large-scale structure of the universe, quantum ensembles, and soft matter systems like emulsions and colloids. Scientists are nearly always taken by surprise when it pops up in view in places as if playing whack-a-mole with the universe. We are still searching for a unifying concept underlying these occurrences. In the process, they've uncovered novel properties of hyper-uniform materials that could prove technologically useful. From a mathematical standpoint, the more you study it, the more elegant and conceptually compelling it seems. On the other hand, what surprises me about it is the potential breadth of its applications. Turcado and a colleague launched a study of hyperuniformity 13 years ago, describing it theoretically as identifying a simple yet surprising example. You take marbles, you put them in a container, you shake them up until they jam. That system is hyperuniform. Marbles fall into an arrangement technically called a maximally random jam packing, in which they fill 64% of space. The rest is empty air. This is less than in the densest possible arrangement of spheres. The cheese packing used to stack oranges in a crate, which fills 74% of space. But cheese packing isn't always possible to achieve. You can't easily shake a box full of marbles into a crystalline arrangement. Neither can you form a lattice. Turcado explained by arranging objects in 5 different sizes, such as the cones and chicken eyes. Stand-ins for cones consider coins on a tabletop. You take pennies and you try to compress the pennies like to go into the triangular labels. We're throwing some nickels in with the pennies, and that stops it from crystallizing. Now, if you have 5 different components, throwing quarters, throwing dimes, whatever, that inhibits crystallization even further. Likewise, geometry demands that even cone cells be disordered. But there is a competing evolutionary demand for the retina to sample light as uniformly as possible, with blue cones positioned far from other blue cones, reds far from other reds, and so on. Balancing these constraints, the system settles for disordered hyperuniformity. Hyperuniformity infers the best of both worlds. 5 cone types arranged in near uniform mosaics provide phenomenal color resolution. But it's a hidden order that you can't detect with your eye. Determining whether a system is hyperuniform requires algorithms that work like a game of ring toss. First, imagine repeating a toss in a ring onto an orderly lattice of dots, and each time it lands, counting the number of dots inside the ring. The number of captured dots fluctuates from one ring toss to the next, but not by very much. That's because the interior of the ring always covers a fixed block of dots. The only variation in the number of captured dots happens along the ring's perimeter. If you increase the size of the ring, you will get a variation along the longest perimeter, and so with the lattice, the variation in the number of captured dots and density fluctuations in the lattice grows in proportion to the length of the ring's perimeter. In higher spatial dimensions, the density fluctuations also scale in proportion with the number of dimensions minus 1. More holography, very interesting. Finally, hidden order. Imagine repeating tossing a ring onto a field of dots and counting the number of whole dots inside the ring each time it lands. The number of enclosed dots per ring toss varies more for large rings than for small rings. This is because all the variation occurs around the ring's edge, and so is proportional to the ring's perimeter. Order is the teeth. Random distribution. The variation in the number of enclosed dots is proportional to the ring's area, since the density of dots varies throughout the ring. This means the variation can become extreme on large scales. Hyper-uniform distribution. For smaller rings, the variation is similar to that of a random distribution, but the variation is proportional to the ring's perimeter rather than its area. So for large rings, the variation resembles that of lattice. Oh, very interesting. Now imagine say a ring toss with a smattering uncorrelated dots, a random distribution marked by gaps and clusters. The hallmark of randomness is that as you make the ring bigger, the variation in the number of captured dots scales in proportion to the ring's area rather than its perimeter. The result is that on large scale, the density fluctuations between ring tosses in a random distribution are much more extreme than in OT. Indeed, it's interesting when it involves hyper-uniform distribution. The dots are locally disordered, so for small ring sizes, the number of captured dots fluctuates from one toss to the next more than a lattice. But as you make the ring bigger, the density fluctuations begin to go in proportion to the ring's perimeter rather than its area. This means that the large-scale density of the distribution is just as uniform as that of a lattice. Among hyper-uniform systems, researchers have found a further zoology of structures, said Princeton physicist Paul Steinhardt. In these systems, the growth density functions fluctuations depends on different powers between 1 and 2 of the ring's perimeter multiplied by different coefficients. What does it all mean? We don't know. It's evolving. Hyperuniformity is clearly a state to which diverse systems converge, but the explanation for universality is a work in progress. It's basically a hallmark of deeper optimization processes of some sort. But what these processes are might vary a lot between different problems. Hyperuniform systems fall into two main categories. Those in the first class are quasi-quick, the crystals, bizarre solids with interlocking atoms follow no repeating pattern yet tessellate space after being hyperuniform. On reaching equilibrium, the stable configuration of particles settle into of their own accord. These equilibrium systems, it is mutual repulsions between the particles that space them apart and give rise to global hyperuniformity. Similar math might explain the emergence of hyperuniformity in Bird's eye, the distribution of eigenvalues of random matrices, and the zeros of the Riemann zeta function, cousins of the prime numbers. The other class is not as well understood in these non-equilibrium systems, which include shaken marbles, emulsions, colloids, ensembles of cold atoms, particles bump into one another but otherwise do not exert mutual forces. External forces must be applied to the system to drive them to a hyperuniform state. Within the non-equilibrium class, there are further intractable divisions. Last fall, physicists in France reported that hyperuniformity can be induced in emulsions by sloshing them at the exact amplitude that marks the transition between reversibility and irreversibility in the material. When sloshed more gently than this critical amplitude, the particles suspended in the emulsion return to their previous relative positions after each slosh. When sloshed harder, the particles' motions do not reverse. Petrol's work suggests fundamental but not fully formed connection between the onset of reversibility and the emergence of hyperuniformity in such non-equilibrium systems. Maximally random jam packing, meanwhile, are a whole different story. Can we connect it to physics? No, not at all. We have absolutely no idea why hyperuniformity shows up in these two different sets of physical systems. As described to link these threads, scientists have also encountered surprising properties of hyperuniform materials. Behaviors that are normally associated with crystals but which are less susceptible to fabrication errors, more like properties of glass and other uncorrelated disordered media. It occurs that dense hyperuniform materials can be made transparent, whereas uncorrelated disordered materials with the same density would be opaque. The hidden order in the particles relative positions causes their scattered light to interfere and cancel out. The interferences destroy scattering. Light goes through as if the material were homogeneous. The student will know what dense, transparent, non-crystalline materials might be useful for, but there are certainly potential applications, particularly in photonics. Recent findings about how hyperuniformity generated in emulsions translates into an easy recipe for storing concrete, like creams, glass, and food. Whenever you want to disperse particles inside a paste, you have to deal with a hard mixing problem. This can be a way to disperse solid particles in a very uniform fashion. First, to identify a material's characteristic amplitude, they derive it at that amplitude a few dozen times with evenly mixed after uniform distribution emerges. They are making photonic circuits, devices that transmit data via light rather than electrons. Hyperuniform materials can have band gaps which block certain frequencies from propagating. Band gaps enable controlled transmission of data. The blocked frequencies can be contained in guided through channels called waveguides. Band gaps were once thought to be unique to crystal lattices and direction-dependent aligning with the crystal axis. This meant photonic waveguides could only go in certain directions, limiting their use of circuits. Since hyperuniform materials have no preferred direction, they will understood band gaps are potentially much more practical, enabling not only wiggly waveguides, but waveguides as you wish. As for the pattern of five-color mosaics in bird's eye termed multi-hyperuniform, it is so far unique in nature. Still haven't pinpointed how the pattern forms, so there are no mutual repulsions between cone cells, like other systems of the equilibrium class, or do cones get shaken up like a box of marble? The guess is the former. Cells can secrete molecules that repel cells of the same type, but have no effect on other types, probably during embryonic development. Each cone cell signals that it is differentiating as a certain type. The investigator cells are doing the same. That's the simple marvel of how this can develop, he said. Local action on each cell is creating a global pattern. Aside from chicken, the same multi-hyperuniform retinal patterns turned up in the three other bird species that Corbo is investigating, suggests that the adaptation is widespread and not tailored to any particular environment. He wonders whether evolution might have found a different optimal configuration in nocturnal species. That would be super interesting. It's trickier for us to get our hands on owls. Okay. So, here's Wheeler of 1989 essay propounding the idea that the physical universe arises from information which he dubbed it from bit. It from qubit. Space-time and everything in it are in some sense emergent. We drew a picture on the blackboard of the universe visualized as an eye looking at itself. In hindsight, he was explaining what it meant to talk about quantum mechanics when the observer is part of the quantum system. Imagine there is something we don't understand about that. Yes, it's the observer effect. Observing the quantum system irreversibly changes it, creating a distinction between past and future. So the observer issue seems possibly related to the question of time, which we also don't understand. With the ADS-CFT duality, we learned that new spatial dimensions can pop up like a hologram from quantum information on the boundary. Do you think time is also emergent, that arises from a timeless complete description? As you read, he thought that the continuum was wrong in both physics and math. He did not think one's microscopic description of space-time should use a continuum of any kind. Neither a continuum of space nor a continuum of time, not even a continuum of real numbers. He wants to explain the meaning of existence. He talks about explaining how physics arises from information. Traditionally, it was thought that interacting quantum field theory couldn't exist above 4 dimensions, and there was the interesting fact that that's the dimensions we live in. But one of the offshoots of the string duality of the 1990s was that it was discovered that quantum field theories actually exist in 5 and 6 dimensions. And it's amazing how much is known about their properties. I've heard about the mysterious 2-0 theory of quantum field theory describing particles in 6 dimensions. This is dual to M theory describing strings of gravity in 7-dimensional ADS space. Does this 2-0 theory play an important role in the web of dualities? Yes, that's the pinnacle. In terms of conventional quantum field theory without gravity, there is nothing quite like it above 6 dimensions. From the 2-0 theory, distance and mean properties, you can deduce an incredible amount. Well, what happens in lower dimensions? An awful lot of important dualities in 4 and fewer dimensions follow from the 6-dimensional theory and its properties. However, whereas we know about quantum field theories normally from quantizing classical field theory, there is no reasonable classical starting point of the 2-0 theory. The 2-0 theory has properties such as a combination of symmetries that sound impossible when we first hear about them. So you can ask why dualities exist, but you can also ask why there is a 6-dimensional theory with such and such properties. This seems to be a more fundamental reason. M-theory was proposed 22 years ago. Personally, I thought it was extremely clear it existed 22 years ago, but the level of confidence is actually much higher today because ADS-CFT has given us precise definitions, at least in ADS space-time geometries. I think our understanding of what it is, though, is still very hazy. ADS-CFT and whatever comes from it is a main new perspective compared to 22 years ago, but I think it's perfectly possible that ADS-CFT is only one side of a multifaceted theory. There might be other equally important facets. Geometric Lagrange from 6 dimensions. Geometric Lagrange dualities usually formulate a statement about Riemann surfaces, but they can be naturally understood as a consequence of electric-magnetic duality of 4-dimensional gauge theory. This duality, in turn, is naturally understood as a consequence of the existence of certain exotic supersymmetric conformal field theories in 6 dimensions. The same 6-dimensional theory also gives a useful framework for understanding some recent mathematical results involving a counterpart of geometric Lagrange duality for complex surfaces. Black-light universe, real space correlation properties of standard cosmological models. After revealing the basic relevant properties of stationary stochastic properties, or processes defining basic terms and quantities, we discussed the properties of the so-called Harrison-Zeldovich-like spectra. These correlations usually characterized exclusively K-space are a fundamental feature of all current standard cosmological models. Examining them in the real space, we know that the characteristics to be negative power law and a self-poising normalized variance in spheres. We know the particular this latter behavior is at the limit of the most rapid decay of this quantity possible for any stochastic distribution, continuous or discrete. This very particular characteristic is usually obscured in cosmology by the use of Gaussian spheres. In a simple classification of all SSP into 3 categories, we highlight with the main super-homogeneous properties of the class to each models, such as this, with P0 equals 0 belong. In statistical physics language, they are well described as glass-like. They meet a scale invariant features in the sense of critical phenomena, nor fractal properties. We illustrate their properties with some simple examples, in particular that of a shuffled lattice. Allen clear that universality and random matrix theory must somehow be connected to the universality of phase transitions, but while the physical equations describing phase transitions seem to match reality, many of the computational methods used to derive them have never been mathematically rigorous. Physicists will settle for comparison with nature. Mathematicians want proof. Proof that phase transition theory is correct, more detailed proofs that random matrices fall into the universality class, third-order phase transitions prove that such a class exists. For the physicists involved, the preponderance of evidence will suffice. The task now is to identify and characterize strong and weak coupling phases in more of the systems that exhibit the Tracy-Wyden distribution, such as growth models that predict and study new examples of Tracy-Wyden universality throughout nature. The telltale sign will be the tail of the statistical curves. Reported in 2010 that the interface between two phases of a liquid crystal material varies according to the Tracy-Wyden distribution. That Yuki had not collected enough data to plot extreme statistical outliers, such as probability spikes along the interface. When he was treated to plot the data again, the scientists saw the first glimpse of the left and right tail. Everybody only looks at the Tracy-Wyden peak. They don't look at the tails because they are very, very tiny things. Okay, so we have stochastic growth, particle phase transition, eigenvalue distribution, financial performance, wireless communication. Right in the middle is Tracy-Wyden distribution. Okay, I'm looking at particle models of quarks, bosons, and leptons. And here it says the neutrino has mass, but its origin remains mysterious since it derives from some mechanism other than the Higgs. That makes it primordial. In general, the more a particle particle interacts with the Higgs boson, the more mass it has. Furthermore, the frequent interactions with Higgs bosons makes those massive particles quantum mixtures of left and right-handed. String theory today looks almost fractal. The more closely people explore any one corner, the more structure they find. Some dig deeper into particular premises, others zoom out to try to make sense of grander patterns. The upshot is that string theory today includes much that no longer seems string. Those tiny loops of strings whose harmonics were thought to be formed for every particle of course known to nature, including those of gravity, hardly appeared anywhere on chalkboards at conferences. At last year's big annual string theory meeting with Stanford University string theorist Ella Silverstein, who used to punch people in the few giving a talk on string theory proper. A lot of the time she works on questions related to cosmology. One high point for string theory is a theory everything came in the late 90s when Malvazina revealed that a string theory, including gravity in 5 dimensions, was equivalent to a quantum field theory in 4 dimensions. So holographic. This ADS-CFT duality appeared to have provided a map for getting a handle on gravity, the most intransigent piece of the puzzle, by relating it to good old, well-understood quantum field theory. Quantum field theories were developed in the 50s to unify special relativity and quantum mechanics. They worked well enough for long enough so it didn't much matter that they broke down at very small scales and high energy. But today, when you visit them, you find stunning structures that came as a complete surprise. Every aspect of the idea that we understood quantum field theory turns out to be wrong. It's a vastly bigger beast. And so field theory is the right hand of ADS-CFT, our starting point. You start with a simplified type of quantum field theory that behaves the same way at small and large distances. If these specific kinds of field theories could be understood perfectly, answers to the questions might become clear. The idea is that if you understand the elephant's feet really, really well, you can interpolate in between and figure out what the whole thing looks like. System is water at its critical point where the distinction between gas and liquid disappears. It's interesting because water's behavior at the critical point is a complicated emergent system that arises from something simpler. As such, it could be hint at dynamics behind the emergence of quantum field theory. See it. Based on Hilbert space, recovering gravity from bulk entanglement. We examine how to construct a spatial manifold and its geometry from the entanglement structure of an abstract quantum state in Hilbert space. Given the decomposition of Hilbert space into a tensor product of factors, we consider a class of redundancy constraint states that generate the area law behavior for entanglement entropy usually found in condensed matter systems. Gap local Hamiltonian. Using mutual information to find a distance measure on the graph, we employ classical multi-dimensional scaling to extract the best-fit spatial dimensionality of the emergent geometry. We then show that entanglement perturbations on such emergent geometries naturally derive local modifications of spatial curvature which obey a spatial analog of Einstein's equation. The Hilbert space, corresponding to a region of flat space, is finite dimensional and scaled as the volume, though the entropy and the maximal change thereof scales like the area of the boundary. A version of the ER equals EPR conjecture is recovered in that perturbations that entangle distant parts of the emergent geometry generate a configuration that may be considered a highly quantum wormhole. studied how what seemed like intractable problems in mathematics were solved by imagining how the question might look to a string. For example, how many spheres fit inside a Calabi-Yau manifold, the complex folded shape, expected to describe how space-time is compactified. Mathematicians have been stuck that a two-dimensional string can wiggle around in such a complex space. As it wiggled, it could grasp new insights like a mathematical multi-dimensional lasso. This is the kind of physical thinking Einstein was famous for. Thought experiments like riding along with a light beam revealed E equals mc squared. Imagine falling off a building led to his biggest eureka moment of all. Gravity is not a force, it's a property of space-time. Using the physical intuition offered by strings, physicists produced a powerful formula for getting the answer to the embedded sphere question and much more. They got at these formulas using tools that mathematicians don't allow. And after string theorists found an answer, the mathematicians proved it on their own terms. This is the kind of experiment he explored. It's an internal mathematical experiment. Not only was the stringy solution not wrong, it led to field level winning mathematics. This keeps happening. The amplitude-hadron is a multi-dimensional object that can be used to calculate particle interactions. Physicists such as Chris Beam are applying techniques from string theory in special geometries where the amplitude-hadron is its best self. String theory has also made essential contributions to cosmology, the role that string theory has played in thinking about mechanisms behind inflationary expansion of the universe, the moments immediately after the Big Bang, where quantum effects met gravity head-on, is surprisingly strong, even though no strings are attached. They have used string theory to discover, among other things, ways to see potentially observable signatures of various inflationary ideas. Same insights could have been found using quantum field theory, but they weren't. It's much more natural in string theory with its extra structure. Inflationary models get tangled in string theory in multiple ways, not least of which is the multiverse. The idea that ours is perhaps of one of a multiple, infinite number of universes, each created by the same mechanism that begat our own. In string theory and cosmology, the idea of the landscape of possible universes became not just acceptable, but even taken for granted by a large number of physicists. The selection effect would be one part natural explanation for why our world is the way it is in a very different universe. We wouldn't be here to tell the story. This effect could be one answer to a big problem string theory was supposed to solve. As Bose put it, what picks out this particular theory is a standard model for the plethora of infinite possibilities. The selection effect is actually a good argument for string theory. The infinite landscape of possible universes can be directly linked to the rich structure that we find in string theory. The innumerable ways of string theory multidimensional space-time can be folded in upon itself. At the very least, a mature version of string theory with its mathematical tools that let researchers view problems in new ways has provided powerful new methods for seeing how seemingly incompatible descriptions of nature can both be true. The discovery of dual descriptions of the same phenomena pretty much sums up the history of physics. A century and a half ago, James Clerk Maxwell saw that electricity and magnetism were two sides of the same coin. Quantum theory revealed the connection between particles and waves. Now physics have strings. If it's too hard to get from A to B using quantum field theory, reimagine the problem in string theory. There's a path. Strings do things differently. It may take centuries to tie together all these loose strings to leave a coherent picture, but young researchers aren't bothered a bit. This generation never thought string theory was going to solve everything. We're not stuck. It doesn't feel like we're on the verge of getting it all sorted, but I know each day that I did the day before, so presumably we're getting somewhere. Spastic consistency checks all the time. Perhaps a true picture is more like the maps of an atlas, each offering very different kinds of information, each spotty. Using the atlas will require the physically fluent many languages, many approaches all at the same time. Their work will come from many different directions, perhaps far-flung. To accept our incredible leading cosmologists like Alan Guth and Stephen Hawking envisioned a universe as one of countless bubbles in a terribly frothy sea. This infinite multiverse would contain universes of constants tuned to any and all possible values, including some outliers like ours that have just the right properties to support life. In this scenario, our good luck is inevitable. A peculiar life-friendly bubble is all we could expect to observe. Modern physicists to believe we shouldn't be here. The meager dose of energy infusing empty space with the higher levels would rip the cosmos apart. It's a trillion, and have many more trillion times tinier than theory predicts. Trillion. For the minuscule amount of mass of the Higgs boson, its relative smallness allows big structures such as galaxies and humans to form by roughly 100 quadrillion times short of expectations. Finding that either of these constants seem a little would render the universe unlivable. Components of the multiverse idea might show that among the rare universes that support life, ours is statistically typical. The exact dose of vacuum energy, the precise mass of our underweight Higgs boson, and other anomalies must have high odds within the subset of habitable universes. The properties of this universe still seem atypical, even in the habitable subset, when it fails. Infinity sabotages statistical analysis. Currently inflating multiverse, where does any bubble that can form do so infinitely many times? How do you measure typical? In a single universe, cows born with two heads are rarer than cows born with one head. But in an infinitely branching multiverse, there are an infinite number of one-headed cows and an infinite number of two-headed cows. What happens to the ratio? For years, the inability to calculate ratios of infinite quantities has prevented the multiverse hypothesis from making testable predictions about the properties of this universe. But the hypothesis of return to a full-fledged theory of physics, the two-headed cow question demands of answer. That proposed in 1980 that a still second of exponential growth may have occurred at the start of the Big Bang. This would have ironed out any spatial variations as if there were wrinkles on the surface of an inflation balloon. The inflation hypothesis, though it is still being tested, shows with all available astrophysical data and is widely accepted by physicists. In the years that followed, Andre Linde of Stanford, Garth, and other cosmologists reasoned that inflation would almost inevitably beget an infinite number of universes. Once inflation starts, it never stops completely. In a region where it does stop, through a kind of decay that settles into a stable state, space and time gently swell into a universe. Like ours. Everywhere else, space-time continues to expand exponentially, bubbling forever. Each disconnected space-time bubble grows under the influence of different initial conditions tied to decays of varying amounts of energy. Some bubbles expand and then contract, while others spawn endless streams of daughter universes. The scientists presume that the eternally inflating multiverse will everywhere obey the conservation of energy, the speed of light, thermodynamics, general relativity, and quantum mechanics. But the values of the constants coordinated by these laws will likely to vary randomly from bubble to bubble. The multiverse model gained considerable traction in 1987 when Steven Weinberg used it to predict the infinitesimal amount of energy using the vacuum of empty space, a number known as the cosmological constant. denoted by the Greek letter lambda. Vacuum energy is gravitationally repulsive, meaning it causes space-time to stretch apart. Consequently, a universe with a positive value for lambda expands faster and faster. In fact, as the amount of empty space grows towards the future as a matter-free void. The universe with negative lambda eventually contracts in a big crunch. Physicists had not yet measured the value of lambda in our universe in 1987, but the relatively sedate rate of quantum expansion indicated that its value was close to zero. This flew in the face of quantum mechanical calculations suggesting lambda should be enormous, implying a density of vacuum energy so large that it would tear atoms apart. Somehow it seemed that our universe was barely diluted. Weinberg turned to a concept called entropic selection in response to the continued failure to find a microscopic explanation of the smallness of the cosmological constant. The causes the life forms from which observers of the universes are drawn require the existence of galaxies. The only values of lambda that can be observed are therefore those that allow the universe to expand slowly enough for matter to come together into galaxies. Weinberg reported the maximum possible value of lambda in a universe that had galaxies. Where the multiverse generates a prediction the most likely density of vacuum energy to be observed, given that observers must exist to observe it. A decade later, astronomers discovered that the expansion of the cosmos was accelerating at a rate that pegged lambda at 10 to the power negative 123 in units of Planck energy density. The value of a stack of zero might have applied an unknown symmetry in the laws of quantum mechanics. Explanation without a multiverse. Where this absurdly tiny value of the cosmological constant appeared random. We fell strikingly close to Weinberg's prediction. It was a tremendous success and very influential. The prediction seemed to show that the multiverse was planetary power after all. Close on the heels of Weinberg's success, Donahue and colleagues used the same entropic approach to calculate the range of possible values for the mass of the Higgs boson. The Higgs doles out mass to other elementary particles, and those interactions dial its mass up or down in a feedback effect. This feedback would be expected to yield a mass for the Higgs that is far larger than its observed value, making its mass appear to have been reduced by accidental cancellation between the effects of all the individual particles. Donahue's group argued that this accidental tiny Higgs was to be expected, given entropic selection. The Higgs boson was just 5 times heavier than complex life, engendering elements like carbon could not arise. Thus, a universe with much heavier Higgs particles could never be observed. Until recently, the leading explanation for the smallness of the Higgs mass was a theory called supersymmetry. But the simplest versions of the theory have failed extensive tests at the Large Hadron Collider near Geneva. Although new alternatives have been proposed, many particle physicists who consider the multiverse unscientific just a few years ago are now gradually opening up to the idea. I would email the impetus. Predicted multiverse theory has increased. Researchers have realized that the predictions by Weinberg and others were too naive. Weinberg estimates the largest lambda compatible with the formation of galaxies. That was before astronomers discovered many dwarf galaxies that could form in a universe in which lambda is 1,000 times larger. These more prevalent universes can also contain observers, making our universe seem atypical among observable universes. On the other hand, dwarf galaxies presumably contain fewer observers than full-size ones, and universes with any dwarf galaxies would therefore have lower odds of being observed. Researchers realized it wasn't enough to differentiate between observable and unobservable bubbles to accurately predict the expected properties of our universe. They needed to weigh the likelihood of observing certain bubbles according to the number of observers they contained, and build a buffer problem. Goff and other scientists thought to measure the odds of observing different kinds of universes. This will allow them to make predictions about the fundamental constants in this universe, all of which have a reasonably high odds of being observed. Scientists' early attempts involved constructing mathematical models of eternal inflation and calculating the statistical distribution of observers levels based on how many of each type arose in a given time interval. The time forming is to measure the final tally of universes at the end, depending on how the scientists define time in the first place. People are getting wildly different answers depending on which random cutoff rule they choose. Started several multiverse measures during the last few decades, looking for one that would transcend arbitrary assumptions. 3 years ago, proposed a measure in the form of an immortal watcher who serves through the multiverse counting events, such as the number of observers. The frequencies of events are then converted to probabilities, thus solving the measure problem. But the proposal was simply impossible upfront. The watcher broadcast survives crunching bubbles like an avatar in a video game, dying and bouncing back to life. In 2011, Goff and Vitaly Venturin, now of University of Minnesota Duluth, imagined a finite sample space. They randomly select a slice of space-time within the infinite multiverse. As the sample space expands, approaching but never reaching infinite size, it cuts through other universes, encountering events such as proton formation, star formation, or intergalactic wars. The events are logged in a hypothetical data bank until the sampling ends. The relative frequency of different events translates into probabilities and thus provides a predictive power. Anything that can happen will happen, but not with equal probability. Still beyond the strangeness of immortal watchers and imaginary databanks, both of these approaches necessitate arbitrary choices about which events should serve as proxies for life. Industrial observations of universes to be counted and converted to probabilities. Protons seem necessary for life, space wars do not. With the observers require stars, or is this too limited a concept of life? With either measure, choices can be made so that the odds stack in favor of our inhabiting a universe like ours. The degree of speculation raises doubts. Cosmic diamond. Bozo first encountered the measure problem in the 1990s with a graduate student working with Stephen Hawking, historian of black hole physics. Black holes prove there is no such thing as an omniscient measurer because someone inside a black hole, the event horizons beyond which no light can escape, has access to different information and events from someone outside, and vice versa. Bozo, another black hole specialist, thinks such a rule must be more general. He said, precluding solutions to the measure problem along the lines of the immortal watcher. Physics is universal, so we've got to formulate what an observer can in principle measure. That insight led Bozo to develop a multiverse measure that removes infinity from the equation altogether. Instead of looking at all of space-time, he homed in on a finite path in the multiverse called the causal diamond, representing the largest swath accessible to a single observer traveling from the beginning of time to the end of time. The finite boundaries of a causal diamond are formed by the intersection of two cones of light, like the dispersing rays from a pair of flashlights pointed towards each other in the dark. One cone points outward from the moment matter was created after a Big Bang, the earliest conceivable birth of an observer, and the other aims backwards from the furthest reaches of our future horizon, the moment when the causal diamond becomes an empty, timeless void, and the observer can no longer access information, linking cause to effect. Life in a causal diamond. Causal diamonds that produce more entropy contain more observers. Time and cosmological constant. Rare diamond, many observers. Our diamond. Common diamond, few observers. High entropy production. The infinite multiverse can be divided into finite regions called causal diamonds that range from large and rare with many observers left to small and common with few observers. Right. In this scenario, causal diamonds like ours should be large enough to give rise to many observers, but small enough to be relatively common. Bozo is not interested in what goes on outside the causal diamond, where infinitely variable, endlessly recursive events are unknowable, in the same way that information about what goes on outside a black hole cannot be accessed by the poor soul trapped inside. If one accepts that the finite diamond being all anyone can ever measure is also all there is, Bozo said, then there is indeed no longer a measure problem. In 2006, Bozo realized that his casual diamond record lent itself the even-handed way of predicting the expected value of the cosmological constant. Causal diamonds with smaller values of lambda would produce more entropy, a quantity related to disorder, or degradation of energy. Bozo postulated that entropy could serve as a proxy for complexity, and thus for the presence of observers. Unlike other ways of counting observers, entropy can be calculated using trusted thermodynamic equations. With this approach, Bozo said comparing universes is no more exotic than comparing pools of water to roomfuls of air. Using astrophysical data, Bozo with collaborators R.J. Krebs and Perez calculated the overall rate of entropy production in our universe. It primarily comes from light scattering off cosmic dust. The calculations predicted a statistical range of expected values of lambda. The known value, 10 to the minus 123, rests just left of the median. We honestly didn't see it coming, Bozo said. It's really nice because the prediction is very robust. Making predictions. Bozo and his collaborators' causal diamond measure has now racked up a number of successes. It offers a solution to a mystery of cosmology called the why now problem, which asks why we happen to live at a time when the effects of matter and vacuum energy are comparable, so that the expansion of the universe recently switched from slowing down, signifying a matter-dominated epoch, to speeding up, a vacuum energy-dominated epoch. Bozo's theory suggests it is only natural that we find ourselves at this juncture. The most entropy is produced and therefore the most observers exist, when universes contain equal parts vacuum energy and matter. In 2010, Harnick and Bozo used their idea to explain the flatness of the universe and the amount of infrared radiation emitted by cosmic dust. Last year, Bozo and his Berkeley colleague Lawrence Saul reported that observers made of protons and neutrons like us will live in universes where the amount of ordinary matter and dark matter are comparable, as is the case here. Right now, the causal path looks really good, Bozo said. A lot of things work out unexpectedly well, and I do not know of other measures that come anywhere close to reproducing these successes or featuring comparable successes. The causal diamond measure falls short in a few ways, however. It does not gauge the probabilities of universes with negative values of the cosmological constant. And its predictions depend sensitively on assumptions about the early universe at the inception of the future pointing light cone. The researchers in the field recognize its problem. By sidestepping the infinities underlying the measure problem, the cosmic diamond is an oasis of finitude into which we can sink our teeth. Friedman, who like Bozo began his career as a black hole specialist, said the idea of a cosmic patch, such as an entropy-producing diamond, is bound to be an ingredient of the final solution to the measure problem. We, Doug Willingham, and many other physicists consider it a powerful and compelling approach, but they continue to work on their own measures of the multiverse. Few consider the problem to be solved. Every measure involves many assumptions beyond merely that the multiverse exists. For example, predictions of the expected range of constants like length and the Higgs mass always speculate that bubbles tend to have larger constants. Clearly, this is a work in progress. The multiverse is regarded either as an open question or off the wall. But ultimately, if the multiverse does become a standard public science, it will be on the basis of the most plausible explanation and the fine-tuning that we see in nature. Perhaps the multiverse theorists have chosen a Sisyphean task. Perhaps they will never settle the two-headed cow question. Some researchers taking a different route to testing the multiverse rather than rifle through the infinite possibilities of the equations. They are scanning the finite sky for the ultimate primary pass. A faint tremor from an ancient bubble code. Early in cosmic history, a universe may have bumped into another, a primordial clash that could have left traces of the Big Bang's afterglow. The universe that we inhabit had long collided with another universe. The crash would have left an imprint on the cosmic microwave background, the faint afterglow from the Big Bang, and if physicists could detect such a signature, it would provide a window into the multiverse. Studying the multiverse by comparing it to a boiling cauldron, with the bubbles representing individual universes, isolated pockets of space-time. As the pot boils, the bubbles expand and sometimes collide. A similar process may have occurred in the first moments of the cosmos. Studying how a collision with another universe in the earliest moments of time would have sent something similar to a shockwave across our universe. We think we might be able to find evidence of such a collision in data from refined space, which maps the CMB. Collision modes of a universe experienced a sudden burst of rapid expansion and instant after the Big Bang, growing up from an infinitesimal small speck to one spanning a quarter of a billion light years in mere fractions of a second. Once started, inflation tends to never completely stop. According to the theory, once the universe starts expanding, it will end in some places, creating regions like the universe we see all around us today, but elsewhere, inflation will simply keep on going eternally into the future. This feature is a cosmologist to contemplate a scenario called eternal inflation. In this picture, individual regions of space stop inflating and become bubble universes like the one in which we live. But on larger scales, exponential expansion continues forever, and new bubble universes are continually being created. Each bubble is deemed a universe in its own right, despite being part of the same space-time, because an observer could not travel from one bubble to the next without moving faster than the speed of light. But each bubble may have its own distinct laws of physics. Simulated multiverse with only two bubbles. They played what happened after the bubbles collided and determined what an observer would see. The team concluded that a collision of two bubble universes would appear to us as a disk on the CMB with a distinctive temperature profile. What a bubble collision would look like. An ancient collision with a bubble universe would have altered the temperature of the cosmic microwave background left, creating a faint disk in the sky right that could potentially be observed. We devised a set of algorithms to automatically search for these disks and data from the WMAP, a space-based report code. The program identified four potential regions with temperature fluctuations consistent with what could be a signature of a bubble collision. Imagine you start with a grid, but within an instant the grid is expanded to a massive size. Use techniques like adaptive mesh refinement and iterative process of winnowing out the most relevant details in such a grid at increasingly finer scales. An unusual type of traveling wave that might help simplify matters even further. 1834 in August, a Scottish engineer was conducting experiments along Union Canal with an eye towards improving the efficiency of the canal boats. One boat being drawn by a team of horses stopped suddenly. Russell noted a solitary wave in the water that kept rolling forward at a constant speed without losing its shape. The behavior was unlike typical waves which tend to flatten out or rise to a peak and topple quickly. Intrigued, Russell tracked the wave on horseback for a couple of miles before it finally dissipated in the channel waters. This was the first recorded observation of a soliton. Russell was so intrigued by the down the wave that he built a 30-foot wave tank in his garden to study the phenomenon, noting key characteristics of what he called the wave of translation. Such a wave can maintain size, shape, and speed over longer distances than usual. The speed depending on the wave's size and the width depending on the depth of the water. And if a large solitary wave overtook a smaller one, the larger, faster wave would just pass right through. Russell's observations were largely dismissed by his peers because his findings seemed to contradict what was known about water wave physics at the time. It wasn't until the mid-60s that such waves were dubbed solitons, and physicists realized their usefulness in modeling problems in diverse areas such as fiber optics, biological proteins, and DNA. Solitons also turn up in certain configurations of quantum field theory. Code the quantum field and will create an oscillation that usually dissipates outward, but configure things in just the right way, and that oscillation will maintain its shape. Just like Russell's wave of translation. Because solitons are so stable, Lynn believes they could work in a simplified toy model. The dynamics of bubble collisions in the multiverse, providing physicists with better predictions of what kinds of signatures might show up in the CMB. This left is right, the expanding walls of our bubble universe are much like solitons. Overall, it is a relatively straightforward matter to model a solitary standing wave. The dynamics become vastly more complicated and difficult to calculate when solitons collide and interact, forcing physicists to rely on computer simulations instead. In the past, researchers have used a particular class of soliton with an exact mathematical solution and tweaked that model to suit their purposes. But this approach only works if the target system under study is already quite similar to the toy model. Otherwise, the changes are too large to calculate. To get around that hurdle, Lynn devised a neat trick based on a quirky feature of soliton collisions. When you imagine two objects colliding, we naturally assume that the faster they are moving, the greater the impact, and the more complicated the dynamics. Two cars driving each other at high speed, for instance, will produce scattered debris, heat, noise, and other effects. The same is true for colliding solitons, at least initially. Collide two solitons very slowly, and there will be very little interaction according to Lynn. As the speed increases, the solitons interact more strongly. Computer model of a collision between two bubble universes. The collision would alter the patterns in the cosmic microwave background. What Lynn found, as the speed continues to increase, the pattern eventually reverses. The soliton interaction begins to decrease. By the time we are traveling at the speed of light, there is no interaction at all. They fly right past each other. Faster you fly the two solitons, the simpler it will become. The lack of interactions makes it easier to model the dynamics of colliding solitons, as well as colliding bubble universes with solitons as their edges, since the systems are roughly similar. According to Johnson, Lynn has uncovered a very simple rule that can be applied broadly. Multiverse interactions are weak during high-speed collisions, making it easier to simulate the dynamics of those encountered. Once we create a new model of the multiverse, use solitons as a tool to map the new model's expected signatures onto cosmic microwave data, and rule out any theories that don't match what researchers see. This process would help physicists identify the most viable models for the multiverse, which, while still speculative, would be consistent with both the latest observational data and with inflationary theory. The multiverse is key for string theory. One reason that more physicists are taking the idea of the multiverse seriously that certain such models could help resolve a significant challenge in string theory. One of the goals of string theory has been to unify quantum mechanics and general relativity, two separate rulebooks in physics that cover very different size scales, into a single simple solution. Around 10 years ago, real string theory exploded, and not in a good way. Researchers began to realize that string theory doesn't provide a unique solution, instead it gives you the theory of a vast number of worlds. A common estimate, one that Weinberg thinks is conservative, is 10 to the 500 possibilities. This monopoly of worlds implies that string theory can predict every possible outcome. The multiverse would provide a possible means of incorporating all the different worlds predicted by string theory. Each notion can be realized in its own double universe. Everything depends on which part of the universe you live in. Multiverse is combined with the theory of evolution. It resembles a topology in certain respects. An organism exists because it survived, yet it holds tremendous explanatory power. It is a simple model that requires little initial input to produce the vast diversity of species we see today. The multiverse model applies to eternal inflation to have the same kind of explanatory power. In this case, the bubble universes function much like speciation. Those universes will happen to have the right laws of physics will eventually succeed. That is, they will become home to conscious observers like ourselves. Our universe is one of many in a much larger multiverse. Our existence seems less likely. My own feeling is you need to adjust the numbers rather finely to get it to work. The rate of formation in the bubble universes is key. If it formed slowly, collisions would not have been possible. The states would have expanded and driven the bubbles apart long before any collision would take place. Alternatively, the bubbles have formed too quickly, they would have emerged before space could expand sufficiently to form disconnected pockets. Somewhere in between is the Goldilocks rate, the just right rate at which the bubbles would have had formed for a collision to be possible. Joint CMB might be evidence of theoretical entities called cosmic strings. These are like the cracks that form in the ice when the lake freezes over. Except here the ice is the fabric of space-time. Magnetic monopoles are another hypothetical defect that could affect the CMB, as the knots or twists in space-time called textures. If no new particles appear at the LHC and the Higgs remains astronomically fine-tuned lightly, then the multiverse hypothesis will strike into the limelight. It doesn't mean it's right that Bozo a long time supported the multiverse picture, but it does mean it's the only game in town. Modified naturalist says physicists might be misgauging the effects of other particles on the Higgs mass, and when calculated differently, the mass might appear natural. Modified naturalist falters on additional particles such as the unknown regions of dark matter included in calculations, but the same unorthodox path could yield other ideas. However, modified naturalists cannot fix an even bigger naturalist problem exists in physics. The fact that the cosmos wasn't instantly annihilated by its own energy the moments after the Big Bang. The energy built into the vacuum of space, known as vacuum energy, dark energy, or the cosmological constant, is a baffling trillion times smaller than what is calculated to be its natural, albeit self-destructive value. No theory exists about what could naturally fix this gargantuan disparity, but it's clear that the cosmological constant has to be enormously fine-tuned to prevent the universe from rapidly exploding or collapsing to a point. It has to be fine-tuned in order for life to have a chance to explain this absurd bit of luck. The multiverse idea has been growing mainstream in cosmology over the last few decades. We got a credibility boost in 1987, calculated that the cosmological constant or universe is expected in the multiverse scenario. Of the possible universes capable of supporting life, the only ones that can be observed and contemplated in the first place are just among the least fine-tuned. Yet the cosmological constant were much larger than the observed value, say by a factor of 10, then we would have no galaxies. It's hard to imagine how life might exist in such a universe. Most particle physicists hope that a more technical explanation of the cosmological constant problem would be found. None has. Now, physicists say the unnaturalness of the Higgs makes the unnaturalness of the cosmological constant more significant. Thinks the issues might even be related. We don't have an understanding of a basic extraordinary fact about our universe. It is big and has big things in it. The multiverse turned into slightly more than just a hand-waving argument in 2000 when Bozo and Polinsky found a mechanism that could give rise to a panorama of parallel universes. String theory posits that space-time is 10-dimensional. At the human scale, we experience just 3 dimensions of space at one time, but string theorists argue that 6 extra dimensions are problematic at every point in the fabric of our 4D reality. They calculate that there are around 10 to the power 500 different ways for those 6 dimensions to be knotted, all tying out varying amounts of energy, making inconceivably vast and diverse array of universes possible. In other words, naturalness is not required. There isn't a single, inevitable, perfect universe. It was a definite aha moment for me. Paper sparked outrage. Particle physics, especially string theorists, have this view of predicting unique to all the constants of nature. Everything will just come out of math and pi is 2. And we came in and said, look, it's not going to happen. There's a reason it's not going to happen. We're thinking about this in totally the wrong way. The Big Bang in the Bozo-Polinsky multiverse scenario is a fluctuation, a compact 6-dimensional knot that makes up one stitch in the fabric of reality suddenly shapeshifts, releasing energy that forms a bubble of space and time. Properties of this new universe are determined by chance, the amount of energy unleashed during the fluctuation. The vast majority of universes that burst into being in this way are thick with natural energy. They either expand or collapse so quickly that life cannot arise in them. Like some atypical universes in which an improbable cancellation yields a tiny value, like the cosmological constant, are much like ours. In the multiverse scenario, a vast and diverse array of double universes fluctuate into existence inside a larger vacuum. A small fraction of the universes have physical properties conducive to life. In the paper posted last month, Lawrence Hall argues that the Higgs boson makes sense in the multiverse scenario. We found that bubble universes that contain enough visible matter compared to dark matter to support life most often have supersymmetric particles beyond the energy range of the LHC, and the finely tuned Higgs boson would be one of them. Similarly, other physicists showed in 1997 that the Higgs boson were 5 times heavier than it is. This would suppress the formation of atoms other than hydrogen, resulting by yet another means in a lifeless universe. Despite these seemingly successful explanations, many physicists worry that there was little to be gained by adopting this worldview. At multiverse impacts. Main theory of scale. Mass and length may not be fundamental properties of nature. So the new idea filtering out of the multiverse. The galaxy was larger than atoms and elephants appear that way, and some physicists have expect the size differences are illusory. Perhaps the fundamental description of the universe does not include the concepts of mass and length, implying that at its core, nature lacks a sense of scale. This misunderstood idea known as scale symmetry constitutes a radical departure from long-standing assumptions about how elementary particles are their properties. It has recently emerged as a common theme of numerous talks and papers by respected particle physicists. With their field stuck by the nasty impasse, the researchers have returned to the master equations and described the particles on their interactions and are asking, what happens when you erase the terms in the equation having to do with mass and length? Nature at its deepest level may not differentiate between scales. With scale symmetry, physicists style with a basic approach that sets forth a massive collection of particles, each unique confluence of characteristics such as whether it is matter or antimatter and has positive or negative electric charge. As these particles attract and repel one another and the effects of their interactions cascade like dominoes through the calculations, scale symmetry breaks, and massive lengths spontaneously arise. Thermodynamic effects generate 99% of the mass of the visible universe. Protons and neutrons are amalgams, each one a trio of lightweight elementary particles called quarks. The energy used to hold these quarks together gives them a combined mass of around 100 times more than the sum of the parts. Most of the mass that we see is generated in this way, so we are interested in seeing if it's possible to generate all mass in this way. The standard approach to doing calculations, the Higgs boson interactions with other particles tends to elevate its mass towards the highest scales present in the equations, dragging the other particle masses up with it. Quantum mechanics tries to make everybody democratic. Particles will even each other out through quantum mechanical effects. This democratic tendency wouldn't matter if standard model particles were the end of the story. What physicists surmise is far beyond the standard model at a scale about a billion times heavier, known as the Planck mass. There exists unknown science associated with gravity. These heavyweights would be expected to fatten up the Higgs boson, process that would pull the mass of every other elementary particle up to the Planck scale. This hasn't happened. Instead, an unnatural hierarchy seems to separate the lightweight standard model particles and the hypothetical particles believed to exist at the Planck scale, right, are about a billion times heavier than the known particles left. The tendency of particle masses to be equalized in calculations makes this a puzzling hierarchy. Supersymmetry particles. Supersymmetry theory posits the existence of a twin for each of the known particles, counteracting the particle's tendency to escalate to the Planck scale. As of yet, no supersymmetric twins have turned up at the Large Hadron Collider. Scale symmetry. The new idea is that particles attain their masses as a result of scale symmetry breaking. The underlying theory of nature lacks any concept of mass, and independent quantum effects cause mass to arise at two widely separated scales. With the scale symmetry approach Darwin calculated the standard model masses in a novel way that did not involve them smearing towards the highest scales. From this perspective, the lightweight Higgs seemed perfectly natural. Still, it wasn't clear how you could incorporate Planck scale gravitational effects into its calculations. For symmetry, each particle had a slightly heavier twin. So the electron had the hypothetical electron combined effects would nearly cancel out, providing the Higgs mass from the moving towards the highest scales, like the physical equivalent of x plus negative x equals 0. Supersymmetry would protect the small but non-zero mass of the Higgs boson. The theory seemed like the perfect missing ingredient to explain the mass of the standard model. So perfect that without it, some theories say the universe simply doesn't make sense. Decades after the prediction, none of the supersymmetric particles have been found. That's what the LHC has been looking for, but it hasn't seen anything. Somehow, the Higgs is not protected. The LHC will continue probing for convoluted versions of supersymmetry, and it switches back on next year, but many physicists have grown increasingly convinced that the theory has failed. Researchers analyzing the largest data set yet, and the LHC have found no evidence of supersymmetric particles. The multiverse hypothesis has surged in progressive popularity in recent years, but the argument feels like a cop-out to many, or at least a letdown. The implications are enormous. Without supersymmetry, the Higgs boson mass if it was reduced not by mirror image effects, but by random and improbable cancellations between unrelated numbers. Essentially, the initial mass of the Higgs seems to exactly counterbalance the huge contribution to its mass from gluons, quarks, gravitational states, and all the rest. And if the universe is improbable, then many physicists argue that it must be one universe of many. Just a rare bubble in an endless, folding multiverse. We observe this particular bubble, the reasoning goes not because its properties make sense, but because the peculiar Higgs boson is conducive to the formation of atoms, and thus the rise of life. More typical bubbles with their plank-sized Higgs are uninhabitable. It's not a very satisfying explanation, but there's not a lot out there. A universe shaped by chance cancellations eludes understanding, and the existence of unreachable alien universes may be impossible to prove. And it's pretty unsatisfactory to use the multiverse hypothesis to explain only things we don't understand. People are forced to adjust. Basic equation of particle physics needs something extra to reign in the Higgs boson, and supersymmetry may not be it. Theorists like Linder have started asking, is there another symmetry that could do the job without creating this huge amount of particles we didn't see? Beginning of where Bardeen left off, researchers like Salvia, Struby, and Linder now think scale symmetry may be the best hope for explaining small mass of the Higgs boson. For me, doing real computation is more interesting than doing philosophy, even if it was possible that this multiverse could be right. For scale symmetric theory to work, it must account for both the small masses of the standard model and the gargantuan masses associated with gravity. In the ordinary approach to doing the calculations, both scales are put in by hand at the beginning, and when they connect in the equations, they try to even each other out. But in the new approach, both scales must arise dynamically and separately, starting from nothing. The statement that gravity might not affect the Higgs mass is very revolutionary. A theory called A-dimensional gravity, or A-gravity, developed by Salvia and Strumian, will be the most concrete realization of the scale symmetry idea so far. A-gravity leads the laws of physics at all scales into a single cohesive picture. The Higgs mass and the Planck mass both arise through separate dynamic effects. As detailed in June in the Journal of High Energy Physics, A-gravity also offers an explanation for why the universe inflated into existence in the first place. According to the theory, scale symmetry breaking would have caused an exponential expansion in the size of space-time during the Big Bang. However, the theory has what most experts consider a serious flaw. It requires the existence of strange particle-like entities called ghosts. Ghosts either have negative energy or negative probabilities of existing, both of which wreak havoc on the equations of the quantum world. Negative probabilities rule out the probabilistic interpretation of quantum mechanics, so that's a dreadful option. The Kelly split. Who first showed in 1977 that certain gravity theories gave rise to ghosts. Such theories can only work if the ghosts somehow decouple from the other particles and speak to themselves. Many attempts have been made along these lines. It's not a dead subject. Rather, it's technical and without much joy. Strumian and Salvia think that given all the advantages of a gravity, ghosts deserve a second chance. When antimatter particles were first considered in equations, they seem like negative energy. They seem nonsense. Maybe these ghosts seem nonsense, but one can find some sensible interpretation. Meanwhile, other groups are crafting their own scale symmetric theories. Linder and colleagues have proposed a model with a new hidden sector particle, while Bardeen, Lycan, Marcella Farina, and Martin Roger, Fowler of Fermilab, and Wolfgang Almenser of the Fermi Institute for Theoretical Physics in Northern Canada argue in an August 14th paper that the scales of the third model and gravity are separated as if by a phase transition. Researchers have identified a mass scale where the Higgs boson stops interacting with other particles, causing the masses to drop to zero. It is at the scale 3 point that a phase change like crossover occurs. And just as water behaves differently than ice, different sets of self-contained laws operate above and below this critical point. And negative energy, of course, exists in the universe as a Casimir effect, negative energy density. And we've also discovered negative mass now in plasma. To get around the lack of scales, the new models require a calculation technique that some experts consider mathematically dubious. And in general, few will say that they really think of the whole approach. Two different knew, but A gravity and the other scales in other models each predict the existence of new particles beyond the standard model. And so future collisions, the upgraded LMC will help test the ideas. Meanwhile, there's a sense of rekindling of hope. Maybe the mathematics is wrong, but the alternative is a multiverse landscape that is a pretty drastic step. So let's see what else might be. Number theory, algebra, and string theory. In 1978, mathematician John Mackay noticed what seemed like an odd coincidence. He had been studying different ways of representing the structure of a mysterious entity called a monster group, a gargantuan algebraic object that mathematicians believe captured a new kind of symmetry. Mathematicians weren't sure that the monster group actually existed, but they knew that if it did exist, it acted in special ways in particular dimensions. The first two of which were 1 and 196,883. Mackay of Concordia in Montreal picked up a mathematics paper in a completely different field involving something called the J function, one of the most fundamental objects in number theory. Strangely enough, this function's first important coefficient is 196,884, which Mackay instantly recognized as the sum of the monster's first two special dimensions. As mathematicians discussed the finding of a fluke, since there was no reason to expect the monster and G function to be even remotely related. However, the connection caused the attention of John Thomson, a field fellow now at the University of Florida, who made an additional discovery. The J function's second coefficient, 21,493,760, is the sum of the first three special dimensions of the monster. 1 plus 1,983 plus 21,296,877. It seemed as if the J function was somehow confirming the structure of the elusive monster group. Even though the mathematicians would demonstrate so many of these numerical relationships that it no longer seemed possible that they were mere coincidences. The paper called Monstrous Moonshine compare conjectured that these relationships also were in connection with the monster group and the J function. He called it moonshine because it appeared so far-fetched. Institute of Mathematics in Bonn, Germany. It was such a wild idea that it seemed like wishful thinking that might be anyone could ever prove that. It took several more years before mathematicians succeeded in even constructing the monster group. But they had a good excuse. The monster has more than 53 elements, which is more than the number of atoms of 1,000 Earths. In 1992, a decade after Robert Greaves of the University of Michigan constructed the monster, Richard Borchert tamed the wild idea of monstrous moonshine, eventually earning a Fields Medal. There was a bridge between the two disparate realms of mathematics in which the monster J function was mainly string theory. The counterintuitive idea of the universal mathematics involved a measure in which strings vibrate to produce the physical effect you experience at the microscopic scale. Boyle's discovery touched off a revolution in pure mathematics, leading to a new field known generalized as back-moody algebra, where the string theory point of view was something of a back level. The clinical dimensional string theory model that links the J function from the monster was far removed from the model string theorists were more excited about. It was being just like an esoteric corner of the theory without much physical interest, or it was math results were started. But now moonshine has undergone a renaissance, one that may eventually have deep implications for string theory. Over the past 5 years, starting with the discovery and analysis of the cave, mathematicians and physicists have come to realize that monstrous moonshine is just the start of the story. Last week, researchers posted a paper presenting a numerical proof of the so-called Umber-Moonshine conjecture formulated in 2012, which proposes that in addition to monstrous moonshine, there are 23 other moonshines, mysterious correspondences between the dimensions of the spectrum group, on the one hand, and the coefficients of a special function on the other. The coefficients of these new moonshines have their origins in a special letter by one of mathematically geniuses, written more than half a century before moonshine was even a glimmer in the mind. 23 means moonshines appear to be intertwined with some of the most central structures in string theory, four-dimensional objects known as case resources. The connection with Umber moonshine hints at hidden symmetries in the surfaces which we still need to understand. The new proof strongly suggests that in each of the 23 cases there must be a string theory model that holds the key to understanding these otherwise baffling numerical correspondence. But the proof doesn't go so far as to actually construct a relevant string theory model including physicists with the 10 rising problem. At the end of the day, we understand what moonshine is, but it will be in terms of physics. Symmetries of any given case have a natural sort of arithmetic. For example, rotating a square 90 degrees and flipping it horizontally is the same as flipping it across the diagonal. In other words, 90 degree rotation plus horizontal flip equals diagonal flip. In the 19th century, mathematicians realized that they could distill the type of arithmetic into an algebraic entity called a group. The same algebraic abstract group can represent the symmetries of many different shapes, giving mathematicians a tidy way to understand commonalities in different shapes. In the 20th century, mathematicians worked at all possible groups, and they gradually discovered something strange. Almost simple finite groups fell into natural categories, but with 26 oddballs into 5 categorizations. Of these, the biggest and last to be discovered was the monster. During the case discovery nearly 4 decades ago, there was no reason to think the monster group had anything to do with J functions. It was serendipitous discovery. The second protagonist of the monster's moonshine story. The J function belongs to a special class of functions whose graphs have repeating patterns, similar to M.C. Escher's tessellation of a disk with angels and devils, which shrinks ever smaller as they approach the outer boundary. These modular functions are the view of the number theory playing a crucial role, for instance, in Andrew Wild's 1994 proof of Fermat's last theorem. Anytime you hear about a striking result of number theory, there's a high chance that it's really a statement about modular forms. As with the sound wave, the J functions repeat the pattern, and it is broken down into a collection of pure tones, with coefficients indicating how loud each tone is. It is in these coefficients that McKay found a link to the monster group. It says of McKay's discovery by showing that there was a particular string theory model in which the J function and the monster group both roles. The coefficients in the J function count the way strings can oscillate at each energy level. And the monster group calculates the model symmetry of those energy levels. Finding the mathematicians a way to study the mind-boggling large monster group in the J function, whose coefficients are easy to calculate. Math is all about building bridges, where on one side you see more clearly than the other. But the bridge is so unexpectedly powerful that before you see the proof, it's kind of crazy. While mathematicians control ramifications of optics, moonshine string theories focus on a singularly different problem, figuring out the geometry for the tiny dimensions of which strings are hypothesized to live. Yet the geometry allows strings to vibrate in different ways, just as tightening the tension on a drum changes its pitch. For decades, they will struggle to find a geometry that produces the physical effect seen in the real world. And the ingredients, one of the most promising candidates for such geometry apart from a four-dimensional space known as K3 surfaces. In contrast with Bourdieu's string theory model, that uses K3 surfaces filled with string theory textbooks. Now enough is known about the geometry of K3 surfaces to count how many ways strings can oscillate at each energy level, but physicists can write down to a limited function, counting certain physical states that appear in all K3 surfaces. In 2010, three string theorists noticed that if they wrote this function in a particular way, out popped coefficients that were the same at some special dimensions of another oddball group called MATHAL24, the M24 group, which had nearly 250 million elements. The physicists have discovered a new moonshine. This time, physicists and mathematicians were all over the discovery. I went to several conferences and all of the talk was about this new MATHAL moonshine. It's a piece of paper with lots of numbers on it. The coefficients of some functions that we're studying called modular forms, which are related to modular functions. According to a particular line of numbers that ask and guess, I think if there is any finite group related to them. You recognize the numbers on another line, they belong to a special dimension of a group called M12. We poured over the rest of the paper, the pair together with Jeffrey Harvey, gradually realized that there was much more to the new moonshine than just the M24 example. But the clues of the true moonshine pictures we found lay in nearly centuries-old writings on one of mathematics' legendary figures. In 1913, the English mathematician G.H. Hardy received a letter from an accounting clerk at Madras, India, describing some mathematical formulas he had discovered. Many of them were old hat and some were flat out wrong. But on the final page were three formulas that blew Hardy's mind. It must be true of Hardy, who calmly invited the clerk to England, the Navasa and the job. Because if they were not true, no one would have the imagination to invent them. Ramanujan became famous for seemingly pulling mathematical relationships out of thin air. And he credited many of his discoveries to the goddess Namagiri, who appeared to him in visions, he said. His mathematical career was tragically brief. And in 1920, as he lay dying in India at age 32, he wrote Hardy another letter saying that he had discovered what he called Mach theta functions, which entered into mathematics beautifully. Ramanujan listed 17 examples of these functions, but didn't explain what they had in common. The question remained open for more than 8 decades. until Sanders Weisers, a graduate student of 8 years and now a professor at the University of Cologne, Germany, figured out in 2002 that they are all examples of what came to be known as Mach modular forms. During Ramanujan's final letter to G.H. Hardy in 1920, stating his discovery of what he calls Mach theta functions. After the Zurich-Moonshine Conference, Chang, Duncan, and Harvey gradually figured out that the M24 moonshine is one of 23 different moonshines, each making a connection between the special dimensions of the group and the coefficient of the Mach modular form. The monstrous moonshine made a connection between the monster group and the J function. For each of these moonshines, researchers conjectured there is a string theory, like the one in monstrous moonshine, in which the Mach modular form counts the certain state and the group captures the model's symmetry. A Mach modular form always has an associated modular function called its shadow, so they named the hypothesis modular moonshine conjecture. Many of the Mach modular forms appear in the conjecture among the 17 special examples that Ramanujan listed in his prophetic letter. Curious enough, Forcher's earlier proof of monstrous moonshine also builds on work by Ramanujan. The algebraic objects at the core of the proof were discovered by Franco Lapowski and Merrimont as they analyzed the three formulas that had so startled Hardy in Ramanujan's first letter. It's amazing that these two letters form the cornerstone of what we know about moonshine. Without either letter, we couldn't write this story. In the new paper, Duncan, Ono, and Ono's graduate student Michael Griffin have come up with a numerical proof of the Umbro moonshine conjecture. One case in which the M24 case had already been proven by Terry Gannon. The new analysis provides only hints of what physicists look for the string theories that will unite the groups of the Mach modular forms. Nevertheless, the proof of the conjecture is on the right track. We had all this structure and it was so intricate and compelling that it was hard not to think there was some truth to it. Having a mathematical proof makes it a solid piece of work that people can think seriously about. The string theory underlying Umbro moonshine is likely to be not just any physical theory, but a particularly important one. It suggests that there is a special symmetry acting on the physical theory of K3 surfaces. Researchers studying K3 surfaces can see the symmetry of T set, suggesting that there's probably a better way of looking at that theory that we haven't found yet. Physicists are also excited about a highly conjectural connection between moonshine and quantum gravity, yet undiscovered theory that will unite general relativity and quantum mechanics. Edward Whitney speculated that string theory in monstrous moonshine could offer a way to construct a model of three-dimensional quantum gravity, in which 194 natural categories of elements in the monster group correspond to 194 classes of black holes. Umbro moonshine will lead physicists to similar conjectures, giving hints of where to look for a quantum gravity theory. That is a big hope. The new numerical proof of the monster of the Umbro moonshine conjecture is like looking for an animal on Mars and seeing its footprint so we know it's there. Now researchers have defined the animal, the string theory, while it illuminates all these deep connections. We really want to get our hands on it. Why comparable? A multiverse explanation of the dark matter baryon coincidence. The density of dark and baryonic matter are comparable. This is surprising because they are controlled by different combinations of low-energy physics parameters. Here we consider the probability distribution over zeta in the landscape. We argue that the wide comparable problem can be solved without detailed but don't make assumptions and independently of the nature of dark matter. The reproduction of dark matter suppresses the probability like 1 zeta if the causal path is used to regulate infinities. This suppression can counteract the previous distribution favoring large zeta. The effect not only explains the wide comparable coincidence, but also renders otherwise implausible models of dark matter viable. For the special case of axion dark matter, Wilczek and independently Kerr-Legal have already noted that one called data suppression prevents overproduction of a GE2 scale UCD axion. That unified theory scale quantum chromodynamics axion. Dark matter is the LSP. The effect might explain the moderate fine-tuning of the weak scale in simple supersymmetric models. A modified naturalist principle and its experimental tests. Motivated by LHC results, we modified the usual criteria for naturalness by ignoring the uncomputable power divergences. The standard model satisfied the modified criterion. Finite naturalness for the measured values of its parameters. Extensions of the SM motivated by observation dark matter were treated with the strong CP problem vacuum instability inflation, satisfy finite naturalness in special ranges of their parameter spaces, which often define new particles below a few TeV. Finite naturalist bounds are weaker than usual naturalist bounds because any new particle with an SM gauge interaction gives a finite contribution to the Higgs mass at two loop order. Proof of the Umbro-Moonshine conjecture. The Umbro-Moonshine conjecture will say that there are finite dimensional graded modules that describe finite groups whose Minkowski-Thompson series of certain distinguished Mach modular forms. Gannon has proved this with a special case involving the largest periodic simple knockout group. Here we established the existence of the Umbro-Moonshine modules in the remaining 22 cases. Umbro-Moonshine. We describe surprising relationships between automorphic forms of various kinds, imaginary quadratic number fields in a certain systems of 6 finite groups that are all parameterized naturally by the divisors 12. The Markov group correspondence recently discovered by Iguchi Oguri-Takiwa recovered as a special case. We introduced a notion of extremal Jacobi form and proved that it characterizes the Jacobi forms arising by establishing connected critical values of Dirichlet series attached to modular forms of weight 2. These extremal Jacobi forms are closely related to certain vector values modular forms studied recently by Jacober, Marty Zeiger in connection with the physics of quantum black holes in string theory. In a manner similar to monstrous moonshine, the automorphic forms would in effect constitute evidence for the existence of infinite dimensional graded modules for the 6 groups in our system. We formulated an Umbro-Moonshine conjecture that was a direct analogy with the monstrous moonshine conjecture of Conway-Norton. Curiously, we find a number of Ramanujan's Mach theta functions appearing as Minkowski-Thompson series. These feature not appear in the monstrous case of the property which allows us to predict the fields of definition of certain homogeneous submodules for the groups involved. For 4 of the groups in our system, we find analogs of both the classical Minkowski correspondence and Minkowski monstrous Lincoln diagram observation manifesting simultaneously and compatibility. Electroweak and conformal symmetry breaking by a strong coupled sector. The LHC and their experiments show so far and show no signs of the physics, and while our beliefs about naturalness should be critically re-examined. We discuss, therefore, in the spatial model with a combined breaking of conformal electroweak symmetry by a strongly coupled hidden sector. Even though the conformal symmetry is anomalous, this may still provide an explanation of the smallness of electroweak scale compared to the Planck scale. Specifically, we start from a classically conformal model in which the strongly coupled hidden sector undergoes spontaneous Charles symmetry breaking. A coupling via a real scalar field transmits the breaking scale to the standard model Higgs and triggers electroweak symmetry breaking. The model contains dark matter candidates in the form of dark pions, and stability is being guaranteed by the flavor symmetry of the quartz sector. We study its relative abundance and direct detection prospects with the Nambu-Jonah-Rosinho method and discuss phase transition in the dark sector as well as the electroweak sector. A-gravity. We explore the possibility that the fundamental theory of nature does not contain any scale. This implies a renormalization. The renormalizable quantum gravity theory with the graviton-kinetic form a term has 4 derivatives and can be reinterpreted as gravity minus an anti-graviton. We compute the superplankton RGE of eight-dimensional gravity coupled to a generic matter sector. The Planck scale and the Planck space can now rise dynamically at quantum levels provided that a slight scalar coupling and the theta function vanish at the Planck scale. This is how the Higgs boson behaves. Mass of Higgs equals 125 gigaelectric volts and T equals 171 gigaelectrovolts. With an A-gravity inflation of a generic phenomenon, the slow roll parameters are given by the beta function of the theory and are small if couplings are perturbative. The predictions at S equals 0.967 and R equals 0.13 arise if the equation is identified with the Higgs of gravity. Furthermore, quadratically divergent corrections to the Higgs mass vanish. The small lead scale is natural and can be generated by A-gravity quantum correction. Watchers of the multiverse. An unresolved question of inflationary cosmology is the assignment of probabilities to different types of events that can occur in the eternally inflating multiverse. We explore the possibility that the resolution of this measure problem may rely on non-standard dynamics in regions of high curvature. But in particular, the Planck singularities at the future boundary of bubbles with negative vacuum energy density may lead to bounces, where contraction is replaced by inflationary expansion driven by different vacua in the landscape. Similarly, singularities inside of black holes might be gateways to other inflating vacua. This would drastically affect the global structure of the inflating multiverse. We consider a measure based on a probe geodesic which undergoes an infinite number of passages through crunches. This can be thought of as the whirlwind of internal watcher. Collecting data in an orderly fashion, we compare this to previous approaches to the measure problem. The watcher's measure is independent of initial conditions and does not suffer from ambiguities associated with the choice of a cutoff source. Another potential benefit from passing through crunches is that the observations collected by the watcher may easily depart from erraticity in very generic landscapes. This may significantly alleviate the problem of Boltzmann rain down. Internal inflation, global time cutoff measures, and a probability paradox. The definition of probability is an eternally inflating universe that requires to measure in order to regulate the infinite space-time volume, and much of the current literature uses global time cutoff for this purpose. Such measures have been found to lead to paradoxical behavior. Recently, Boltzmann and Friedel, Reichner, and Rosenhaus have argued that under reasonable assumptions, there is consistent interpretation of such measures is that time must end at the cutoff. Here we argue that there is an alternative consistent formulation of such measures in which time extends to infinity. Like formulations with a mathematical model of the infinite multiverse, which can be constructed without the use of a measure. Probabilities, which are all the same requirements for a probability measure, can then be defined by mathematical limits. There is a peculiar feature, however, which we call time delay bias. If the outcome of an experiment is reported with time delay that depends on the outcome, then the observation in the report will bias in favor of the shorter time delay. We show how the paradoxes can be resolved in this interpretation of the measure. Holographic probabilities and eternal inflation. In the global description of eternal inflation, probabilities for vacua and materialistic ambiguous. The local plane of view is preferred by holography and naturally picks out a simple probability measure. It is insensitive to large expansion factors or lifetimes and so resolves a recently noted paradox. Any cosmological measure must be complemented with the probability for observers to emerge in a given vacuum. In lieu of anthropic criteria, I propose to estimate by the entropy that can be produced by the local patch. This allows for prior free predictions. Predicting the cosmological constant from the causal and probate principle. We compute the expected value for the cosmological constant in our universe in the causal entropic principle. Since observers must obey the laws of thermodynamics and causality, the principle asserts that physical parameters are most likely to be found in the range of values for which total entropy potential within a causally connected region is maximized. Despite the absence of more explicit criteria, the resulting probability distribution turns out to be in excellent agreement with observation. A particularly fine velocity of stars dominates the entropy production, demonstrating the remarkable power of the thermodynamic selection criteria. The alternative approach, weighing by the number of observers per baryon, is less well defined. It requires problematic assumptions about the nature of observers and yet prefers values larger than experimental bounds. Why comparable? I think I read this one already. I think I read this one also. Faith and Hilbert State. Yes. And I'm doing this one to Lagrange from 6th dimension. Okay, let's see. Okay, here's one I probably have. This one here. This is about K-space. Okay, so all this is done. Okay. Wow. Okay. So this is quite a bit. I am going to temporarily take a break. Like I did about 3 hours worth. So that should be plenty for now. I will take this up again in a little while. Hopefully, we'll have this completed by the end of the weekend. This was about a 3-hour tour, and I'm still not done. We still have a few things to go, including quantum gravity's time problem. Physicists find a way to see the grid, the quantum gravity grid. String theory only game in town, Albert Einstein, holograms, and quantum gravity. A hologram within a hologram, hints of solutions to black hole information paradox. So hopefully we'll have this done by the end of the weekend. For the time being, this will be it. And we should resume in a few hours. resume the rate of time. We will start with wormholes and white holes. I'll just make a mental note of that. Okay, we are resuming with part 40, type F of the origin series. Back to talking about statistics and natural order and universality. In 1972, the biologist Robert May devised a simple mathematical model that works much like an archipelago. Imagine an archipelago where each island hosts a single tortoise species and all the islands are connected, say by rafts of WhatsApp. Tortoises interact by dipping into one another's food supplies, their populations fluctuate. So in 1972, Robert May wanted to figure out whether a complex ecosystem can ever be stable, or whether interactions between species inevitably lead some to wipe out others. By index chance interactions between species as random numbers in a matrix, we calculated the critical interaction strength. A measure of the number of flat sand rats, for example, needed to destabilize the ecosystem. Below this critical point, all species maintain steady populations. Above it, the populations shot towards zero or infinity. Little did May know the tipping point he discovered was one of the first glimpses of a curiously pervasive statistical law. The law appeared in full form 2 decades later, when mathematicians Craig Tracy and Harold Widow proved that the critical point in the kind of model they used was the peak of a statistical distribution. In 1999, Gino Bay, Percy Deef, and Kurt Johansson discovered that the same statistical distribution also describes variations in sequences of Shepard's integers. Completely unrelated mathematical abstraction. Still, the distribution appeared in models of the wiggling perimeter of a bacterial colony and other kinds of random growth. Before long, it was showing up all over physics and mathematics. The question is why? Why does it pop up everywhere? Systems of many interacting components, be they species, integers, or subatomic particles, kept producing the same statistical curve, which has become known as the Tracy-Widom distribution. This puzzle curve seemed to be the complex cousin of the familiar bell curve or Gaussian distribution, which represents the natural variation of independent random variables, like the heights of students in a classroom or their test scores. Like the Gaussian, the Tracy-Widom distribution exhibits universality, a mysterious phenomenon in which diverse microscopic effects give rise to the same collective behavior. The surprise is as universal as it is. When uncovered, universal laws like the Tracy-Widom distribution enable researchers to accurately model complex systems whose inner workings they know little about, like financial markets, exotic phases of matter, or the internet. It's not obvious that you could have a deep understanding of a very complicated system using a simple model with just a few ingredients. Universality is the reason why theoretical physics is so successful. Universality is an intriguing mystery. Why do certain laws seem to emerge from complex systems, almost regardless of the underlying mechanisms driving those systems at the microscopic level? Now, a surprising explanation for the ubiquitous Tracy-Widom distribution is beginning to emerge. Lopsided curve. The Tracy-Widom distribution is an asymmetrical statistical bump steeper on the left side than the right. Suitably scaled, its summit sits at a telltale value, the square root of 2n, the square root of twice the number of variables in the systems that give rise to it, and the exact transition point between stability and instability that May calculated for his model ecosystem. The transition point corresponded to a property of a matrix model called the largest eigenvalue, the greatest in a series of numbers calculated from the matrices of rows and columns. Researchers had already discovered that n eigenvalues of a random matrix, one filled with random numbers, tend to space apart along the real number line according to a distinct pattern. The The largest eigenvalue typically located at or near the square root of 2n. Tracy and Wyndham determined how the largest eigenvalues of random matrices fluctuate around this average value, piling up into the lopsided statistical distribution that bears their names. When the Tracy-Wyndham distribution turned up in the next integer sequences problem in other contexts that had nothing to do with random matrix theory, researchers began searching for the hidden thread, tying all its manifestations together just as mathematicians in the 18th and 19th centuries sought a theorem that would explain the ubiquity of the bell-shaped Gaussian distribution. The central limit theorem, which was finally made rigorous about a century ago, certified for test scores and other uncorrelated variables, meaning any of them can change without affecting the result, will form a bell curve. By contrast, the Tracy-Wyndham curve appears to arise from the variables that are strongly correlated, such as interactive species, stock markets, and matrix eigenvalues. The feedback loop of mutual effect between the correlated variables makes their collective behavior more complicated than that of uncorrelated variables, like test scores. While researchers have rigorously proved certain classes of random matrices in which the Tracy-Wyndham distribution universally holds, they have a looser handle on manifestations and counting problems, random walk problems, growth models, and beyond. Whereas uncorrelated random variables in the test scores play out into the bell-shaped Gaussian distribution, interacting species, financial stocks, and other correlated variables give rise to a more complicated statistical curve. Steeper on the left than on the right, the curve has a shape that depends on n, the number of variables. No one really knows what you need in order to get Tracy-Wyndham, said a mathematical physicist at Technical University of Bonn, Munich, Germany. The best we can do, he said, is to gradually uncover the range of its universality by tweaking systems that exhibit the distribution, seeing whether the variance give rise to it too. So far, researchers have characterized three forms of the Tracy-Wyndham distribution, rescaled versions of one another that describe strongly correlated systems with different types of inherent randomness. But there could be many more than three, perhaps even an infinite number, of Tracy-Wyndham universality classes. The big goal is to find the scope of universality of the Tracy-Wyndham distribution. How many distributions are there? Which cases give rise to which ones? As other researchers identify further examples of the Tracy-Wyndham peak, collaborators are hunting for clues in the curve's left and right tails. Going through a phase. Wyndham became interested in the problem in 2006 during a workshop at the University of Cambridge in England. He met a pair of physicists who were using random matrices to model string theory's abstract space of all possible universes. The string theorists reasoned that stable points in this landscape corresponded to the subset of random matrices whose largest eigenvalues were negative, far to the left of the average value of the square root of 2n at the peak of the Tracy-Wyndham curve. They wondered just how rare these stable points, the peak of viable universes, might be. To answer the question, Magenta and David Dean, now at the University of Bordeaux in France, realized that they needed to derive an equation describing the tail to the extreme left of the Tracy-Wyndham peak, a region with statistical distribution that had never been studied. Within a year, their derivation of a left large deviation function appeared in physical review letters. Using different techniques, Magenta and Massimo Virgiosola of Castro Institute in Paris calculated the right large deviation function 3 years later. On the right, Magenta and Dean were surprised to find that the distribution dropped off at a rate related to the number of eigenvalues n. On the left, it tapered off more quickly as a function of n squared. 2011, the form of the left and right pole gave Magenta Schur and Peter Forster of the University of Melbourne in Australia a flash of insight. They realized the universality of the Tracy-Witten distribution could be related to the universality of phase transitions. Events such as water freezing into ice, graphite becoming diamond, and ordinary metals transforming into strange superconductors. Because phase transitions are so widespread, all substances change phase when fed or starved of sufficient energy, and take only a handful of mathematical forms. They are for statistical physicists almost like a religion. In the minuscule margins of the Tracy-Witten distribution, William Darcher and Forrester recognized familiar mathematical forms, distinct curves, describing two different rates of change in the properties of a system, sloping downward from either side of a transitional peak. These were the trappings of a phase transition. In the thermodynamic equation describing water, the curve that represents the water's energy as a function of temperature has a kink at 100 degrees Celsius, the point at which the liquid becomes steam. The water's energy slowly increases up to this point, suddenly jumps to a new level, then slowly increases again, along a different curve in the form of steam. Crucially, where the energy curve has a kink, the first derivative of the curve, another curve, that shows how quickly the energy changes at each point as a peak. Similarly, the physicists realized the energy curves of certain strongly correlated systems have a kink at square root of 2n. The associated peak for these systems is the Tracy-Witten distribution, which appears in the third derivative of the energy curve. That is the rate of change of the energy's rate of change. This makes the Tracy-Witten distribution a third-order phase transition. The fact that it pops up everywhere is related to the universal character of phase transition, Schur said. This phase transition is universal in the sense that it does not depend too much on the microscopic details of your system. According to the formal details, the phase transition is separated phases of system with energy scaled with n squared on the left and n on the right. But Legendre and Schur wondered what characterizes Tracy-Witten universality class. Why do third-order phase transitions always seem to occur in systems of correlated variables? The answer was buried in a pair of esoteric papers in 1980. A third-order phase transition had shown up before, identified that year in a simplified version of theory governing atomic nuclei. The theoretical physicists Daniel Gross, Edward Witten, and Benta Raniel discovered a third-order phase transition separating a weak coupling phase, in which matter takes the form of nuclear particles, and a higher temperature strong coupling phase, in which matter melds into plasma. After the Big Bang, the universe probably transitioned from a strong to a weak coupling phase as a core. After examining the literature, Schur said he and Legendre realized there was a deep connection between our probability problem and this third-order phase transition that people had found in a completely different context. Weak to strong. Legendre and Schur have since approved substantial evidence that the Tracy-Witten distribution and its large deviation tails represents a universal phase transition between weak and strong coupling phases. In main ecosystem model, for example, the critical point at square root of 2n separates a stable phase of weakly coupled species whose populations can fluctuate individually without affecting the rest of an unstable phase of strongly coupled species in which fluctuations cascade throughout the ecosystem and throw it off balance. In general, Majumdar and Schur believe systems in the Tracy-Witten universality class exhibit one phase in which all components act in concert, and another phase in which the components act alone. The asymmetry of the statistical curve reflects the nature of the two phases. Because of mutual interaction between the components, the energy of the system in the strong coupling phase on the left is proportional to n squared. Meanwhile, in the weak coupling phase on the right, the energy depends only on the number of individual components, n. Whenever you have a strongly coupled phase and a weakly coupled phase, Tracy-Witten is a connecting crossover function between the two phases. Majumdar and Schur's work is a very nice contribution. The Pierre Roussel, a physicist of École Normale Supérieure in France, who helped prove the presence of the Tracy-Witten distribution in a stochastic growth model called the KPZ equation. Rather than focusing on the peak or the Tracy-Witten distribution, the phase transition is probably the deeper level of explanation, Roussel said. It could basically make us think more about trying to classify these third-order transitions. Rio Canadan, the statistical physicist who introduced the term universality and helped classify universal phase transitions in the 1960s, said it was long and clear to him that universality in random matrix theory must somehow be connected to the universality of phase transitions. But while the physical equations describing phase transitions seem to match reality, many of the computation methods used to derive them have never been made mathematically rigorous. Physicists will in a pinch go for a comparison with nature, Kavanaugh said. Mathematicians want proofs. Proof that phase transition theory is correct. More detailed proofs that random matrices fall into the universality class of third-order phase transition proves that such a class exists. For the physicists involved, a preponderance of evidence will suffice. The task now is to identify and characterize strong and weak coupling phases in more of the system that exhibit the Tracy-Witten distribution. Its growth models and to predict and study new examples of Tracy-Witten universality throughout nature. The telltale sign will be the tales of the statistical curves. At a gathering of experts in the field in Japan in August, Roussel encountered Kazumasa Takeuchi, University of Tokyo physicist, who reported in 2010 that the interface between two phases of liquid crystal materials varied according to the Tracy-Witten distribution. 4 years ago, Takeuchi had not collected enough data to plot extreme statistical outliers such as prominent spikes along the interface. Going with Roussel treated Takeuchi to plot the data again, the scientists saw the first curves of the left and right tail. Roussel immediately emailed Majumdar with the news. Everybody only looks at the Tracy-Witten peak, Majumdar said. We don't look at the tails because they are very, very tiny things. Now here's an article about a possible third-order phase transition of the large N Lattice gauge theory. The large N limit of the three-dimensional U-N Wilson Lattice gauge theory is explicitly evaluated for all fixed lambda equals g squared n by sequence descent methods. The lambda dependence was discussed in the third-order phase transition at lambda equals 2 is discovered. The possible existence of a weak to strong coupling third-order phase transition in the large N four-dimensional Lattice gauge theory is suggested, and its meaning and implication are discussed. So that was to conclude the statistical portion of the show, showing universality, numbers, across many different kinds of groups, and I believe that this is pretty fantastic. This has a string theory and cosmology aspect to it, of course, which is why I was discussing it. even though it's sort of just one of the different things that appear in those concepts. But I believe that this is more research for the future. And so, I will conclude for this portion, and the next portion will return to discussing wormholes and white holes. So hopefully you stay tuned. The next part will commence shortly. Okay, I accidentally left this paper out of the previous version, which was 40F, so this is 40G. I'm including this paper. Random matrices, universality, phenomenon for Wigner ensembles. In this paper, we survey some recent progress on rigorously establishing the universality of various spectral classes and statistics of Wigner, furnishing random matrix ensembles, focusing on the Lohmann theorem and its refinements and applications, including universality, the sign kernel, and the central limit theorem of several spectral parameters. We also took the opportunity here to issue some errata for previous papers in this area. After that, there was another one in here. Also should be included. This one's large deviations with extreme eigenvalues of random matrices. We calculate analytically the probability of large deviations from its mean of the largest smallest eigenvalue of random matrices belonging to the Gaussian orthogonal unitary and symplectic ensembles. In particular, we show that the probability that all the eigenvalues of n times n random matrix are positive, negative decreases for large n as approaches the exponent bracket negative beta, theta, 0, n squared, where the parameter beta characterizes the ensemble and the exponent beta 0 equals natural logarithm 3 divided by 4 equals 0.274. 653 is universal. We also calculate exactly the average density of states in matrices whose eigenvalues are restricted to be larger than the fixed number psi. That's generalizing the celebrated Wigner semicircle law. The density of states generically exhibits an inverse square root singularity at psi. Okay. Alrighty then. See if there's any other ones in here. Here's another one. Top eigenvalue of a random matrix, large deviations in third order phase transitions. From Ledemner and Scheer from January of 2014, 31st. We study the fluctuations of the largest eigenvalue, lambda max, and times n random matrices with the limit of large n. In the limit of large n, the main focus is on Gaussian beta ensembles, including in particular the Gaussian orthogonal beta equals 1, unitary beta equals 2, and symplectic beta equals 4 ensembles. The probability density function of lambda max is for large n of a central part inspired by Tracy with a distribution blank on both sides by 2 large deviation tails, while the central part characterizes the typical fluctuations of lambda max of order chi n to the negative 2/3. The large deviation tails are instead associated with extremely rare fluctuations of order phi 1. Here we review some recent developments in the field of this extremely rare events using a column gas approach. We discuss in particular the third order phase transition, which separates the left tail from the right tail, a transition akin to the so-called close-Witten-Wadia phase transition found in 2D lattice quantum chromodynamics. We also discuss the occurrence of similar third-order phase transitions in various physical problems, including non-intersecting Brownian motions, conductance, fluctuations in mesoscopic physics, and entanglement in a bipartite system. Alright. Here's another one. Universal fluctuations of growing interfaces, evidence in turbulent liquid crystals. June 11th, 2010. Akiuchi and Son. We investigate growing interfaces of topological defect turbulence in the electroconvection of pneumatic liquid crystals. The interfaces exhibit self-contained roughening characterized by both spatial and temporal scaling laws of the Carrara-Parisi-Zhang theory in 1+1 dimensions. Moreover, we reveal a distribution in the two-point correlation of the interface fluctuations of universal ones governed by the largest eigenvalue of random matrices. This provides quantitative experimental evidence of universality, prescribing detailed information of scale invariant fluctuations. Alright then, I believe that is it. And that covers the research associated with that paper. So we will next be moving on to white holes and wormholes. Finally. For that will be coming up very shortly. Okay, so this will begin part 47 officially, but it is also part 48. This is going to be about white holes and wormholes. On general relativity, a white hole is a hypothetical region of space-time and singularity that cannot be entered from the outside. Although energy, matter, light, and information can escape from it. In this sense, it's the reverse of a black hole, which can be entered only from the outside and from which energy, matter, light, and information cannot escape. White holes appear in the theory of eternal black holes in addition to a black hole region in the future. Such a solution of the Einstein field equation has a white hole region in its past. This region does not exist for black holes that have formed through gravitational collapse, however, nor are there any observed physical processes through which a white hole could have formed. Supermassive black holes are theoretically predicted to be at the center of every galaxy, and that possibly a galaxy cannot form without one. Stephen Hawking and others have proposed that these SDHs spawn a supermassive white hole Big Bang. This is very interesting. This is interesting about the Big Bang being a black or white hole. Big Bang model is distinct from a black or white hole. The real universe may be different from the FRW universe, so we can rule out the possibility. Can we rule out the possibility as a black or white hole? Possibility that the Big Bang is actually a white hole remains. It's not a black hole because black hole singularity is in the future while the Big Bang singularity was in the past. But the possibility that the Big Bang is actually a white hole remains. Major assumption of cosmology is that the universe is homogeneous and isotropic on large scales. That is, it looks the same everywhere and in every direction at any given time. There is good astronomical evidence that the distribution of galaxies is fairly homogeneous and isotropic on scales larger than a few hundred million light years. The high level of isotrope of the cosmic background radiation is strong, supporting evidence for homogeneity, but the size of the observable universe is limited by the speed of light and the age of the universe. We see only as far as about 10 to 20,000 million light years, so 10 to 20 billion light years, which is about 100 times larger than the scale on which structure is seen galaxy distribution. Homogeneity has always been a debated topic. The universe itself may well be many orders of magnitude larger than what we can observe, or it may even be infinite. Astronomer Mark Rees compares our view with looking out to sea from a ship in the middle of the ocean. As we look out beyond the local disturbances of the waves, we see apparently endless and featureless escape. From a ship in the horizon will only be a few miles away, and the ocean will stretch for hundreds of miles before they will land. When we look out in space with our large telescopes, our view is also limited to a finite distance. No matter how smooth it seems, we cannot assume that it continues like that beyond what we can see. So homogeneity is not certain on scales much larger than the observable universe. We might argue in favor of it on philosophical grounds, but we cannot prove it. In that case, we must ask if there was a white hole model for the universe that would be as consistent with observations as the FRW model. Some people initially think that the answer must be no, because white holes, like black holes, produce tidal portions that stretch and compress in different directions. Hence, they are quite different from what we observe. This is not conclusive because it applies only to the spacetime of a black hole in the absence of matter. Inside a star, the tidal forces can be absent. A white hole model that fits cosmological observations would have to be the time reverse of a star collapsing to form a black hole. To a good approximation, we could ignore pressure and treat it like a spherical cloud of dust with no internal forces other than gravity. Stellar collapse has been intensively studied since the seminal work of Snyder and Oppenheimer in 1939, and this simple case is well understood. It is possible to construct an exact model of stellar collapse in the absence of pressure by gluing together any FRW solution inside the spherical star and the Schwarzschild solution outside. Space-time within the star remains homogeneous and isotropic during the collapse. It follows that the time reversal of this model for a collapsing sphere of dust is indistinguishable from the FRW models if the dust sphere is larger than the observable universe. In other words, we cannot rule out the possibility that the universe is a very large black hole. Only by waiting many billions of years until the edge of the sphere comes into view could we know. It has to be admitted that if you drop the assumptions of homogeneity and isotropy, then there are many other possible cosmological models, including many with non-trivial topologies. This makes it difficult to derive anything concrete from such theories, but this has not stopped some brave and imaginative cosmologists thinking about them. One of the most exciting possibilities was considered by C. Hellevy in 1987, who envisioned a universe being created as a string of beads of isolated white holes that explode independently and coalesce into one universe at a certain moment. This is all described by a single exact solution of general relativity. There is one final twist to the answer to this question. It has been suggested by Stephen Hawking that once quantum effects are accounted for, the distinction between black holes and white holes might not be as clear as it first seems. This is due to Hawking radiation, a mechanism by which black holes can lose matter. A black hole in thermal equilibrium with surrounding radiation might have to be time symmetric, in which case it would be the same as a white hole. The idea is controversial, but if true, it would mean that the universe could be both a white hole and a black hole at the same time. Perhaps the truth is even stranger. In other words, who knows? That was very interesting. Okay. Let's get back to white holes. Like black holes, white holes have properties like mass, charge, and angular momentum. They attract matter like any other mass, but objects falling towards the white hole would never actually reach the white hole's event horizon. Or in the case of the maximally extended Schwarzschild solution, discussed below, the white hole event horizon in the past becomes a black hole event horizon in the future. So any object falling towards it will eventually reach the black hole horizon. Imagine a gravitational field without a surface. Acceleration due to gravity is the greatest on the surface of any body. Since black holes lack a surface, acceleration due to gravity increases, but it never reaches a final value as there is no considered surface in a singularity. That's why it increases exponentially. In quantum mechanics, a black hole emits Hawking radiation, and so if you come to thermal equilibrium with a gas of radiation, not compulsory. Because a thermal equilibrium state is time reversal invariant, Stephen Hawking argued that the time reversal of a black hole in thermal equilibrium results in a white hole in thermal equilibrium, each absorbing and emitting energy to equivalent degrees. Consequently, this may imply that black holes and white holes are the same structure, wherein the Hawking radiation from an ordinary black hole is identified with a white hole's emission of energy and matter. Hawking's semi-classical argument is reproduced in a quantum mechanical ADS-CFT treatment. String theory comes in. Where a black hole in anti-de Sitter phase is described by a thermal gas in a gauge theory whose time reversal is the same as itself. Very interesting. The possibility of the existence of white holes was put forward by Russian cosmologist Igor Novikov in 1964. White holes are predicted as part of a solution to the Einstein field equations known as the maximally extended version of the Schwarzschild metric, describing an eternal black hole with no charge and no rotation. Here, maximally extended refers to the idea that the space-time should not have any edges, or any possible trajectory of a free-falling particle following a geodesic in real space-time. It should be possible to continue this path arbitrarily far into the particle's future, unless the trajectory hits a gravitational singularity like the one at the center of the black hole's interior. In order to satisfy this requirement, it turns out that in addition to the black hole interior region, the particles enter when they fall through the event horizon from the outside. There must be a separate white hole interior region, which allows us to extrapolate the trajectories of particles that an outside observer sees rising up away from the event horizon. Where observer using Schwarzschild coordinates, infalling particles take an infinite time to reach the black hole horizon, infinitely far in the future, while outgoing particles that pass the observer have been traveled outward for an infinite time since crossing the white hole horizon infinitely far in the past. However, the particles or other objects experience only a finite, proper time between crossing the horizon and passing the outside observer. The black hole, white hole appears eternal from the perspective of an outside observer, in the sense that particles traveling outward from the white hole interior region can pass the observer at any time, and particles traveling inward, which will eventually reach the black hole interior region, can also pass the observer at any time. Just as there are two separate interior regions of the maximally extended spacetime, there are also two separate exterior regions, sometimes called two different universes. The second universe allowing us to extrapolate some possible particle trajectory in the two interior regions. This means that the interior black hole region can contain a mix of particles that fell in from either universe, and thus an observer who fell in from one universe might be able to see light that fell in from the other one. And likewise, particles from the interior white hole region can escape into either universe. All four regions can be seen in a space-time diagram that uses Kruskal's coordinates. Kruskal's diagram illustrated for 2GN equals 1. The quadrants are the black hole interior, the white hole interior, and the two exterior regions. The dark 35-degree lines which separate these four regions are the event horizons. The darker hyperbolas which draw the top and bottom of the diagram are the physical singularities. Halo hyperbolas represent contours of the source sharp R coordinate, and the straight lines through the origin represent contours of the source sharp C coordinate. In this space-time, it is possible to come up with coordinate systems such that if we take a hypersurface of constant time, a set of points that all have the same time coordinate, that every point on the surface of a space-like circle should give what is called a space-like surface, and draw an embedding diagram depicting the curvature of space at that time. The embedding diagram will look like a tube connecting the two exterior regions known as the Einstein-Rosen bridge, or Schwarzschild-Formula. Okay. Depending on where the space-time hypersurface is chosen, the Einstein-Rosen bridge will connect two black hole event horizons in each universe, with points in the interior of the bridge being part of the black hole region of space-time, or two white hole event horizons in each universe. Points in the interior of the bridge being part of the white hole region. It is impossible to use the bridge to cross from one universe to the other, however, because it is possible to enter a white hole event horizon from the outside, and anyone entering a black hole horizon from either universe will inevitably hit the black hole singularity unless it is a charged or spinning black hole. That's very important. Okay, so Further, the Maximus-Schwarzschild method describes an idealized black hole white hole that exists purely from the perspective of external observers of a more realistic black hole. Therefore, at some particular time from a collapsing star would require a different metric. While the influence stellar matter is added to a diagram of black hole's history, it removes the part of the diagram corresponding to the white hole interior region. But because the equations of general relativity are time reversible, they exhibit time reversal symmetry. General relativity must also allow the time reverse of this type of realistic black hole that forms from collapsing matter. The time reverse case would be a white hole that has existed since the beginning of the universe and that emits matter until it finally explodes and disappears. Despite the fact that such objects are permitted theoretically, they could exist only if they were built with the initial conditions of the Big Bang. Initially, this prediction that the white hole would be unstable in the sense that if any small amount of matter fell towards the horizon from the outside, this would prevent the white hole's explosion, as seen by distant observers, with the matter emitted from the singularity never able to escape the white hole's gravitational radius. The view of black holes, first proposed in the late 80s, might be interpreted as shedding light on the nature of classical white holes. Some researchers have proposed that when a black hole forms, a Big Bang may occur at the core singularity, which would create a new universe that expands outside of the parent universe. Very interesting. It's a Nikolai-Poplawski's conjecture. Big Bang may occur at the core singularity, which would create a new universe that expands outside of the parent universe. The Einstein-Cardan-Siamba-Kibble theory of gravity extends general relativity by removing a constraint of the symmetry of the affine connection regarding its asymmetric and asymmetric part, the torsion tensor, as a dynamical variable. Torsion naturally accounts for the quantum mechanical intrinsic angular momentum spin of matter. According to general relativity, the gravitational collapse of a sufficiently compact mass forms a singular black hole. In the Einstein-Cardan theory, however, the minimal coupling between torsion and Dirac spinors generates a repulsive spin-spin interaction that is significant in fermionic matter at extremely high densities. Such an interaction prevents the formation of a gravitational singularity. Instead, the collapsing matter on the other side of the event horizon reaches an enormous but finite density and rebounds. This is the big bounce, forming a regular Einstein-Rosen bridge. Very interesting. The other side of the bridge becomes a new growing baby universe. For observers in the baby universe, the parent universe appears as the only white hole. Accordingly, the observable universe is the Einstein-Rosen interior of a black hole existing as one of possibly many inside a larger universe. The Big Bang was a non-singular big bounce at which the observable universe had a finite minimum scale factor. Very important. A 2012 paper argues that the Big Bang itself is a white hole. It further suggests that the emergence of a white hole, which was named a small bang, is spontaneous. All the matter is ejected at a single pulse. Thus, unlike black holes, white holes cannot be continuously observed. Rather, their effects can be detected only around the event itself. The paper would propose identifying a new group of gamma-ray bursts with white holes. In 2014, the idea of the Big Bang being produced by a supermassive white hole explosion was explored in the framework of a five-dimensional vacuum. By Madrid, Aguilar, Moreno, and Bellini. Okay, so we're going to explore all of these. So this is very interesting. This is Universe at Home with Large Universe. This is Nicholas Pavlovsky's original paper. Wormhole research. Could our universe be located within the interior of a wormhole, which is itself part of a black hole that lies within a much larger universe? Such a scenario in which the universe is born from inside a wormhole, also called an Einstein-Rosen bridge, is suggested in a paper from Indiana University Theoretical Physicist Nicholas Pavlovsky in Physics Letters B. The final version of the paper is available online and will be published in the journal. Pavlovsky takes advantage of the Euclidean-based coordinate system called isotropic coordinates to describe the gravitational field of a black hole and to model the radial geodesic motion of a massive particle into a black hole. In studying the radial motion through the event horizon, the black hole's boundary of two different types of black holes, Schwarzschild and Einstein-Rosen, both of which are mathematically legitimate solutions of general relativity, Pavlovsky admits that the only experiment or observation can reveal the motion of a particle flowing into an actual black hole. But he also notes that since observers can only see the outside of the black hole, the interior cannot be observed unless an observer enters or resides within. This condition would be satisfied if our universe were the interior of a black hole existing in a bigger universe. Because Einstein's general theory of relativity does not choose a time orientation, if a black hole can form with a gravitational plastic matter through an event horizon in the future, then the reverse process is also possible. Such a process would describe an exploding white hole, matter emerging from an event horizon in the past, like an expanding universe. We find the connection. A white hole is connected to a black hole by an Einstein-Rosen bridge, wormhole, and is hypothetically the time reversal of a black hole. Pavlovsky's paper suggests that all astrophysical black holes, not just Schwarzschild and Einstein-Rosen black holes, may have Einstein-Rosen bridges, each with a new universe inside that forms simultaneously with the black hole. From that it follows that our universe could have itself formed inside a black hole existing inside another universe. By continuing to study the gravitational collapse of a sphere of dust in isotropic coordinates and by applying current research to other types of black holes, views where the universe is born from the interior of an Einstein-Rosen black hole could avoid problems seen by scientists with the Big Bang theory and the black hole information loss problem, which claims all information about matter is lost as it goes over the event horizon, in turn defying the laws of quantum physics. This model in isotropic coordinates of the universe of the black hole could explain the origin of cosmic inflation, Pavlovsky theorizes. Very interesting. Okay. So, We can go back and also read this. Cosmology with torsion, an alternative to cosmic inflation. We propose a simple scenario which explains why our universe appears spatially flat, homogeneous, and isotropic. We use the Einstein-Cartan-Kimmel X theory of gravity, which naturally extends general relativity to include the spin of matter. The torsion of space-time generates gravitational repulsion in the early universe, filled with quarks and leptons, preventing the cosmological singularity. The universe expands from a state of minimum of finite radius. We show that the dynamics of the closed universe immediately after this state naturally solves the flatness and horizon problem of cosmology because of an extremely small and negative torsion density parameter. Omega S is equivalent to minus 10 to the negative 69th power. Thus, the X-gravity provides a compelling alternative to speculative mechanisms of standard cosmic inflation. This scenario also suggests that the contraction of our universe preceding the bounce at the minimum radius may correspond to the dynamics of matter inside a collapsing black hole existing in another universe, which could explain the origin of the Big Bang. That is the superverse that we've been talking about. The larger universe. See, it's all connected. It works out. Non-singular big bounce cosmology from spinor torsion coupling. The Einstein-Cartan-Kimmel theory of gravity removes the constraint of general relativity, with the affine connection be symmetric by regarding its anti-symmetric part, the torsion tensor, as a dynamic variable. The minimal coupling between the torsion tensor and Dirac spinors generates a spin-spin interaction which is significant in fermionic matter at extremely high densities. We show that such an interaction averts the unphysical Big Bang theory, singularity, replacing it with a cusp-like bounce at a finite minimum scale factor before which the universe was contracting. This scenario also explains why the present universe at larger scales appears spatially flat, homogeneous, and isotropic. The revival of white holes or small bangs. Black holes are extremely dense and compact objects from which light cannot escape. There is an overall consensus that black holes exist, and many astronomical objects are identified with black holes. White holes are understood as the exact time reversal of black holes, therefore they should continuously throw away material. It is accepted, however, that a persistent ejection of mass leads to gravitational pressure, the formation of a black hole, and thus to the death of white holes. So far, no astronomical sources have yet been successfully tagged as a white hole. The only known white hole is the Big Bang, which was instantaneous rather than continuous or long-lasting. We thus suggest that the emergence of a white hole, which we name a small bang, is spontaneous. All the matter is ejected at a single pulse. Unlike black holes, white holes cannot be continuously observed, rather their effect can only be detected around the event itself. Gamma ray bursts are the most energetic explosions in the universe. Long gamma ray bursts were connected with supernova eruptions. There is a new group of gamma ray bursts which are relatively close to Earth but surprisingly lack any supernova emission. We propose identifying these bursts with white holes. White holes seem like the best explanation of gamma ray bursts that appear in voids. We also predict the detection of rare, gigantic gamma ray bursts with energies much higher than typically observed. Very interesting. So these white holes might be these gamma ray bursts. They're not associated with supernova explosions. Alrighty. The primordial explosion of a false white hole from a 5D vacuum. We explore the cosmological consequences of some possible Big Bang produced by a black hole with mass m in a 5-dimensional extended SDS. Space. Under these particular circumstances, the effective 4D metric obtained by the use of a constant foliation on the extra coordinates is comported as a false white hole, FWH, which evaporates for all unstable modes at a wavelength bigger than the size of the FWH. Basically, anything outside the white hole, see it evaporating. Outside the white hole, the repulsive gravitational field can be considered as weak, so that the dynamics for fluctuations of the inflation of the inflating field and the scalar perturbation of the metric can be linearized. Very interesting. Okay, so this article actually have a complete article here. In the last 2 decades, inflation cosmology has become the strongest candidate to explain the observed properties in the universe on cosmological scales. The fact is supported by experimental evidence. During this epoch, the energy density of the universe was dominated by some scalar field that played on with negligible kinetic energy. Density. In such a way that its corresponding vacuum energy density is responsible for the exponential growth of the scale factor of the universe. Along this second-order phase transition, a small and smooth region of the order of size of the Hubble radius includes so large that it easily encompasses the co-moving volume of the entire presently observed universe. And consequently, the observable universe became so spatially homogeneous and isotropic on scales today of the range 10 to the 8th to 10 to the 10th light years. There are plenty of stationary models, the majority of them in good concordance with observations, but none free of problems, as for example, the Transplanckian problem, the hierarchy problem, etc. This has led cosmologists to look for some new theoretical alternatives. Recently, we have suggested a new inflationary perspective from a 5D extended theory of general relativity, ETGR, in which we use a Ricci flat metric represented by a 5D line element. Here, it's a dimensionless metric function, psi is the space-like and non-compact fixed extra coordinate. The metric 1 is Ricci flat, furthermore, this is an extension to 5D spaces of 4D SDS metric. The coordinate t is a timeline, like c is denoting the speed of light, r, theta, t are the usual spherical polar coordinates. Psi 0 is arbitrary constant with length units, and the constant parameter v has units of mass length inverse, like so. As we show in 12, certain values of psi and chi and psi 0, the metric in 1 has 2 natural horizons. The inner one is analogous to the celestial horizon, and the external one is analogous to the Hubble horizon. What is it? Putting black holes in it, 2 horizons, the Gaussian horizon and the Lang horizon. A particular case of the metric is such that, in this case, there is a unique horizon which is false because it takes its sign for r. However, the metric will be filled at r equals 0. It can be seen more clearly in the writing function r in this section. First, the physical domain of interest is r is greater than 0. You can see that function r equals 0, however, b as 2 less than 0 has the same signature. So, basically, the rest of the article is a series of formulas. we shall study the cosmological consequences of some possible Big Bang produced by a black hole with mass M and define the extended SDS matrix. Under these particular circumstances, the effective 4D metric obtained by the use of foliation is computed as a false white hole, which is the closing matter is with lambda is greater than lambda W each white hole. The track mode with lambda is less than lambda white hole. The letter is organized as follows in section 2, develop 5D dynamics with scalar field fluctuations in the metric and the Frohman field of a weak field approximation. In section 3, we explore the effective 4D dynamics of these fields by using a semi-classical approximation for the inflated field. Furthermore, we calculate the squared field fluctuations for the quantum inflated fluctuations and metric fluctuations. These factors are well outside the FWH. Finally, in section 4, we give some final comments. So basically, this is going to be a whole bunch of equations. So I'm going to skip down to the final comments. We have studied an interesting case in which the universe expands on an effective 4D hypersurface obtained after take a constant foliation on the extra space-like coordinate of an extended SDS Ricci flat metric. The 4D effective spacetime describes a universe that expands on cosmological scales, but collapses on astrophysical ones. Because it has a black hole in its center, mass M equals chi 0, parentheses 3, square root of 3g. Under these circumstances, the universe behaves as a white hole that evaporates on scales greater than its radius. Which means, for anyone outside the universe, they see it disappearing quickly into its own dimension. Behavior in the universe on these large scales is similar to that of a white hole, so that we have called it a false white hole, FWH. We have studied the large-scale evolution of the scalar metric fluctuations and the quantum fluctuations of the metric. In both cases, the amplitude of the fluctuations decreases during inflation with power spectra that are nearly scale invariant. Logical skills. Okay. That was good. Actually, that was very good. The equations are basically the picture. They show how it's possible and how it's done. So, let me see if there's anything else left here in this discussion about this. Okay. So back to these Kruskal-Scuris coordinates. They apply to spacetime or a spherical object. But in that case, after a description of spacetime inside the radius of the object. Since the star remains outside the event horizon, the Kruskal coordinates crosses it in the Kruskal-Scuris coordinates. In any black hole which we observe, we see it at a time where its matter has not yet finished collapsing. So it is not really a black hole yet. Similarly, objects falling into a black hole remain outside the event horizon, in Kruskal coordinates, but cross it in Kruskal-Scuris coordinates. Okay. We have this gravitational constant multiplied by the Schwarzschild mass parameter. C equals 1. Kruskal-Skir's diagram. Each frame of the animation shows the blue hyperbola as the surface where the Schwarzschild radial coordinate is constant, and with the smaller value each successive frame until it ends at the singularities. It follows that on the union of the exterior region, the event horizon and the interior region of the Schwarzschild radial coordinate are not to be confused with the Schwarzschild radius RS equals 2gm, is determined in terms of Kruskal-Skir's coordinates as the unique solution of the equation. The coordinate of singularity is located at t squared minus x squared equals r sub s equals 2gm with the regular coordinate of the event horizon. Okay. The maximally extended Schwarzschild solution. The transformation between Schwarzschild coordinates and Kruskal-Skir's coordinates defined for r is greater than 2gm, and negative infinity is less than t, which is less than infinity, can be extended as an analytical function, at least the first singularity, which occurs at t squared minus x squared equals 1. Thus, the above metric is a solution of Einstein's equations throughout this region. The odd values are negative infinity is less than x is less than infinity. Negative infinity is less than t squared minus x squared, which is less than 1. Note that this extension assumes that the solution is analytic everywhere. In the maximally extended solution, there are actually two singularities at r equals 0, one for positive t and one for negative t. The negative t singularity is a time-reversed black hole, also a white hole. Particles can escape from a white hole, but they can never return. The maximally extended Schwarzschild geometry will be divided into 4 regions, each of which can be covered by a suitable set of Schwarzschild coordinates. The Kruskal-Skir's coordinates, on the other hand, cover the entire space-time back. The 4 regions are separated by event horizons. There is an exterior region minus x is less than t or less than plus x. 2gm is less than x. Interior black hole, the absolute value of x is less than t, which is less than the square root of 1 plus x squared. 0 is less than r is less than 2gm. Parallel exterior region plus x is less than t, which is less than minus x. 2gm is less than r. Interior white hole. Negative square root of 1 plus x squared is less than t, which is less than the absolute, but the negative absolute value of x. 0 is less than r is less than 2gm. Transformation given above, between Schwarzschild and Kruskal-Skir's coordinates apply only in regions 1 and 2, which is the exterior and interior black hole region. If we take the square root as positive or simple, similar transformation can be written down in the other 2 regions. They run from negative infinity to positive infinity, with the infinities at the event horizons. Based on the requirements of the quantum classical Hawking radiation is unitary, T. Hawk proposed that the regions 1 and 3 and 2 and 4 are just mathematical artifacts open using branches for roots rather than parallel universes. And the equivalence relation Tx omega equivalent to negative T negative x negative. Should be imposed where negative omega would be an antipode of omega on the 2 sphere. If we think of regions 3 and 4 as having spherical coordinates but with a negative choice for square root to compute r, then we just correspondingly use opposite points on the sphere to denote the same point in space. Corresponds to a sphere, the point Tx equals 0, 0, corresponds to the event horizon r equals 2gm in the Schwarzschild picture. Corresponds not to a sphere, but to the projective point rp squared equals x squared, plus minus. And the topology of the underlying manifold is no longer 4 quad minus line equals 4 squared times f squared. The manifold is no longer simply connected. It is a loop involving superluminal portions going from a point in spacetime back to itself, but at the opposite Kruskal-Skirov coordinates cannot be reduced to a null loop. Kruskal-Skirov coordinates have a number of useful features, which make them helpful for building intuition without source spacetime. Chief among these is the fact that all radio like geodesics, the roll line of light rays over the radio direction look like straight lines at a 45-degree angle when drawn. And a Kruskal-Skirov diagram. This can be derived from the metric equation given above, which guarantees that dx equals plus minus dt with the proper time, ds equals 0, all time like roll lines are filled in line objects so that every point have a slope close to the vertical time axis t coordinate. So light cone drawn t coordinate of 45 degrees. So light cone drawn in a Kruskal-Skirov diagram will look just the same as a light cone in a Minkowski diagram with special relativity. The event horizons bounding the black hole and white hole interior regions are also a pair of straight lines at 45 degrees, reflecting the fact that a light ray emitted at the horizon in a radial direction aimed outward in the case of a black hole, inward in the case of a white hole would remain on the horizon forever. Thus, the two black hole horizons coincide with the boundaries of the future light cone of an event at the center of the diagram at t equals x equals 0, while the two white hole horizons coincide with the boundaries of the past light cone of the same event. Any event inside the black hole interior region will have a future light cone that remains in this region such that any roll line within the event's future light cone will eventually hit the black hole singularity, which appears as a hyperbola bounded by the two black hole horizons. And any event inside the white hole interior region will have a past light cone that remains in this region, such that any roll line within this past light cone must have originated in the white hole singularity, a hyperbola bounded by the two white hole horizons. Note that although the horizon looks as though it is an outward expanding cone, the area of the surface is given by r is just 16 pi m squared, a constant. These coordinates can be deceptive if care is not exercised. It may be expected to consider what curves of constant Schwarzschild coordinate will look like if plotted on a Kruskal-Skirov diagram. It turns out that curves of constant r coordinates and Schwarzschild coordinates always look like hyperbolas bounded by a pair of event horizons at 45 degrees, while lines of constant t coordinates and Schwarzschild coordinates always look like straight lines at various angles passing through the center of the diagram. The black hole event horizon bordering exterior region 1 would coincide with the Schwarzschild t coordinate of plus infinity, while the white hole event horizon bordering this region would coincide with the Schwarzschild t coordinate of negative infinity, reflecting the fact that in Schwarzschild coordinates, the falling particle takes an infinite coordinate time to reach the horizon. That is, the particle's distance from the horizon approaches 0 and the Schwarzschild t coordinate approaches infinity. The particle traveling up away from the horizon must have crossed it an infinite coordinate time in the past. This is just an artifact of how Schwarzschild coordinates are defined. The free-falling particle will only take a finite proper time as measured by its own clock to pass between an outside observer and an event horizon. And if the particle's whirl line is drawn in the Kruskal-Skirov diagram, this will also only take a finite coordinate time in Kruskal-Skirov coordinates. The Schwarzschild coordinate system can only cover a single exterior region and a single interior region, such as regions 1 and 2 in the Kruskal-Skirov diagram. The Kruskal-Skirov coordinate system, on the other hand, can cover a maximally extended spacetime, which includes the region covered by Schwarzschild coordinates. Here, maximally extended refers to the idea that the spacetime should not have any edges. And each geodesic path can be extended arbitrarily far in either direction unless it runs into gravitational singularity. Technically, this means that a maximum extended spacetime is either geodesic or complete, meaning any geodesic can be set to arbitrarily large positive or negative values of the affine parameter, which in the case of the timeline geodesic could just be the proper time. Or if any geodesic are incomplete, it can only be because they end at a singularity. In order to satisfy this requirement, it was found that addition of a black hole interior region 2, which particles enter when they fall through the event horizon from the exterior region 1, there has to be a separate white hole interior region 4, which allows us to extend the trajectory of particles which an outside observer sees rising up away from the event horizon, along with a separate exterior region 3, which allows us to extend some possible particle trajectories into two interior regions. There are actually multiple possible ways to extend the exterior Schwarzschild solution into a maximally extended spacetime with the crystal spheres. Extension is unique in that it is a maximal analytic, simply connected vacuum solution, in which all maximally extended geodesics are either complete, or else the curvature scalar diverges along them in a finite affine time. Okay. That was a mouthful. Okay. Now basically the rest of this is equations. These light cone coordinates have the useful features for outgoing zone geodesics are given by U equals constant, while ingoing null geodesics are given by V equals constant. Furthermore, the future and past event horizons are given by the equation UV equals 0, and curvature singularity is given by the equation UV equals 1. The light cone coordinates are close to the Eddington-Finkelstein coordinates. Okay. So, there are some other interesting coordinate systems. I just found the Roger coordinates. The Roger coordinates are a particular set of coordinates for the Schwarzschild metric for the Einstein field equations. Changing from Schwarzschild to a metric coordinates removes the coordinate singularity at the Schwarzschild radius. Okay. Very good. Let's see. I'm looking at a GP coordinate system. Okay, so in this coordinate system, define the range of an object which plunges radially towards the black hole from rest to infinity. Which show coordinates speed tends to 0 as r approaches the event horizon. The range appears to explode as it gets near the event horizon and melted at the event horizon as measured by the bookkeeper. Indeed, an observer outside the event horizon will see the raindrop plunges slower and slower, its image infinitely redshifted, and never makes it through the event horizon. However, the bookkeeper does not physically measure the speed directly. He translates data relayed by the shell observer to its final values into peak speed. The result is only an accounting entry. The speed of the raindrop is inversely proportional to the square root of the radius, which equals the negative Newtonian speed velocity. This is very far away from the black hole, the speed is extremely small. As the raindrop plunges toward the black hole, the speed increases. At the event horizon, the speed has a value 1. There is no discontinuity or singularity at the event horizon. Inside the event horizon, r is less than 2m. The speed increases as the raindrop gets ever more closer to the singularity. Eventually, the speed becomes infinite at the singularity. As shown below, the speed is always less than the speed of light. The results may not be correctly predicted by the equation at and very near the singularity, since the true solution may be quite different when quantum mechanics and quantum gravity is incorporated. Despite the problem with the singularity, it's still possible to compute the travel time for the raindrop from the horizon to center of black hole mathematically. We're using integrals. Integrate the equation of motion result. dr equals 4/3 m. Using the result for the speed of the raindrop, we can find the proper time along the trajectory of the raindrop in terms of the time tr. Closely related set of coordinates is the Lemaitre coordinates, in which the radial coordinate is chosen to be constant along the path of the raindrop. Since r changes as the raindrops fall, the metric is time dependent, while the GP metric is time independent. The metric obtained if in the above we take the function fr to be negative, or what we choose above is also called the GP coordinate system. The only change to the metric is that cross term takes a stop. Metric is regular for outgoing raindrops. This particle which leave the black hole traveling outward with just escape velocity for their speeds at infinity of 0. The usual GP coordinates, such particles cannot be described for r is less than 2 of their zero value. dr over dtr at r equals 2m. This is an indication that a source-bound black hole has two horizons, a past horizon and a future horizon. The original form of the GP coordinates is regular across the future horizon where particles fall into and they fall into a black hole, while the alternative negative version is regular across the past horizon from which particles come out from the black hole if they do so. Scarce coordinates are regular across both horizons with the extent of making the metric strongly dependent on the time coordinate. At places very far away from the black hole, r yields infinity, dr over dtr equals plus minus 1, the speed of light is 1, the same as the special relativity. At the event horizon, r equals 2m, the speed of light shining outward away from the center of the black hole is dr over dtr equals 0. It cannot escape from the event horizon, instead it gets stuck at the event horizon. Since light moves faster than all others, matter can only move inward at the event horizon. Everything inside the event horizon is hidden from the outside world. Inside the event horizon, r is less than 2m. The read observer measures that the light moves toward the center with speed greater than 2. This is plausible. Even in special relativity, the proper speed of moving objects. No object should have speed greater than the speed of light as measured in the same reference frame. Thus, the principle of causality is preserved. Indeed, the speed of the raindrop is less than that of light. The time of travel for light shining inward from the event horizon to the center of the black hole can be obtained by integrating the equation for the velocity of light. The result is tr equals 4m. Natural logarithm 2 minus 2m is equivalent to 0.77 m. The light travel time for a stellar black hole with a typical size of 3 solar masses is about 11 microseconds. Ignoring effects of rotation for Sagittarius A, supermassive black hole residing at the center of the Milky Way with a mass of 3.7 trillion or 7 million solar masses, of the light travel time is about 14 seconds. The supermassive black hole at the center of Milky Way 87, a giant elliptical galaxy in the Virgo cluster, is the biggest known black hole. It has a mass of approximately 3 billion solar masses, so almost 1,000 times bigger than it. It would take about 3 hours for light to travel to the central singularity of such a supermassive black hole. And for lights or and for raindrops, 5 hours. How does the universe look like? It's seen by a radar observer plunging into a black hole. The view can be described as the following illustration of stars. Each incoming light ray can be backtraced to a corresponding ray at infinity. The impact parameter for the incoming light ray is the distance between the corresponding ray at infinity and a ray parallel to it that plunges directly into the black hole. Because of spherical symmetry, the trajectory of light always lies in the plane passing to the center of sphere. It's possible to simplify the metric by assuming theta equals pi over 2. Let's see here. The impact parameter I can be computed showing the range observers R coordinate R0 and mean angle theta R0. Theta R theta. Okay. Pi R theta. Then the actual angle pi of the distant star is determined by the numerically integrating d from RO to infinity. A chart of the sample result is shown at the right. And R divided by n equals 500, the black hole is still very far away. It's substantially diametric angle of around 1 degree in the sky. The stars are not disturbed much by the presence of the black hole, except for the stars directly behind it. Due to gravitational lensing, these obstructed stars are non-deflected 5 degrees away from the back. In between these stars and the black hole is a circular band of secondary images of the stars. Duplicate images are instrumental in the identification of the black hole. And R divided by n equals 30, the black hole will become much bigger, spanning a diametrical angle of 15 degrees in the sky. The band of secondary images is also going to 10 degrees. It's not possible to find faint tertiary images in the bar, which are used for the light rays that have looped around the black hole once already. The primary images are distributed more tightly in the rest of the sky. Common distribution is similar to that previously. At R divided by n equals 2, the horizon, the black hole now occupies a substantial portion of the sky. The green observer would see an area up to 42 degrees from the radially inward direction that is pitch dark. The band of secondary and tertiary images, rather than increasing, has decreased in size to 5 degrees. The operation effect is now quite dominant. Speed of plunging has reached the light speed. The distribution pattern of primary images is changing drastically. Their primary images are shifting towards the boundary of the band. The edge of the band is now crowded with stars. Doppler effect. The primary image of the stars, which were originally located behind the rain observer, have their images appreciably red shifted, while those that were in front are blue shifted and appear very bright. At R divided by m equals 0.001, the curve of distant star angle, where the view angle appears to form a right angle at the 90-degree view angle. Almost all of the star images are congregated in a narrow ring, 90 degrees from the radially inward direction. Between the ring and the radially inward direction is the enormous black hole. On the opposite side, only a few stars shine faintly. As the rain observer approaches singularity, R equals 0, and cosine GR towards square root of R over 2m. Most of the stars in their images caused by multiple orbits of the light around the black hole are squeezed to a narrow band at the 90-degree angle. The observer sees a magnificent bright ring of stars bisecting the dark sky. Both Knive and Goldstern used this solution to argue that Einstein's theory was incomplete in that it gave multiple solutions for the gravitational field of the body. And moreover, with different physics, they argued the length of rocks would sometimes be longer and sometimes shorter in the radial than the tangential directions. The trick of the The proposal was that he no longer stuck to a full quadratic static form, but instead allowed a cross-time-space product, making the metric form no longer static but stationary, no longer direction symmetric, but preferentially oriented. In a second longer paper, Fleming explained how he derived a solution that directly solved Einstein's equation for generic, spherically symmetric form of the metric. The result equation 4 of this paper depended on two arbitrary functions with the r-coordinate yielding a double infinity of solutions. We now know that these simply represent a variety of choices of both time and radial coordinates. But we wrote to Einstein to introduce a solution and wanted Einstein to Paris complete. In Einstein's reply letter, he apologized for not being in position to visit students for why he was not pleased with Henry's arguments, emphasizing that the coordinates themselves have no meaning. Finally, Einstein came to Paris in early April. On 5th of April, 1922, in a debate at the Collège de France, with Camille Becquerel, Berlin, Cartan, Dr. Hadamard, Benjamin Nordman on the infinite potentials, Einstein, baffled by the non-quadratic Frost-term and line element, rejected Hadamard's solution. Okay. Oh. Alright, so we basically just have a couple more examples here. Actually, one more. One about wormholes. So, let me quickly get to that. Interuniversal travel. A possible resolution of the paradoxes resulting from wormhole-enabled time travel rests on the many worlds of education of quantum mechanics. In 1991, David Boyd showed that quantum theories were consistent in the sense that the so-called density matrix can remain free of discontinuities in space-time with closed timeline curves. However, later it was shown that such a model of closed timeline curves can have internal inconsistencies and will lead to strange phenomenon like distinguishing non-orthogonal quantum states and distinguishing proper and improper mixture. Closing destructive positive feedback loop of virtual particles circulating through a wormhole time machine. A result indicated by semi-classical calculations is averted. Particle returning from the future does not return to its universe of origination, but to a parallel universe. This suggests that a wormhole time machine with an exceedingly short time jump is a theoretical bridge between contemporaneous parallel universes. Right there. Because a wormhole time machine introduces a type of nonlinearity to quantum theory, this sort of communication between parallel universes is consistent with Joseph Polchinski's proposal of an Everett flow. It's Steven Weinberg's formulation of nonlinear quantum mechanics. Possibility of communication between parallel universes has involved inter-universal travel. Wormholes can also be depicted as pendulum diagrams or Schwarzschild black hole. The pendulum diagram, an object travels faster than light will cross the black hole and will emerge from another end into a different space, time, or universe. This will be an intra-universal wormhole. So, Shannon Hall states that an alternate universe allows the physics to be different more or less from ours. Gravity might even work in the opposite direction. So is it possible that somebody in one of these alternate universes could develop a method of travel between them? Okay. So I like this David Deutsch solution. Traveling through the second dimension of time to get between the different time persons. Localized closed timeline curves can perfectly distinguish quantum states. We show that qubits traveling along closed timeline curves are a resource that a party can exploit to distinguish perfectly any set of quantum states. As a result, an adversary with access to closed timeline curves can break any prepare and measure quantum qubits to reach the protocol. Our result also applies that a party with access to closed timeline curves can violate the Hollywood vow. Purification of mixed states, closed timeline curves is not possible. During quantum theory, mixed state can be purified in large Hilbert space by bringing ancillary system. The purified state does not depend on the state of an extraneous system with which the mixed state is going to interact and on the physical interaction. Here we prove that it is not possible to purify a mixed state that traverses the closed timeline curve CTC and allow it to interact in a consistent way with the causality respecting CR quantum system in the same manner. Thus, in general, for arbitrary interactions between CR and CTC systems, there is a universal church of the larger Hilbert space or mixed state CTC. It shows that in quantum theory, CTC works with proper and improper mixtures. Weinberg's nonlinear quantum mechanics and the Einstein-Podolsky-Rosen paradox. I show that Weinberg's nonlinear quantum mechanics leads to either to communicate via EPR correlations or to communicate both communications between branches of the wave function. Okay, so we have some metrics. Series of wormhole metrics describing the space-time geometry of a wormhole and serve as its theoretical models for time travel. An example of a traversable wormhole metric is the following. ds squared equals negative c squared, dt squared plus dt squared plus bracket k squared plus l squared, close bracket, another bracket, d theta squared plus sine squared theta d p squared, close bracket. First presented by Ellis. And a special case of the Ellis trademark. This four-dimensional space is described mathematically by two congruent parts or sheets corresponding to mu equals 0 and mu is less than 0, which are joined by a hyperplane r equals 2m or u equals 0, in which g vanishes. We call a connection between the two sheets a bridge. Okay. The Ellis wormhole is a special case of the Ellis straight hole in which the ether is not pouring and there is no gravity. what remains is a pure traversable wormhole comprising a pair of identical twin, non-flat, three-dimensional regions torn out of two spheres. The throat of the wormhole. As seen in the image shown, the two-dimensional equatorial cross-sections of the wormhole are cardanoidal collars that are asymptotically flat, far from the throat. There being no gravity and force, a inertial observer test particle can sit forever at rest or any point in space, but instead of motion by some disturbance, will follow a geodesic of an equatorial cross-section at constant speed, as would also a photon. This phenomenon shows that in space-time, the curvature of space has nothing to do with gravity. The curvature of time, one could say. As a special case of the Ellis drain hole itself, a traversable wormhole, the Ellis drain hole dates back to the drain hole's discovery in 1969. The H.G. Ellis, independently at about the same time as K.A. Brodikoff. Ellis and Brodikoff derived the original traversable wormhole, the switch of the Einstein vacuum field equations augmented by inclusion of a scalar field. Theta minimally, or phi minimally coupled to geometry of space-time with coupled polarity opposite to the orthodox polarity negative instead of positive. Some years later, Morris and Thorne manufactured a duplicate of the Ellis wormhole to use as a tool for teaching general relativity, asserting that the existence of such a wormhole required the presence of negative energy, a viewpoint Ellis had considered and explicitly refused to accept on the grounds that arguments for it were unpersuasive. Okay, in Minkowski space-time, every time like and every light-like null geodesic with a straight whirlwind that projects onto a flat line geodesic of the equatorial cross-section of a time slice of constant t, as for example the one of t equals 0, and v was pi divided by 2, the metric of which is line of equation 2 around space and polar coordinates. Well, and if the variable parameters arrive after the parameter n on the Ellis drain hole solution is set to 0 and stop the ether flow and thereby eliminate gravity. If one goes further and set the n to 0, the metric becomes that of Minkowski space-time. The flat space-time of special theory of relativity. Every test particle or photon is seen to follow such an equatorial geodesic at a fixed coordinate speed, which could be 0, there being no gravitational field built into Minkowski space-time. These properties of Minkowski space-time all have their counterparts in the Ellis wormhole. Modified, however, by the fact that the metric and therefore geodesic of the equatorial cross-section of the wormhole are not straight lines. Rather, are the straightest possible path to the cross-section of the of interest to see what these equatorial geodesics look like. The equatorial cross-section of the wormhole is defined by t equals 0 and v equals pi divided by 2, representative of all such cross-sections. H squared is greater than n squared, which implies that p squared is greater than equal to h squared minus n squared is greater than 0, thus that the geodesics defined to one side of the wormhole or the other is a floating point. Rho equals square root of h squared minus n squared, or rho equals the negative square root of h squared minus n squared. H squared equals n squared, which entails that rho squared is greater than 0, so that the geodesic does not contain the cross field at rho equals 0. That spirals onto it from one side to the other. H squared is less than n squared, which allows the geodesic to traverse the wormhole from either side to the other. The figure is further examples of the three types. If S is allowed to vary from negative infinity to infinity, the number of orbital revolutions possible for each type. Let's including with odd numbers. For the first and third types, the number rises to infinity as h squared goes to n squared. For the smaller type of latitudes, the number is already infinite. That these geodesics can bend around the wormhole to clear the curvature space alone without the aid of gravity to cause test particles and photons to follow paths of deviate significantly from straight lines and can create lensing effects. The shows the dynamic version of the Alice wormhole that is a solution with same field equations that the static wormhole is the solution of. Metric is c squared dr squared equals c squared dt squared minus d sigma 2. Or d sigma 2 equals d rho 2 plus the absolute value of 1 plus a squared rho squared plus a squared c squared t squared d sigma 2. A being a positive constant, there is a point singularity of t equals rho equals 0, but everywhere else the metric is regular, curvatures are finite. Geodesics that do not encounter the point singularity are complete. So if they do techniques that is beyond it, proceeding along any geodesics that encounter the singularity from the opposite time direction. They have compatible tangents. Similarly, geodesics on the graph of z equals xy to the third that encounters the singularity at the origin. Metric describes a hypercatenoid similar to the equatorial catenoid of the static wormhole with the radius n of the float, where rho equals 0 now replaced by a c absolute value t, and in general each circle latitude of geodesic radius rho having circumferential radius r t. V equals u, the metric of v equals pi divided by 2 equals the cross section, which describes a hypercone with its vertex at a singular point if latitude circles of geodesic radius rho have circumference. ds squared equals dp squared plus 1 plus h squared p squared d chi squared. 2 pi r 0 rho. 2 pi square root of 1 plus a squared rho. Unlike the catenoid, neither the hypercatenoid nor the hypercone is really representable as a surface in the so the portions currently can be embedded in this one. Schematically, it's the equator from negative to infinity, equal plus straight from hypercatenoids with the radius, to hypercones, hypercatenoids with 0 radius and t equals 0. When expand back to hypercatenoids with infinite radius. Examination of the curvature tensor reveals that the full dynamic Alice wormhole space-time manifold is asymptotically flat in all directions, time-like, light-like, and space-like. The pitch better than Alice wormhole, spatial level, not gravitational level, there is no gravity in the Alice wormhole. Micro-lensing by the Alice wormhole, wave effect of lensing by the Alice wormhole, image-centered displacement due to micro-lensing by the Alice wormhole, exact lens equations for the Alice wormhole, and lensing by wormholes. The Alice wormhole is the earliest complete mathematical model of a traversable wormhole. Its status is the symmetric solution of the Einstein vacuum field equations, augmented by inclusion of a scalar field by minimally coupled to the geometry of spacetime with coupling polarity opposite to the orthodox polarity, negative instead of positive. So this is by Alice Bronikov. Bronikov pointed out that a two-dimensional analog quality solution is a hyperboloid of one sheet, and that only use of the anti-orthodox coupling polarity will allow a solution with such a topology. The motivation is to find non-singular rotation for the Schwarzschild model of an elementary gravitational particle shows that only the anti-orthodox polarity would do. We found all the solutions for either polarity as a logical. The solution manifold for the anti-orthodox polarity is considered that and found it to be composed of two asymptotically flat three-dimensional regions joined at a two-sphere. Okay. singularity free, devoid of one-way electrolysis, geodetically complete, gravitationally attractive on one side of the kernel, and more strongly repulsive on the other. Equipped with a timeline vector, field he interpreted as a velocity field of an ether, flowing from rest at infinity on the attractive side, down into the Drano and out into infinity on the repulsive side, creating or responding to gravity by pulling all the way. And to go through the Drano in either direction by photons. Table like the time is coming to the name Ellis geometry with special case of a Drano in which ether is not flowing and flows by gravity. As also a letter edited by Clark. The special case is often referred to as the Ellis wormhole. When the Fulgor wormhole is considered in full of the approach of the reversible wormhole, Neil Brodikoff is attached to it alongside that of Ellis. Imagine two Euclidean planes, one above the other. Pick two circles of the same radius, one above the other, and move their exteriors. Now glue the exteriors together at the circles, bending the exterior smoothly so that there is no sharp edge at the grid. If one is carried over to the capital C, picture it right, or something similar. Next, picture the whole connected upward over C. Able to fluid flow with no swirling into the hole from above and out the lower side. You see all the way indenting the lower regions into a more conical shape than it's seen in C. So if you imagine stepping smoothly up from flat 3D, replacing the equation of three spheres, and the circles with spheres, and think of the fluid flowing from all directions, the hole from above, and out below directions unchanged, you will have a pretty good idea of what a Drano is. This technical description of a Drano as a space-time manifold is provided by the space-time metric published in 1973. The Drano metric solution presented by Ellis has the proper time forms. Exposure to C-rate explicit. Solution depends on two parameters and then satisfying the inequality 0 plus equal to n is less than n, but otherwise unconstrained. In terms of these, the functions f and r are given by. Facilitate comparison. The Schwarzschild solution rho of this solution has been replaced by rho minus m. Asymptotically flow tending towards infinity. Upon comparison, Drano metric to the Schwarzschild metric. And then the outline of the Drano of the Schwarzschild metric mass parameter. On the other side, rho tends towards negative infinity. The graph of R below exhibits these asymptotic. The rho reflects the corresponding to rho equals 2m, where the Schwarzschild metric has its notorious one-way event horizon. Considering the exterior where rho is greater than 2m, and the black hole interior where rho is less than 2m, R attains at rho equals 2m, a positive minimum value at which the upper region where P is greater than 2m, opens out into a more spacious lower region where P is less than 2m. Greater than 2m to less than 2m. As we read for the graph of where a test particle follows one of the geodesic starts from west at rho equals high, rho equals infinity, falling downward towards the Drano, gaining speed all the way, passes through the Drano, and out into the low region, still gaining speed in the downward direction, arrives at rho in negative infinity. The vector field in question is taken to be the velocity field of a more or less substantial ether, pervading all space-time. This ether is in general more than a mere inert medium for the propagation of electromagnetic waves. It is a restless flowing continuum whose internal relative motions manifest themselves to us in gravity. Mass particles appear as sources or sinks of this flowing ether. For time like geodesics in general, the radial equation of motion from this, it is the stretching of the ether flow as measured by the term f minus f squared divided by 2 prime rho that produces the downward flow of gravity. Every test particle's orbit gives of low as rho equals 3m will fall through the drain. There are test particles with enough angular speed, v omega divided by dr, absolute value of this, 2,000 kilometers to hold that the orbits, circular ones in particular, are confined to the part of the upper region where rho is greater than 3si. The downward pull produces in the upper region acceleration towards the drain hole as attractive gravity, but the lower region acceleration away from the drain hole, thus repulsive gravity. The downward pull reaches its maximum where r rho as a minimum, namely at the throat of the drain hole where p or rho equals 2m, and if m equals 0, test particles sit with rest anywhere in space. This is a special case for non-gravitating drain hole known as the Alice rule. d rho divided by d tau equals d omega divided by d tau equals 0. It's clear that the radial equations of motion the test particles start from any point in the upper region with the radial velocity d rho divided by d tau equals 0, but without sufficient angular velocity, d omega divided by dr fall down through the drain hole and into the lower region. Not so clear, but nonetheless true that the test particle starting from a point in the lower region can with sufficient upward velocity pass through the drain hole into the upper region. This drain hole is traversable by test particles in both directions. Same holds true for photons. The catalog of geodesics of the drain hole can be found in the Alice paper. The lightweights will best hold their own, while otherwise you shift downstream to wherever the people is going. This situation is been jet that people would like to use should avoid ethereal rockets. Latter situation is seen with parametric, which is -1, the source total event horizon, when r rho equals rho is 2m, and less than -1, then the event horizon will be less than 2m. By contrast, the drain hole m squared rho is less than 1 minus e dv negative 2m pi divided by a power is less than 1, and f rho equals negative with the absolute value of m squared rho using half power m squared greater than -1 for every value of p or every value of rho. So there is the horizon on one side of which that is struggling against the ether flow cannot gain the ground. This R is also defined as a whole real line, and R is started away from theta by R rho to m. So it's rho started away from theta by rho to m. M squared is started away from 1 by square root of 1 minus e to the negative 2m pi divided by 8. The trigonometric promises neither a coordinate system where 1 minus f squared times rho tends towards 0, nor a geometric singularity where r times rho tends towards 0. Not even asymptotic. For the same reason, every geodesic with an unbound orbit, and with some additional argument that every geodesic with a bound orbit with alpha polarization is primitive from negative infinity to infinity. The manifold is therefore geodesic. As the earlier stretching of the ether flow produces in the upper region a downward acceleration. If m divided by r squared below the common test particles are wrong with r rho equivalent to rho as rho towards infinity, and we find m as the attractive gravitational mass of the non-local localized drain hole particle at the lower region. The downward acceleration is formally the same, but because rho r times rho is asymptotic to negative rho e m pi divided by a rather than to negative rho as rho towards negative infinity. One can infer the reflexive gravitational mass of the drain hole particle is negative m. We learned the mass of the drain hole requires finding the isometry of the drain hole manifold that extends to the lower regions. Such an isometry can be described as follows, where m equals m divided by n. Note the drain hole manifold is parameters are m and n, and m parallel. The drain hole manifold is parameters are m and n parallel. equals negative ME, M pi divided by A, and parallel equals ME, M pi divided by A. The isometry defines a point M, and N has the coordinates T, rho, beta, I, with the point of M, and N with the parallel have the coordinates T parallel, rho parallel, V parallel, pi parallel equals GT, the negative M, pi divided by A, negative rho, E, M pi divided by A, V, and chi. When the first from this that M divided by N, and M parallels are in fact the same manifold, and that the two regions, the lower region where rho is heading towards negative infinity, now the size of the upper region where parallel is going towards infinity, as M and its gravitational mass of gravitational repellent particles more strongly than the true upper region attracted. With the ratio M parallel to absolute value divided by M, absolute value equals negative M parallel divided by M equals E to the M pi divided by A power. Asymptotic flatness. The granular is asymptotically flat as rho approaches infinity as seen from the asymptotic behavior R rho approximately rho and F rho approximately 2M divided by rho approximately 0. That is asymptotically flat as rho towards negative infinity as seen from the corresponding behavior as parallel rho towards infinity and from the isometry between N and M and parallel. Described above. Unlike the parameter M, the interpreter of the attractive gravitational mass of the granular parameter N has no obvious physical interpretation. This actually fixes both the radius R times 2M of the granular, which increases from N when M equals 0 to NE as M towards N, and the energy of the scalar field chi, which decreases from N pi divided by 2 M equals 0 to N squared N divided by 2 as M tends towards N. Reason earlier, I suggests that N specifies in some way the inertial mass of the particles modeled by a granular. It's further that the Higgsbian way of expressing this idea is to say that the granular requires inertial mass from the scalar field. Yeah. By disallowing Einstein's unjustified 1916 assumption that the inertial mass is the source of gravity, I was aware of the new improved field equations, a solution of which is a cosmological model that fits well the supernova observations in 1998 revealed the acceleration of the expansion of the universe. In these equations, there are two scalar fields minimally coupled to space-time geometry with opposite polarities. The cosmological constant, lambda, is replaced by the net repulsive density of gravitating matter, owing to the presence of primordial granules tunnels. Very interesting. Continuous creation of new tunnels. Each with excess of repulsion over attraction. Those granule tunnels associated with particles of visible matter provide their gravity. Those not tied to visible matter are seen by the unseen dark matter. That's where the wormholes might be. Dark energy is the net repulsive density of all the granule tunnels. Wow, this works. The cosmological model has a big bounce instead of a big bang. The stationary acceleration out of the bounds and a smooth transition to an era of decelerative coasting, followed ultimately by a return to decelerative exponential expansion. Eventually, it's going to collapse back in again and start the new universe. But the time version all combined with this full paper emerging in the second temporal dimension. Very interesting. Further applications. The wormhole serves as a starting point for building the traversable wormhole in the 2014 movie Scattering by an Ellis wormhole. Spatial lensing, not gravitational lensing, as there is no gravity in the Ellis wormhole. Partial lensing by the outward wave effect is lensing by the outward. It is internal displacement due to microlensing by the outward. Right lens equations for the outward. Lensing by wormhole. Cosmology without Einstein's assumption that inertial mass produces gravity. Giving up Einstein's assumption implicitly in 1963 equations that inertial mass, even its appearance as energy, is equivalent to active gravitational mass, and therefore its experience of gravity allows revising the field equations to a form in which a positive cosmological constant is seen to misrepresent a uniform negative net mass density of gravitationally attractive and gravitationally repulsive matter. Field equations with both positive and negative active gravitational mass densities of both primordial and continuously created matter incorporated along with two scalar fields to erect constraints in the space-time geometry field, cosmological solutions that consider inflation, deceleration, cold spin, acceleration, and a big bounce instead of a big bang, and provide good focus to a Hubble diagram of type 1a supernova data. The repulsive matter is identified as the backsides of the great holes introduced by the author in 1973 as solutions of those same field equations. Great holes, for typical examples of traversable wormholes, are the topological tunnels in space, which tunnels in space, which gravitationally attract on their front entrance sides and repel more strongly on their backs. The front side serves as the gravitating pull of invisible baryonic particles of primordial matter and as the continuously created invisible particles of the dark matter. Meaning, hold together the large-scale structures seen in the universe. The backside serves as the misnamed dark energy, leveling the current acceleration and the expansion of the universe. The nature of cosmic stories, as well as experiments and notes, is attributed expulsion of great hole entrances from regions populated by great hole exits. Accumulation of the entrances or boundaries separating exposed regions. Further Reinberg's non-linear quantum mechanics leads either to communication via EPR correlations or to communication between branches of the wave function. Okay, so this is almost it. Yay! Wow. Okay. That was a lot. Okay, so ER equals EPR. Now, I am extending ER equals EPR into quantum mind theories because we can see where intuition, ESP, precognition, etc. come from, with the wormhole connection between the environment and the mind, leads to entangled states, which leads to direct communication on a subconscious level, and instinctive reactions like fear, joy, etc. Or something is about to happen since all that information is in the environment. ER equals EPR is a conjecture in physics dealing with two entangled particles. Einstein, Podolsky, Rosen, or EPR pair are connected by a wormhole Einstein-Rosen bridge, and may be a basis for unifying Galois-Archivian quantum mechanics into a theory of everything. Overview: the conjecture was proposed by Leonard Susskind and Juan Walsena in 2013. They proposed a non-traversable wormhole Einstein-Rosen bridge is opposed to a pair of maximally entangled UPR refers to quantum entanglement, UPR paradox. The symbol is derived from the first letters of the surnames of authors who wrote the first paper on wormholes, Albert Einstein and Nathan Rosen, and the first paper on entanglement. Einstein, Boris, Podolsky, and Rosen. The two papers were published in 1935, but the authors did not claim any connection between the concepts. Preliminary evidence, though indirect, for ER equals EPR is that a certain entangled pair has been realized as an ER bridge using ADS-CFT correspondence. That would be the holographic theory. All connected. This is a conjectured resolution of the AMPS firewall paradox. Whether or not there is a firewall depends upon what is thrown into the outer distant black hole. However, as the firewall lies inside the generalized and no external signaling would be possible. This conjecture is an extrapolation of the observation by Mark Ramsdorf maximally extended EDS force-field black hole which is a non-traversable wormhole is due to a pair of maximally entangled thermal-conformal field theories via the ADS-CFT correspondence. The backup their conjecture by showing that the pair production of a charged black holes in the background magnetic field leads to entangled black holes, but also a Wick rotation to a wormhole. Stein and Maltsina envisioned the gathering of all the Hawking particles and smushing them together until they collapsed into a black hole. That black hole would be entangled and thus connected by a wormhole with the original black hole. That trick transformed a confusing mess of Hawking particles paradoxically entangled with both a black hole and each other into two black holes connected by a wormhole. It's like a parent dark universe. Entanglement overload is averted and the firewall problem goes away. This conjecture sits uncomfortably with the linearity of quantum mechanics. An entangled state is a linear superposition of separate states. Presumably, separate states are not connected by any wormholes, but yet a superposition of such states is connected by a wormhole. The authors push this conjecture even further by claiming any entangled particles, even particles not ordinarily considered to be black holes, and pairs of particles with different masses or spin, or with charges which are opposite, are connected by Planck scale wormholes. The conjecture leads to a greater conjecture that the geometry of space, time, and gravity, and consciousness is determined by entanglement. Oh, very interesting. Okay. In nature, the quantum source of space-time. Many physicists believe that entanglement is the essence of quantum weirdness, and some now suspect that ultimately the essence of space-time geometry. Okay, so no one has a clear idea of what this underlying reality is, but physicists are increasingly convinced that it must exist. Maldacena, Sussman, and others have been testing the ER equals EPR hypothesis to see if it is mathematically consistent with everything else that is known about entanglement and wormholes. And so far, the answer is yes. There's a section on tensor networks. For example, if a team developed by condensed matter physicists to track the quantum states of each other with subatomic particles. Brian Campbell was using them this way in 2007, calculating how groups of electrons interact with solid material. He found that the most useful network for this purpose started by arranging adjacent pairs of electrons, which are most likely to interact with each other by making larger and larger groups of a pattern that resembles a hierarchy of a family tree. But then there are portions on the field theory, so we learn about multiple bulk boundary correspondence and notice an intriguing pattern. The mapping between the bulk and the boundary showed exactly the same tree-like network. You can think of space as being built from entanglement. So we wondered whether this resemblance might be more than this coincidence. In 2012, we published calculations showing that it was. It independently reached much the same conclusions as Van Ransdonk, thereby adding strong support to the geometry entanglement idea. You can think of space as being built from entanglement in this very precise way, using the tensors. Spindler is now at Stanford, and I've seen tensor networks which are frequently used too to explore the geometry entanglement correspondence. Another prime example of quantum relations theory of quantum error correcting code, which physicists invented to aid in the construction of quantum computers. These machines encode information not in bits but in qubits, quantum states such as up, down, spin, and electrons can take on values of 1 and 0 simultaneously. In principle, when the qubits interact and become entangled in the right way, such a device can perform calculations that an ordinary computer could not finish in the lifetime of the universe. So in practice, the process is incredibly fragile. Science distributors from the outside world will disrupt the qubit's delicate entanglement and destroy any possibility of quantum computation. Need for quantum error correcting codes. One hallmark of these codes is they always found local information stored into a qubit that to be spread out over a wide region of space. Otherwise, damage in a single spot could destroy any local recovery. And that locality in turn captured the fascination of many quantum information theorists feel when they first encounter Maldacena false boundary correspondence. It shows a very similar kind of non-locality. An holographic principle again. Information that corresponds to a small region of the bulk is stored over a vast region of the boundary. Anyone could look at ADS-CFT and say that it's a sort of vaguely analogous to a quantum error correcting code. Argue for something stronger, that the Maldacena duality is itself a quantum error correcting code. We have demonstrated that this is mathematically correct in a simple model, and are now trying to show that the assertion holds more generally. People have been saying for years that entanglement is somehow important for the emergence of the bulk, but for the first time I think we are really getting a glimpse of how and why. This prospect beyond entanglement seems to be enticing for the Simons Foundation, a philanthropic organization in New York City that announced in August that it would provide $2 million per year for at least 4 years to help researchers move forward on the gravity-quantum information connection. Information theory provides a powerful way to structure our thinking about fundamental physics. The aspect of Simon sponsorship will support 16 main researchers at 14 institutions worldwide, along with students, postdocs, and a series of workshops in schools. Ultimately, one major goal is to build up a comprehensive dictionary for translating geometric concepts into quantum language and vice versa. This will hopefully help physicists to find their way to the complete field of quantum gravity. So researchers face several challenges. One is that the bulk boundary correspondence does not apply in our universe, which is neither static nor bounded. It is expanded and apparently infinite. Most researchers in the field do think that the calculation using Maldacena's correspondence are telling them something true about the real universe. but there's little agreement as yet on exactly how to translate results from one origin to the other. Another challenge is standard definition of entanglement refers to particles only at a given moment. A complete theory of quantum gravity will have to add ties to that picture. Entanglement is a big piece of the story, but it's not the whole story. That's what's done. He said he thinks physicists have to embrace other concepts of quantum information theory, computational complexity, the number of logical steps or operations needed to construct the quantum state of a system. A system with low complexity is analogous to a quantum computer. With almost all the qubits on zero, it is easy to define and build. One with high complexity is analogous to a set of qubits encoding a number that will take eons to compute. Einstein's role to computational complexity began about a decade ago when he noted that the solution to Einstein's equations of general relativity allowed a wormhole into ADS space to get longer and longer as time went on. What did that correspond to on the boundary? He wondered what was changing there. Einstein knew that it could be entanglement, because the correlations that produce entanglement between different particles in the boundary reached their maximum in less than a second. In an article last year, however, he and Douglas Stanford, now at the University of Advanced Study, showed that as time progressed, the quantum proof of the boundary was varied exactly the way expected from computational complexity. It appears more and more that the growth of each year of a black hole exactly the growth of computational complexity. Quantum entanglement mixed together pieces of space. He says that computational complexity may drive the growth of space, and that brings in the elusive element of time. One potential consequence, which he is just reading to explore, could be only between the growth of computational complexity and the expansion of the universe. Another is that because the inside of black holes are the very regions of quantum gravity quantum computational complexity may have a role in a complete theory of quantum gravity. Despite being challenging, there is a sense among the practitioners of this field that they have begun to build something real and very important. I didn't know what space was made of before system, but it wasn't clear that question even had meaning, but now it is becoming increasingly apparent that the question does not make sense, and the answer is something that we understand as it's made of entanglement. I love complexity. Mandelbrot said fractal pattern widely recognized as the symbol for complexity at its most beautiful. Okay, well here, the holographic principle is proven. In one paper, Heidi Kataji computes the internal energy of a black hole, the position of the vectorized, and the boundary between the black hole and the rest of the universe, and entropy and other properties based on the predictions of string theory, as well as the effects of so-called virtual particles that continuously pop into and out of existence. And the other, he and his collaborators calculate the internal energy of the corresponding lower dimensional cosmos with no gravity. The two computer calculations match. Okay, so abstract the space-time built out of quantum bits, where the shape of space depend on how the bits are entangled. The ER equals EPR conjecture relates the entanglement entropy of a collection of black holes to the cross-sectional area of Einstein-Rosen bridges of wormholes connecting them. We show that the geographical or geometrical entropy of classical ER bridges satisfy the sub-additivity triangle, strong sub-additivity, and Cagney-Winter inequality. These are non-trivial properties of entanglement entropy, so this is evidence for ER equals EPR. We further show that the entanglement entropy associated with classical ER bridges has non-positive tripartite information. This is not a property of entanglement entropy in general. For example, the entangled 4-qubit pure state has positive tripartite information. This state cannot be described by a classical ER bridge. Large black holes with massive amounts of entanglement between them can fail to have a classical ER bridge if they are built out of GHZ states. States with non-positive tripartite information are called monogamous. We conclude that classical ER bridges require monogamous EPR correlations. Oh, this is Van Ramsdorf's essay. We argue that the emergence of classically connected spacetime is intimately related to the quantum entanglement of degrees of freedom in a non-perturbative description of quantum gravity. Disentangling the degrees of freedom associated with two regions of spacetime results in these regions pulling apart and pushing off from each other in a way that can be quantified by standard measurements of you have physics and anti-de Sitter black holes and black hole solution of general relativity, or its spectrum, which represents an isolating massive object, but with a negative cosmological constant. Such a solution asymptotically approaches anti-de Sitter space at spatial infinity, and the generalization of the curved active solution which asymptotically approaches Minkowski spacetime at spatial infinity. 3 plus 1 dimensions, where G is the time coordinate, R is the radial coordinate, omega is the polar coordinate, C is the constant, and K is the ABS coordinate. In general, in D plus 1 dimensions, according to the ABS CFD correspondence, if that was quantized, an ABS black hole would be dual to thermal state on the conformal boundary in the context of, say, ABS PCE. This would correspond to the decomponent of the core boron plasma. Okay. So there's also an anti-de Sitter CMT correspondence. The CMT stands for condensed matter theory. the decades, experimental condensed matter physicists have discovered a number of exotic states of matter, including superconductors and superfluids. These states are described using the formalism of quantum field theory, but some phenomena are difficult to explain using standard field theory techniques. Some condensed matter theorists hope that the ADS-CFT correspondence will make it possible to describe these systems in the language of string theory and learn more about their behavior. So far, some success has been achieved using string theory methods to describe the transition of a superfluid to an insulator. A superfluid is a system of electrically neutral atoms that flows without any friction. Such systems are often produced in the lab using liquid helium, but recently experimentalists have developed new ways of producing artificial superfluids that form trillions of cold atoms into a piece of crisscrossing lasers. These atoms initially behave as a superfluid, but if experimentalists increase the intensity of the lasers, they become less mobile and then suddenly transition to an insulating plate. During the transition, the atoms behave in an unusual way. For example, the atoms slow to a halt at a rate that depends on the temperature of Planck's constant, fundamental parameter of quantum mechanics, which does not enter into the description of the other phases. This behavior is recently been understood by considering a dual description, where properties of the fluid are described in terms of a higher dimensional black hole. Very interesting. Wormholes connecting two black holes in different parts of space-time can exist. Only particles in the black hole surface are quantum entangled. If the entanglement of the wormhole stops to suggesting that entanglement is a thread that binds space-time together. Black hole is an extreme stretching of smooth space-time which should have no substructure and thus no entropy. For such kind, this contradiction points to a hole in Einstein's theory. We know that general relativity is incomplete, he said, with an ability to account for the entropy of black holes is probably the most obvious incompleteness of the theory. Here's where the ADS-CFT conjecture comes in. String theory equations describe gravity in some volume of space-time are just the same as a set of quantum equations describing the surface of that volume. If you could solve the surface equations, you could get a viable theory describing gravity inside. ADS-CFT and holographic principle. It showed how something that looked like two separate black holes from the outside might be connected on the inside. This interior connection formed a shortcut. A wormhole, Einstein-Rosen. The really odd thing though is that Malmsteen's duality showed that such a wormhole would only form the outside of the black holes, or quantum entanglement. Entanglement is not an on-off thing, it can exist in varying degrees. So what would happen if you were to slowly reduce the amount of entanglement between the black hole surfaces to nothing? The answer is rather like pulling the two ends of a piece of chewing gum. Two sides get further apart, and what's connecting them will split into some gum and eventually collapse. The wormhole becomes thinner until it breaks, and then you have two unconnected bits of space-time. They rush the process, increase the entanglement, and the wormhole starts to form again. It's always there, you just pick up the attack. It took a few more years for the penny to finally drop in Malmsteen's mind, and for him to make the suggestion laid out in that excited email. What if, asked Malmsteen, a wormhole and entanglement are in fact two sides of the same coin? The same physics at two different scales. Space-time in the form of wormholes can be created and destroyed simply by tweaking the amount of entanglement. Space-time is really a geometrical manifestation of entanglement. Very close connection between quantum mechanics and the continuity of space-time, which seems to be something very solid, could come from the ghostly properties of entanglement. Quantum entanglement is a form of information, and so space-time is a manifestation of quantum information. Okay, so with superposition, it's interesting because it says that when quantum systems become entangled and therefore enter a superposition, suddenly gain a wormhole, which the superposition principle doesn't obviously allow. Oh, so Einstein, the older Einstein, was a polyglot. After all, Einstein spent much of his later years arguing for a hidden reality that wasn't subject to the vagaries of quantum mechanics. But the young Einstein apparently had a much more flexible mind. Susskind guesses that the young Einstein would have the crazy ideas about them. Although these two particles might be entangled, their entanglement doesn't necessarily conflict with the entanglement of the particle inside the horizon and its immediate partner outside, because they aren't all happening at the same time. Uncomfortable apparitions such as embraces firewalls at the event horizon disappear. Particles just outside the horizon, but the particles far away are connected via a wormhole. When a wormhole connects two objects, one must lie to the future of the other. Quantum versus teleportation and ER equals EPR. Quantum gravity may have as much to tell about the foundations and interpretations of quantum mechanics as it does about gravity. Copenhagen interpretation of quantum mechanics and Everett's relative scale formulation are complementary descriptions which in a sense are dual to one another. I put the series to discuss this duality in the light of the ER equals EPR conjecture. Okay, so this should conclude. Well, I'm very close to concluding this. It's already gone on for a very long time. Let me see if I can. Find the part on hormones. Okay, here's hormones. Alright, I think this one. Proposed to move wormholes exist that might allow time travel. A proposed time travel machine using a traversable wormhole might hypothetically work in the following way. One end of the wormhole is accelerated to some significant fractional speed away from our advanced propulsion system and then brought back to the plate of orbit. Alternatively, another way is to take one entrance of the wormhole and move it within the gravitational field of an object that has higher gravity than the other entrance, and then return it to a position near the other entrance. For both these methods, time dilation causes the end of the wormhole that has been moved to have aged less, or to become younger. For the stationary as seen by an external observer, however, time connects differently through the wormhole than outside it. So that synchronized clocks At either end of the wormhole will always remain synchronized as seen by an observer passing through the wormhole, no matter how the two ends move around. This means an observer entering the younger end would exit the older end at a time when it was the same age as the younger end, effectively going back in time as seen by an observer from the outside. One significant limitation of the time machine is that it only possible to go as far back in time as the initial creation of the machine. It is more of a path through time rather than a device that itself moves through time. And it will not allow the technology itself to be moved backward in time. According to current theory of the nature of wormholes, construction of a traversable wormhole would require the existence of a substance with negative energy, often referred to as subatomic matter. Technically, the wormhole spacetime requires a distribution of energy that allows the various energy conditions, such as a null energy condition, along with a weak, strong, and dominant energy condition. However, it is known that quantum effects can lead to small measurable violations of the null energy condition. And many physicists believe that the requirement of energy will actually be possible due to the Casimir effect in quantum physics. Although early calculations suggested a very large amount of negative energy would be required, later calculations showed that the amount of negative energy can be made arbitrarily small. In 1993, Matt Rissler argued that the two maps of a wormhole with such a reduced clock difference could not be brought together without inducing quantum field or gravitational effects that would either make the wormhole collapse or the two maps would collapse. Or otherwise prevent information from passing through the wormhole. This, the two maps could not be brought close enough for causality values to be however in 1997. Paper Visser hypothesized that a complex Roman ring, configuration of an n-number wormhole according to a symmetric polygon, still active with time machine, although he concludes that they were more likely a flaw in classical quantum gravity theory rather than proof. The causality violation. Workshop, we discussed two types of wormhole, the Stephen Morris Thorne theoretical wormhole and the somewhat more housebroken Visser wormhole. Both wormholes are shortcuts to space-time, completely consistent with certain gravity theory that agree to offer the possibility of faster light travel and even time travel. Which were shortcuts to advanced civilization in order to go manipulating planet mass energy by being able to snatch from the quantum foam. The ability to use useful science to realize that placing a Casimir effect, vertical capacitor, and the wormhole mouth. These could principally be used for faster light travel and time travel. Matt Visser wormhole provides the FTL space travel with a more benign environment. Visser conceived the creation of a wormhole geometry of the cutting, so the wormhole improves into space-time and pulling the edges together. Instead of distributing the curvature of space at the wormhole mouth over a broad region, including the space through which travel must pass. This is replacing the flat space or remote connection of struts that contain a region of very sharp curvature. Needed to make the strut is not ordinary matter, but in a sense it's perhaps available. The springs and your fractures, the usual common strings are very massive, perhaps Earth mass per meter. Creating the slot wormholes, this area needs a slightly different version of the property of negative mass. The negative mass of the strut edges average the M2 wormholes bounced by the positive mass of the mouth itself. Meaning the wormhole structure with a relatively small, perhaps zero mass. This would suggest making a wormhole mouth in the form of a cube with flat, phase wormhole connections on the square sides and strings as the edges. Each cube face may connect to the face of another wormhole mouth cube before the 6 cube faces may connect to 6 different cube faces in 6 separate locations. Research use the wormhole mouth is reminiscent familiar SF notion of a stargate. It's very interesting that cosmic strings are completely visible wormholes cosmology since the theory that loops of quantum string are reproduced in the early phases of the Big Bang. Particularly the solar inflationary phase where the universe undergoes very rapid expansion. The relation of negative energy string loops forming one level of the Big Bang could result in stable objects that have a net positive mass. The extent of the plausible scenario for the formation of stable natural wormholes that might still exist in the universe. How to find a wormhole? With a positive electric charge Q coupled to a wormhole mouth, the electric lines of force radiating original charge must flow through the aperture of the wormhole. The net result is that the entrance wormhole mouth has lines of force radiating away from it, and the exit wormhole mouth has lines of force radiating toward it. In effect, the entrance mouth has now been given a positive electric charge, and the exit mouth acquires a corresponding negative charge. Similarly, the mass M passes through a wormhole mouth, the entrance mouth has a mass increased by M, and the exit mouth has a mass reduced by M. In the early universe, these mass changes might create a dynamically unstable situation. If one natural wormhole mouth begins to increase mass, its swing will correspondingly reduce mass, and so it requires a net negative mass. The mouth with positive mass will attract more mass to it, while the negative mass swing will gravitationally repel any nearby mass. Thus, the mass of knowledge should grow until eventually damped by the growing distance scale from the expansion of the universe. The act of wormhole mouths on planet size or star size negative mass. These would repel nearby masses, or like normal stars or planets, would be attracted to the mass of our galaxy in orbit around it. While negative mass of such objects might be exploited in searching for them. You see the gravity field of the object as a web going briefly over a period of days or weeks to increase the brightness of a more distant background star as the object has a color between the observer and the background star. Negative mass object will produce a gravitational lensing effect in the form of a diverging line of converging lines. Background sections will be dimmed or extinguished if the negative mass object passes through the line of sight. That vanishes and returns, producing a time profile that is quite distinctive. The EMP wormholes also describe the way in which the time machine waves a relative time relation to create time distance between one mouth and the other. This arises with the magnitude of quantum vacuum fluctuations depends on the space-time interval square root distance squared minus c time squared, and on a circuit threading through the wormhole and then back in normal space. As the wormhole becomes a time machine, the interval first becomes very small, then becomes zero, and then becomes negative. During the transition in the region near zero, interval as a crossover is called the Cauchy horizon. Black hole. During the quantum fluctuations should, according to Hawking's calculations, go without limit and destroy the wormhole. And it's interesting to know that there's a transition from the Cauchy horizon produces this catastrophe, not the existence of a time-spanning wormhole. Somehow the time-spanning wormhole negative interval will be established. It would perhaps be as stable as a space-spanning wormhole positive interval. And it should corollary of this is that even when two wormholes each span a positive interval, a path running both of them then have a zero interval leading to the Cauchy instability. This and a recent paper showed that under certain circumstances the instability might be evaded, but only for a very small aperture wormhole separated by a distance approaching the diameter of the universe. That's not very small. If there are naturally occurring wormholes, it was suggested that because of back reaction, they might arrange themselves to fill all of the available wormhole space. If they vigorously resist low quantum fluctuations and back reaction, any attempt to create new wormholes or to significantly alter the space-time connections of existing ones. Authors describe, this includes Kip Thorne and Michael Morris, authors describe how advanced civilization might A, create a large wormhole, destabilize it, prevent recollapse, and reconvert it to a time machine. Device for traveling or at least communicating back and forth in time. There's furthermore no well-established theory that can accommodate both quantum mechanics and the physics of strong gravitational fields within the same mathematical framework. Sleeper is a vehicle for getting in a rather unorthodox way what restrictions a perfect year quantum gravity might place on the physics of wormholes. Authors demonstrate that general relativity contains within this framework mechanisms that appear to permit both faster light and time travel. Based on example of quantum theory on visual length small distance scale is not empty at all, even at nuclear dimensions 10 to the minus 14 centimeters. Empty space is filled with particle and antiparticle pairs that are constantly flashing into and brief. The distance bankrolled on the kind of borrowed mass energy, only to leak out of existence again as the law of conservation of energy asserts research results. If the length scale is contracted to a size appropriate to quantum gravity, 10 to the minus 33, this quantum fireworks intensifies to a quantum fold of violent fluctuations in the topology and geometry of space. Quantum black holes form and vanish in a span of 10 to the minus 23 seconds, how occur in convoluted regions of space. In any physically allowed configuration from a brief existence. In this environment, they speculate a possible civilization considerably more advanced than ours by pulling a wormhole out of the quantum foam and enlarging into a classical science connection between two nearby points in space. This would use the well-known quantum mechanical process called tunneling. Jump from one allowed energy state to another across a barrier of intermediate states. They're forbidden by energy conservation. Stabilize the wormhole, pull from the quantum field, warming its immediate collapse, pulls the electric field with such enormous strength that it creates enough energy in the top wormhole to force it to remain open. This is like the cosmos placing a pair of spheres with equal electric charges at the two spatial entrances of the wormhole. The spheres would be held in place, thus to balance the force of the gravitational attraction, thus offsetting the force of the electrical repulsion. Such a system might be very small, an atom-scale opening permitting the passage of only a few photons at a time, or it might be large enough to pass a large field. If reduced to stabilized wormhole, the engineering can begin. The size of the connection can be enlarged or contracted depending on energy considerations. The two portal ends of the wormhole connection can be separated from each other. For example, a portal placed aboard a ship might be carried to some location many light years away. Some trip might require a long time, but during the trip and afterwards, instantaneous communications and transport through the wormhole would be available. The ship could even be supplied with fuel or provisions through the portal. Similar scenarios are being example understands the energy stars in which starships were traveling with parts travel at sublight speed but be carried on board matter transmitters that permitted instantaneous transmission of crew and supplies from Earth. Direction of a time machine. Suppose that initially a wormhole establishes a connection between two spatial points A and B that have no motion with respect to each other are simultaneous in time. Simultaneous is simply concept of relativity. We mean that an observer at A would determine the clock reading at B would get the same reading by a normal space, by the light beam signal. Brackets the transmit time, for example, as you would through the wormhole. Now suppose in the spirit of the twin paradox of special relativity, the portal B is placed aboard a spaceship and portal A remains on Earth. Ship carrying B, say, accelerates rapidly to 86.6% of light speed of travel, a distance of 1 light-foot. Then reverses course and returns towards the same speed. The arrival portals, A and B, are placed near one another at 86.6% of the velocity of light. Any clock aboard the ship will run at just half the speed of a similar clock on Earth due to relativistic time dilation. Therefore, at the end of the trip, the ship's clock will be about 1 year 12 as compared to an identical clock that will remain on Earth. And a Morse law and a portal going out, portal B will also be 1 year 12 as compared to portal A. Now, a message sent through B to A will emerge 1 year in the future of B, and the message sent through A to B will emerge 1 year in the past of A. Similarly, a traveler making the same trips through the wormhole will travel 1 year into the future or the past. The wormhole connection through space will be transformed to a connection through time. A wormhole time machine. Restrictions usually associated with special relativity implicitly assume that no time travel is time travel is possible. Clearly, one could travel in effect at an infinite velocity that traveling from one place to another at some sublight velocity and arrival traveling backwards in time to the instant of departure. Put another way, the simultaneous simultaneity measurements dominated by special relativity must lead to a definite and ambiguous determination of simultaneous readings of two clocks separated in space. The clock comparisons made possible by wormholes are not definite, because one clock could be in the future beyond displaced by any time interval produced by travel histories of the portals. Special relativity, after all, is embedded in the theory of general relativity that produces these relations of wormhole pictures is preserved. Laws of physics that would be destroyed by the conception of wormhole space-time connection is causality, the mysterious principle that prohibits communication backwards in time. That requires a cause to precede its effects and time sequence in all space-time references. Causality as a law of the universe would not survive even a two-way communication link across time, let alone a portal permitting trans-time matter transmission. The principal purpose of Morse and Yertz are definitely what an advanced simulation might do with wormholes, as mentioned above, is to demonstrate in effect that if causality is to be preserved as a law of physics, it must be seen at the quantum level. Quantum gravity theory which have not yet been developed must impose some new physical limitations that make impossible the production of stable wormholes, like the Morse form scenario. General relativity, our present theory, gravity, prohibits neither fast and light space travel nor time travel with wormholes, so it does require the two go together. Writers of hard SF should have fun with that. Reversible wormhole geometry. In its brief report, I introduced yet another class of geometries for which some classical chronology protection theorems are of dubious physical reliability. You consider Roman ring of traversable wormholes where a number of wormholes are arranged in a ring in such a manner that no subset of wormholes is near to chronology violation, though the combined system can be arbitrarily close to chronology violation. Ensure that with enough wormholes in the ring, the gravitational vacuum polarization, the expectation of the quantum energy, stress energy tensor, can be made arbitrarily small. In particular, the back reaction can be kept arbitrarily small, all the way to the reliability rises. So semi-classical quantum gravity becomes unreliable before the gravitational back reaction is absorbed. Okay, so I believe this is just about done. Okay. So, just about finished here, finally. This has become one long exercise. So yes, I will be concluding this now. And this is the end of the true part 47 of the Origin SC series. And so this should conclude the sojourn into the quantum wormhole world. However, I might resume at any point if you want to elaborate on any of these. Okay. I am signing off, and we'll talk to you all later. Okay, so I'm just going over this Homer Ellis fantastic theory. I'm going to add this to the last part. Chronology without Einstein's assumption that inertial mass produces gravity. Giving up Einstein's assumption implicit in the 1916 field equation is that inertial mass, even its appearance as energy, is equivalent to active gravitational mass, and therefore the force of gravity allows revising the field equations to form in which a positive cosmological constant is seen to misrepresent a uniform negative net mass density of gravitationally attractive and gravitationally repulsive matter. Field equations with both positive and negative active gravitational mass densities of both primordial and continuously created matter incorporated along with two scalar fields to relax the constraints of the space-time geometry, yield cosmological solutions that exhibit inflation, deceleration, coasting, acceleration, and a big bounce instead of a big bang, and provide good fits to a Hubble diagram of type 1A supernova data. where parts of matter is identified as the backsides of the drain holes introduced by the author in 1973 as solutions of those same field equations. Drain holes put examples of invisible wormholes are topological tunnels in space which gravitationally attract on the front entrance sides and repel more strongly on their back exit sides. The front sides serve both as the gravitating cores of the visible baryonic particles, primordial matter, and as the continuously created invisible particles of the dark matter, to hold together the large-scale structures being in the universe. The backside serve as the misnamed dark energy, driving the current acceleration and expansion of the universe. Formation of cosmic voids, walls, filaments, and nodes is attributed to the expulsion of drainage of drain hole entrances from regions populated by drain hole exits. Accumulation of the entrances on boundaries separating those regions. Okay, last part. Formation of cosmic voids, walls, filaments, and nodes is attributed to expulsion of drain hole entrances from regions populated by drain hole exits. And accumulation of the entrances on boundaries separating those regions. Okay, that's a wrap for now. Back to the nature of the paper. Van Ramsdon's approach to resolving incompatibility restraint already was needed in this area's entanglement, phenomenon that many physicists believe to be ultimate in quantum weirdness. Entanglement lets the measure of one particle continuously determine the state of a partner particle, no matter how far away it is, even on the other side of the Milky Way. Einstein loathed the idea of entanglement, and Van Ramsden, drawing on work by right-sided physicists going back over a decade, argued for the ultimate irony, that despite Einstein's objections, entanglement might be the basis of geometry and thus of Einstein's geometric theory of gravity. Space-time, he said, was just a geometric picture of how stuff in the quantum system is entangled. The idea is a long way from being proven as hardly a complete theory of quantum gravity, but independent studies have reached much the same conclusions, drawing intense interest from major theorists. A small industry of physicists is now working to expand the geometry-entanglement relationship using all the modern tools developed in quantum computing and quantum information theory. I would not hesitate for a minute to call the connection between quantum theory and gravity that has emerged in the last 10 years revolutionary. Much of this work rests on a discovery announced in 1997 by physicist Juan Maldacena, gravity without gravity, now at the Institute for Advanced Study in Princeton University. Maldacena's research had led him to consider the relationship between two seemingly different model universes, one in the cosmos similar to our own, although it neither expands nor contracts in its three dimensions, is filled with quantum particles and obeys Einstein's equations of gravity. Known as anti-de Sitter space, ADS is commonly referred to as the bulk. The other model is also filled with elementary particles, but it has one dimension fewer and doesn't recognize gravity. Commonly known as the boundary, it is a mathematically defined membrane that lies in infinite distance from any given point in the bulk. It completely encloses it, much like the 2D surface of a balloon enclosing a 3D volume of air. The boundary particles obey the equations of the quantum system, known as conformal field theory, CFT. Maldacena discovered that the boundary and the bulk are completely equivalent, like 2D circuitry of a computer chip that encodes 3D imagery of a computer game. Relatively simple gravity-free equations that prevail on the boundary contain the same information and describe the same physics as the more complex equations that rule the bulk. Kind of a miraculous thing. Suddenly, said Maldacena's duality gave physicists a way to think about quantum gravity in the bulk without thinking about gravity at all. They just had to look at the equivalent quantum state on the boundary. And in the years since, so many have rushed to explore this idea that Maldacena's paper is now one of the most highly cited articles in physics. Among the enthusiasts was Van Ramsden, who started his sabbatical by pondering one of the central unsolved questions posed by Maldacena's discovery. He Directly how does the quantum field on the boundary provide gravity in the bulk? There had already been hints that the answer might involve some sort of relation between geometry and entanglement, but it was unclear how significant these hints were. All the earlier work on this idea had dealt with special cases such as the bulk universe that contained a black hole. So when Ramsden decided to settle the matter and work out whether the relationship was true in general or was just a mathematical oddity. Very interesting. He first considered an empty bulk universe, which corresponded to a single quantum field on the boundary. This field and the quantum relationships that tie various parts together contained the only entanglement in the system. But now Van Ramsden wondered what would happen to the bulk universe if that boundary entanglement was removed. He was able to answer that question using mathematical tools introduced in 2006 by Shinzo Rui, now at the University of Illinois Urbana-Champaign, and Tadashi Takanagi, now at the Yukawa Institute for Theoretical Physics at Kyoto University in Japan. The equations allowed the model of slow and methodical reduction in the boundary field's entanglement and to watch the response in the bulk, where he saw space-time steadily elongating and pulling apart. The entanglement connection. Ultimately, he found reducing the entanglement to zero and breaks the spacetime into disjointed chunks, like chewing gum stretched too far. Geometry entanglement relationship with general Van Ramsden realized. Entanglement is the essential ingredient that makes space-time together into a smooth whole, not just in exotic cases with black holes, but always. I felt that I had understood something about a fundamental question that perhaps nobody had understood before, he recalled. Essentially, what is space-time? Entanglement and Einstein. Quantum entanglement and geometric glue, this was the essence of Van Ramsden's rejected paper and winning essay, and an idea that has increasingly resonated among physicists. The one that has yet found a rigorous proof, so the idea still ranks as a conjecture, but many independent lines of reasoning support it. In 2013, for example, Maldacena and Leonard Susskind of Stanford published a related conjecture that they dubbed ER equals EPR, in honor of two landmark papers from 1935. ER by Einstein and Rosen introduced what is now called a wormhole, a tunnel through space-time connecting two black holes. EPR by Einstein, Rosen, and Boris Podolsky was the first paper to clearly articulate what is now called entanglement. Maldacena and Susskind's conjecture was that these two concepts are related to more than a common publication. If any two particles are connected by entanglement, the physicist suggested that they were effectively joined by a wormhole, and vice versa. The connection that physicists call a wormhole is equivalent to entanglement. There are two different ways of describing the same underlying reality. No one has a clear idea of what this underlying reality is, but physicists are convinced that it must exist. Maldacena, Susskind, and others have been testing the ER equals EPR hypothesis to see if it is mathematically consistent with everything else that is known about entanglement and wormholes. And so far, the answer is yes. Other lines of support for the geometry entanglement relationship come from condensed matter physics and quantum information theory, fields in which entanglement already plays a central part. This has allowed researchers from these disciplines to attack quantum gravity with a whole array of fresh concepts and mathematical tools. Now we're to tensor networks again. Tensor networks, for example, are a technique developed by condensed matter physicists try to progress states that reach numbers of subatomic particles. Swingle in 2007, Dr. Reduced Electron, direct repository, found that the most useful network for this purpose started by linking adjacent pairs of electrons, which are most likely to interact with each other while making larger and larger groups in a pattern that resembles the hierarchy of the family tree. Within during a course of quantum field theory, Swingle learned about the field bulk boundary correspondence, noticed that the tree pattern, the mapping between the bulk and the boundary showed exactly the same tree-like network. You can see the space is being built from entanglements. Independently reach much the same conclusion as Van Strong, thereby adding strong support to the geometry of entanglement idea. You can think the space is being built from entanglement in this very precise way using the tensors. As the networks become frequently used tools to explore geometry entanglement correspondence. Another prime example of post-fertilization is the theory of quantum error correction codes, which physicists invented to aid the construction of quantum computers. These machines encode information out in bits and qubits, quantum states such as up-down, spin of electron that can take on values of 1 and 0 simultaneously. In principle, when the qubits interact and become entangled, the right way such a device can perform calculations that an ordinary computer cannot finish in the lifetime of the universe. So in practice, the process can be incredibly fragile and silence disturbance from the outside world. It will disrupt the qubit's delicate entanglement and destroy any possibility of quantum computation. That need inspired quantum error correcting codes, numerical strategies that repair corrupted correlations between the qubits and make the computation more robust. One hallmark of these codes is that they always found local. The information needed to restore any given qubit has to be spread out over a wide region of space. Otherwise, damage any single spot can destroy any recovery. That non-locality in turn accounts for the fascination that many quantum information theorists feel when they first encounter solvents in bulk boundary correspondence. It shows a very similar kind of non-locality. The information that corresponds to a small region of the bulk is spread over a vast region of the boundary. Anyone could look at ADS-CFT and sort of think the analogous to a quantum error correcting code. But they argue for something stronger, that the Malthusian duality is itself a quantum error correcting code. They have illustrated that this is mathematically correct in the model. And now I'm trying to show that the assertion holds more general. People have been saying for years that entanglement is somehow encoded for the emergence of the bulk. But for the first time, I think we are really getting a glimpse of how and why. Now the science foundation formed purple, give it 2.5 million per year for 4 years to be third on gravity quantum information. Information theory provides a powerful way to start thinking about fundamental physics. Exceeding researchers at 13 institutions worldwide, students postdoctorate the workshops in the school. Ultimately, one major goal is to build a comprehensive dictionary for translating geometric concepts into quantum language and vice versa. We hopefully help physicists find a way to the complete theory of quantum gravity. Several challenges. One is that the bulk boundary correspondence to the apply in our universe, which is neither static nor bounded, and expanding and parallel infinite. Most researchers in the field using calculation using Malthusian correspondence are telling them something true about the real universe, but there's little agreement as yet on exactly how to translate results from one machine to the other. Another challenge is that the same definition of entanglement also refers to particles only in a given moment. A complete theory of quantum gravity will have to add time to the picture. Entanglement is a big piece of the story, but it's not the whole story. These physicists may have to embrace another concept in quantum information theory, computational complexity. The number of logical steps or operations in the quantum state of the system. A system with low complexity is analogous to a quantum computer with almost all the qubits on zero. It is easier to define and build. One with higher concepts analogous to a set of qubits encoding a number that would take eons to compute. Thus, science rose to computational complexity together a decade ago, where we noticed that the solution to Einstein's equation of general relativity allowed a wormhole in ADS-C to get longer and longer as time went on. Did that correspond to on the boundary you wondered? What was changing there? Einstein knew that it couldn't be entanglement because the correlations that produce entanglement between different particles on the boundary reached their maximum in less than a second. In Article Astro, he and Douglas Stanford at the Institute for Advanced Study showed that as time progressed, the quantum state of the boundary would vary in exactly the way expected with computational complexity. It appears more and more that the growth of the interior of black holes is actually the growth of computational complexity. That's Einstein. If quantum entanglement mixed together pieces of space, he says, then computational complexity may drive the growth of space, and thus bring in the elusive element of time. One potential consequence, which he is just beginning to explore, could be a link between the growth of computational complexity and the expansion of the universe. Another is that because the inner of black holes are the very region where quantum gravity is thought to dominate, that computational complexity can have a key role in the complete theory of quantum gravity. Despite there being challenges, there is a sense among the practitioners of this field that they began to build something real and very important. I didn't know what space was made of before this window, I wasn't clear, and especially given our meaning, but now it's become increasingly apparent that that should make sense now. It goes through something we understand. So it goes with entanglement. After Moran Buffett wrote the 20 papers on quantum entanglement in 2009. All of them he said have been accepted for publication. So that should be it. Okay, the two universes that proved ADS-CFT, one as a cosmos with black hole has 10 dimensions with 8 of them forming an 8-dimensional sphere. Lower dimensional gravity-free one has but a single dimension and its menagerie of quantum particles resembles a group of idealized strings or harmonic oscillators attached to one another. Nevertheless, the Maldacino, the numeric proof that these really disparate worlds are actually identical gives hope that the gravitational properties are equivalent to what will be explained by simpler cosmos, purely in terms of quantum theory. Namely, that the thermodynamics of certain black holes can be reproduced from a lower dimensional universe, like Leonard Susskind. Testing quantum gravity and all sequence of papers is very nice because it tests the real nature of the universe is overviewed by our hours. So basically, the internal energy of a black hole, the position of its event horizon, boundary between the black hole and the rest of the universe, its entropy and other properties based on the predictions of theory of the effects of so-called virtual particles that continuously pop up into and out of existence. There's one universe and the other. He and his scholars calculated the internal energy corresponding lower dimensional cosmos with no gravity to two computer calculations. We translates back and forth between the two languages and solve problems in one model would seem intractable in the other, and vice versa. Proposed an audacious model of the universe in which gravity rises from infinitesimal time in vibrating strings can be reinterpreted in terms of well-established physics. The mathematically intricate world of strings, which exists in 9 dimensions of space, both one of time, would be merely a hologram. The real action would play out in a simpler, flatter cosmos where there is no gravity. When we saw the string theory calculations that we're working on, the fellow students who recognized the equation the same one we had been using to analyze the plasma. They could know immediately what was going on. When we worked on an idea proposed in 1997 by Juan Maldacena, realized the string theory predicts the mathematical equivalence between two hypothetical universes, one of which would be similar to our own. It would have the same dimensions of space and one dimension of time, for example, and be filled with the same type of elementary particles, which would in turn obey familiar looking, for instance, quantum field equations, but it would not contain strings or gravity. The other universe would be the opposite, containing both strings and gravity. Indeed, the gravity would be strong enough to form black holes, but no elementary particles. It would also have an additional dimension of space. Maldacena's insight was simple and audacious. Any process involving particles and fields in the first universe, and it could equally well be described as a process involving gravity, black holes, and strings in the second universe, and vice versa. The equations might look different, but the fundamental physics would be exactly the same. That was why Sunstein and Gluon equations and string theory calculations started. They were the three-dimensional equivalent of the gravitational fields that he and Paul Castro had been studying in the four-dimensional universe. I was plugging back and forth between universes was weird, even though string theory standards and weird for non-string theorists. And Maldacena had shown that the map doesn't work not just between 3 and 4 dimensions of space, but also between 4 and 5, 5 and 6, and so on. As I started to talk, we began to see that Maldacena's mapping might be a powerful problem-solving strategy. We could start with a messy set of quantum field equations in our real three-dimensional world, report Gluon plasma equations say, then map those to the four-dimensional world in which the equations tend to be much easier to solve. Then we could map the results back to a three-dimensional world and read off the answer that worked. We turn the calculation on its head to give us a prediction from the value of the shear viscosity of a plasma, such that referring to a key parameter of the quark gluon fireball. Undermining nuclear physics, jokes and ours was the first useful paper to come out with string theory. 2008, the team's predictions were confirmed by the relativistic heavy ion collider at Brookhaven in Upton, New York. These were strong quantitative results and they still stand today as the best results achieved by the program to relate string theory to experiment. Also, success also caught the attention of Stuber Sackler, who condensed metal theorists at Harvard. Physicists said that seen a plasma effect back evidence Starbuck's equations. Sackler saw quantum critical phase transitions, changing the state of occurring materials when they were near absolute zero. When quantum mechanical effects began to dominate, they were using different words, he said, but it was the same physics. Sackler hoped that Malvicino's idea could have provided his fellow theorists with some much needed help in exploring this chosen realm. Over the decades, experimental physics discovered a long list of guided quantum states, including superconductors that allow currents to flow without resistance, fluids that flow viscosity, and keep up the walls of beakers. Bose-Einstein condensates made of atoms moving in step like a single superatom, and strange metals that behave in ways somewhat different from ordinary metals. Physicists still have no way to predict what will turn up in the lab next. We can't even answer the fundamental question of how many phases of matter exist. So it's Sean Hartman, string theorist at Stanford. Sackler's first efforts to apply Malvicino's idea to a lab material had resulted in two papers he co-authored in 2007, one with Sun and his colleagues, another with the team included Hartman. Since then, Sackler's project have built up a recipe for mapping the conductivity of strange metals to the properties of black holes in the string theorist's four-dimensional universe. The project with string theorists at MIT and others are also pursuing. These groups get answers that they have reproduced through the American behavior of the metal. They also map the behavior of four-dimensional black holes in string theory, the conditions at which many materials will change phase into states other than the familiar solid liquid gas. We now have a whole new hammer for attacking the problems I have been working on for 20 years. Sackler's involvement in turn has helped ignite people to order from much matter physicists. A lot of us got disputed with the force of Sabir's personality and reputation. We realized it was taking this seriously. Maybe we should too. What's called the string theorists. Eventually, the field has become generally unenthusiastic about following up on the quantum calculations. At least part of the reason is to the bias against studying string theories, period. So it's not really among some folks that was turned near. Roughly 10 to the 500 pounds basic equations, each of which describes the possible universe with its own size, shape, dimensionality, and physical laws. Through Malvicino's ideas of string theorists, each solution will be expressed in countless materials yet to be discovered. The rewards are mutual. If I talk about superconductors and black holes in the colloquium, folks are attracted to it like bees to honey. It's not giving young blood to condense matter physics as their first choice. It is unique to try to actively make two groups of physicists collaborate so quickly. I haven't personally seen any other sort of drive over the course of my career. agree that condensed matter physicists are much more hesitant in pairing up with string theory counterparts, and remarkably unsuccessful at getting condensed matter physicists to let string theorists speak at their big meetings. They feel that they will need to learn string theory to talk to them. Instead, I am asking them to have coffee with aliens. That might be fun. The end results come to reduce derivation or answer the condensed matter theorists that are already calculating using more mundane methods. Some possible predictions from string theory were a tad bizarre from the condensed matter viewpoint. For example, the calculations suggest that when some crystalline materials are cooled towards absolute zero, they will end up in one of many low-energy ground states, but that violates the full law of thermodynamics, which insists that these materials towards just one ground state. That's the goal in the room that should keep people awake at night. Skeptics, theorists, and visually searching for possible predictions that will lead to killer evidence that the collaborations are worthwhile. Hunting for black hole configuration in the string theory universe that map to undiscovered space transitions, triggers to figure out which materials can exhibit those transitions. Right now, everyone is going around asking, have you seen something like this? But the hope is that as techniques advance, experimenters will be able to engineer materials with the properties we predict. Applying string theory to an existing challenge, calculating how conductance should change with temperature. And its focus of atoms transition from a fluid state to an insular. He thinks that it should be possible to test this prediction in the next couple of years. Even if the program is successful, there are limits as to how much relation can benefit either partner. String theory can offer a handbook of properties to look for and predictions for how they should change with experiments. It will never be able to declare the theory of how the properties emerge from the behavior of electrons. Similarly, experimental verification of string theory's predictions about condensed matter will not prove that strings themselves are an accurate description of reality. Perhaps Green argues the connections to materials will show that people have fundamentally misunderstood what string theory is. Maybe string theory is not a unique theory of reality, but something deeper, a set of mathematical principles that can be used to relate to all physical theories. Maybe string theory is the new calculus. Okay, so that is the end of the facts. All of them. I think that should be it. Just about finished. Okay. So, Let me just make sure there is no other one. I don't think there is. Alright, I'm ending this one. If there's more, I shall add it later. Hello everyone, this is part 51. I have some important updates to make to the Origin series, mostly regarding black holes and also somewhat unification. So we're going to start with this great article about solving the black hole information paradox. The most famous paradox in physics is its end. In a landmark series of calculations, physicists have proved that black holes can shed information, which seems impossible by definition. The work appears to resolve a paradox that Stephen Hawking first described 5 decades ago. In a series of breakthrough papers, theoretical physicists have come tantalizingly close to resolving the black hole information paradox that has advanced and bedeviled it for nearly 50 years. Information, they now say with confidence, does escape a black hole. If you jump into one, you will not be left for good. Particle by particle, the information needed to reconstitute your body will reemerge. Most physicists have long assumed it would. That was the upshot of strict theory, the leading candidate for a unified theory of nature. The new calculations, though inspired by strict theory, stand on their own. Information gets out through the workings of gravity itself, just ordinary gravity with a single layer of quantum effects. This is a peculiar role reversal for gravity. According to Einstein's general theory of relativity, the gravity of a black hole is so intense that nothing can escape it. The more sophisticated understanding of black holes developed by Stephen Hawking and his colleagues in the 1970s to not question this principle. Hawking and others sought to describe matter in and around black holes using quantum theory, but they continued to describe gravity using Einstein's classical theory. A hybrid approach that physicists call semi-classical. Although the approach predicted new effects of the perimeter of the hole, the interior remained strictly sealed off. Physicists figured that Hawking had nailed the semi-classical calculation. But further progress would have to treat gravity too as constant. This is what the authors of the new study dispute. They have found additional semi-classical effects, new gravitational configurations that Einstein's theory permits, but that Hawking did not include. Using it first, these effects come to dominate when the black hole gets to be extremely old. The hole transforms from a hermit kingdom to a rigorously open system. Not only does information spill out, anything new that falls in is regurgitated almost immediately. The revised semi-classical theory has looked to explain how exactly the information gets out, but such has been the pace of discovery in the past 2 years the theorists already have hinted of the escape mechanism. That is the most exciting thing that has happened to this subject since Hawking. It's a landmark calculation. You might expect the authors to celebrate, but they also say they feel let down. Now, the calculation involved deep features of quantum gravity rather than a light dusting. It might have been even harder to pull off, but once that was accomplished, they would have illuminated those depths. So they worried they would have solved this one problem without achieving the broader closure they sought. The hope was if we could answer this question, we could see the information coming out. In order to do that, we would have had to learn about the microscopic theory, alluding to the fully quantum theory of gravity. What it all means will be intensely debated in Zoom calls and webinars. The work is highly mathematical and has a Rube Goldberg quality to it, stringing together one calculational trick after another in a way that is hard to interpret. Wormholes, the holographic principle, emergent space-time, quantum entanglement, quantum computers, nearly every concept of fundamental physics these days makes an appearance, making the subject both captivating and confounding. And not everyone is convinced. Some still think that Hawking got it right and that string theory or other novel physics has to come into play if information is to escape. I'm very resistant to people who come in and say I've got a solution, it's just quantum mechanics and gravity. Because it's taken us around in circles before. But almost everyone appears to agree on one thing. But some way or other, space-time seems to fall apart at a black hole, implying that space-time is not the root level of reality, but an emergent structure from something deeper. Although Einstein conceived of gravity as a geometry of space-time, his theory also entails the dissolution of space-time, which is ultimately why information can escape its gravitational physics. In 1992, Don Payne and his family spent their Christmas vacation house sitting in Pasadena, enjoying the swimming pool and watching the Rose Parade. Page, a physicist at the University of Alberta in Canada, also used the break to think about how paradoxical black holes really are. His first studies of black holes when he was a graduate student in the 70s were key to his advisor, Stephen Hawking's realization that black holes emit radiation. The result of random quantum processes at the edge of the hole. Put simply, a black hole rocks from the outside in. The particles it sheds appear to carry no information about the interior contents. If a 100 kilogram astronaut falls in, the hole grows in mass by 100 kilograms. Yet when the hole emits the equivalent of 100 kilograms of radiation, that radiation is completely unstructured. Nothing about the radiation reveals whether it came from an astronaut or a lump of lead. That's a problem, because at some point the black hole emits its last ounce and ceases to be. And all that's left is a big amorphous cloud of particles zipping here and there at random. It would be impossible to recover whatever fell in. That makes black hole formation and evaporation an irreversible process, which appears to defy the laws of quantum mechanics. Hawking and most other theorists at the time accepted that conclusion. If irreversibility collided the laws of physics as they were then understood, so much the worse for those laws. But Page was concerned with his irreversibility would violate the fundamental symmetry of time. In 1980, he worked with his former advisor and argued that black holes must release, or at least preserve, information. That caused a schism among physicists. Most general relativists I talked to agree with Hawking, said Page. The particle physicists tended to agree with me. On his Pasadena vacation, Page realized that both groups had missed an important point. The puzzle wasn't just what happened at the end of the black hole's life, but also what led up to it. He considered an aspect of the process that had been relatively neglected: quantum entanglement. The emitted radiation maintains a quantum mechanical link to its place of origin. If you measure either the radiation or the black hole on its own, it looks random. But if you consider them jointly, they exhibit a pattern. It's like encrypting your data with a password. The data without the password is gibberish. But the password, if you have chosen a good one, is meaningless too. but together they unlock the information. Maybe, on the page, information can come out of the black hole in a similarly encrypted form. Page calculated what that would be for the total amount of entanglement between the black hole and the radiation. Quantity known as the entanglement entropy. Starting the whole process, the entanglement entropy is zero, since the black hole has not yet emitted any radiation to the entanglement. At the end of the process, if information is preserved, the entanglement entropy should be zero again, since there is no longer a black hole. So here we have a duality, the black hole and the entropy, and the black hole and the radiation. Together they add up to the entropy. I got curious how the radiation entropy was changed in between. Page 6. Initially, as radiation trickles out, the entanglement entropy grows. Page reasons that this trend has to reverse. The entropy has to stop rising and start dropping, if it is to hit zero by the endpoint. Over time, the entanglement entropy should follow a curve, shaped like an inverted V. The page curve. When a black hole releases radiation, the radiation and the black hole should be quantum-mechanically linked. The total amount of connection is called the entanglement entropy. According to Stephen Hawking's original calculations, this quantity keeps rising until the black hole dies. But if information gets out, the entanglement entropy should instead follow the page curve. Page calculated that this reversal would have to occur roughly halfway through the process, at a moment now known as the page time. This is much earlier than physicists assumed. The black hole is still enormous at that point, certainly nowhere near the subatomic size at which any putative exotic text would show up. But no laws of physics should still apply, and there is nothing in those laws to bend the curve down. With that, the problem got much more acute. Physicists had always figured that a quantum theory of gravity came into play only in situations so extreme that they sound silly. Such as a star collapse into the radius of a proton. Now, Page was telling them that quantum gravity models under conditions that, in some cases, are comparable to those in your kitchen. Page's analysis justified calling the black hole information problem a paradox as opposed to merely a puzzle. It exposed a conflict within the semi-classical approximation. The Page time paradox seems to point to a breakdown of low-energy physics in a place where there is no business breaking down, because the energies are still low. According to philosophers of physics. On the bright side, Page's clarification of the problem paved the way to a solution. He established that if entanglement entropy follows the Page curve, the information gets out of the black hole. In doing so, he transformed the debate into a calculation. Physicists are not always so good at words. We do best with sharp equations. Now, physicists just have to calculate the entanglement entropy. If they can pull it off, they get a straight answer. Does the entanglement entropy follow an inverted V or not? If it does, the black hole preserves information, which means particle physicists were right. If it doesn't, the black hole destroys or bottles up information. like general relativists that held themselves to the first donut at faculty meetings. Even though Page spelled out what physicists have to do, it took the theorists nearly 3 decades to figure out how. Inside out black hole. Over the past 2 years, physicists have shown that the entanglement entropy of black holes really does follow the Page curve, indicating that information gets out. They did the analysis in stages. First, they showed how it would work using insights from string theory. But in papers published last fall, researchers cut the tether to string theory altogether. The work began in earnest in October 2018, when Albert Omari of the Institute for Advanced Study laid out a procedure for studying how black holes evaporate. Omari, who was joined soon by several colleagues, applied a concept first developed by Juan Malmsina, our IRS, in 1997. Pennington was working in parallel. Consider a universe encased in a boundary like a snow globe. Apart from having a big wall around it, the interior is basically like our universe. It has gravity, matter, and so forth. The boundary, too, is a kind of universe. It does not have gravity, and being just a surface, lacks depth. But it makes up for that with vibrant quantum mechanics. But all in all, it's exactly as complex as the interior. Different though these two universes may look, they are perfectly matched. Anything in the interior or bulk is a counterpart on the boundary. And even though the geometry of the bulk is unlike the geometry of our own universe, this ADS-CFT duality, as the string theorist's favorite figure Aristos Malmsina introduced it. By the logic of this duality, if you have a black hole in the bulk, it has a shadow curve on the boundary. Because the boundary is governed by quantum physics without the complications of gravity, it unequivocally preserves information. So much the black hole. When researchers set out to analyze how black holes evaporate in ADS-CFT, they first had to overcome a slight problem. In ADS-CFT, black holes do not in fact evaporate. Radiation fills the confined volume like steam in a pressure cooker. And whenever the hole emits, it eventually reabsorbs. The system will reach a steady state. The very marvelous DeRocha, theoretical physicist at the University of Lisbon. To deal with that, Alvear and his colleagues adopted a suggestion of Rocha's. Put the equivalent of a steam valve on the boundary to bleed off the radiation, then prevent it from falling back in. It sucks the radiation out, said Neda Engelhardt of the Massachusetts Institute of Technology, one of Alvear's co-authors. The researchers plopped a black hole at the center of the bulk space, began bleeding off radiation, and watched what happened. To track the entanglement entropy of the black hole, they drew on more granular understanding of ADS-CFT. That Engelhardt and others, including Alan Wall at the University of Cambridge, have developed in the past decade. Physicists are now able to pinpoint which parts of the bulk correspond to which part of the boundary, and which properties of the bulk correspond to which properties of the boundary. The key to relating the two sides of the duality is what physicists call a quantum extremal surface. These surfaces are general features. You don't need a black hole to have one. Basically, you imagine blowing a soap bubble in the bulk. The bubble naturally assumes a shape that minimizes its surface area. The shape need not be round, like the bubbles at a child's birthday party, because the rules of geometry differ from the ones we are familiar with, because the bubble is a probe of that geometry. Quantum effects can descend to. By calculating where the quantum extremal surface lies, researchers obtain two important pieces of information. First, the surface carves the bulk into two pieces that matches each to a portion of the boundary. Second, the area of the surface is proportional to part of the entanglement entropy between those two portions. The boundary. Okay, so the area of the surface of the quantum extremal surface is proportional to part of the entanglement entropy between those two portions of the boundary. If the quantum extremal surface relates a geometric concept area to a quantum one, entanglement. Area to entanglement, providing a glimpse into how gravity and quantum theory might become one. But when researchers use these quantum extremal surfaces to study an evaporating black hole, a strange thing happened. Early in the evaporation process, they found and expected that the entanglement entropy of the boundary rose. Because the hole was the only thing inside space, the authors deduced that its entanglement entropy was rising. In terms of Hawking's original calculation, so far so good. Suddenly that changed. A quantum extremal surface abruptly materialized just inside the horizon of the black hole. Initially, the surface had no effect on the rest of it. But eventually, it became the deciding factor for entropy, leading to a drop. The researchers compared to a transitioning like boiling or freezing. We think of this as a change in phase analogous to thermodynamic phases between gas and liquid, Engelhardt said. It meant three things. First, a sudden shift signaled the onset of new physics, not covered by Hawking's calculation. Second, the extremal surface split the universe in two. One part was equivalent to the boundary. The other was a hear-me dragon's realm, about which the boundary had no information, indicating that bleeding radiation from the system was having an effect on its information concept, on its information content. So basically, the boundary, part of the boundary was covered what was happening inside the universe, but the other part was not. The radiation coming out of the black hole was actually affecting the information content. Third, the position of the quantum extremal surface was highly significant. It was located just inside the horizon of the black hole, As the whole shrank, so did the quantum extreme surface, and with it, the entanglement entropy. That would produce the downward slope that Page predicted. The first time any calculation had done that. Sorry about that. I guess I'm also running out from entanglement entropy. Anyway, here is the great black hole information escape. As black holes radiate, information appears to be lost. But this can be avoided if the entanglement entropy of the radiation rises then falls. Recent calculations have shown how this happens via quantum extremal surface. It appears just inside the black hole's event horizon. Everything inside of the surface is only not part of the black hole. Exactly how this happens, and what it all means, is still an enormous mystery. 1. Black holes radiate by forming entangled particle pairs. One particle flies out, the other in. 2. As the number of entangled particle pairs grows, so does the entanglement entropy. 3. A quantum extremal surface appears just inside the horizon, making the black hole into something like a shell. 4. The innermost particles are no longer part of the black hole. Their entanglement no longer counts towards the entropy. 5. As the black hole radiates the last of its energy, the total entanglement entropy drops to 0. Ta-da! That's how you have the inverted V-shaped Page curve. By showing that the entanglement entropy tracked the Page curve, the team was able to confirm that black holes release information. It dribbles out in a highly encrypted form made possible by quantum entanglement. In fact, it is so encrypted that it doesn't look as if the black hole has given up anything. But eventually, the black hole passes a tipping point where the information can be decrypted. The research posted in May 2019 shows all this using new theoretical tools that quantify entanglement in a geometric way. Even with these tools, the calculation has to be strict to its essence to be doable. The bulk in this ADS-CFT universe at just a single dimension of space, for example. The black hole was not a big black hole, it was not a big black ball, but a short line segment, in a single dimension of space. Still, the researchers argued gravity is gravity, and what goes for this impoverished line land should hold for the real universe. And in April 2020, Hashimoto, Izuka, and Matsuo of Osaka University analyzed black holes in a more realistic flat geometry, so 2D geometry, and confirmed that the findings still hold. In August 2019, Almiri and another set of colleagues took the next step and turned their attention to the radiation. They found that the black hole and its emitted radiation both follow the same Page curve, so that information must be transferred from one to the other. Glacier does not say how it was transferred, only that it is. As part of the work, they discovered that the universe undergoes a baffling rearrangement. At the outset, the black hole is at the center of space, and the radiation is flying out. But after enough time has passed, the equations say particles deep inside the black hole are no longer part of the hole anymore, but part of the radiation. They have not flown outward, but simply been reassigned. This is significant because the interior particles would ordinarily contribute to the entanglement entropy between the black hole and the radiation. If they are not part of the black hole anymore, they no longer contribute to the entropy, stating why it begins to decrease. Basically, the particles deep inside the black hole are not in the black hole anymore. They're in the radiation all of a sudden, like they jumped. And this is why the entropy worked out. The authors dubbed the inner core of radiation the island, and called its existence surprising. Okay, so they jumped from being particles inside the black hole to being radiation. What does it mean for particles to be in the black hole, but not of the black hole? Okay, so they're still inside the black hole, but they're not part of it, which is even more puzzling. So they didn't actually jump, they just transformed. In confirming that information is retained, the physicists eliminated one puzzle only to create an even bigger one. Whenever I asked Almiri and others what it meant, it looked off into the distance. They were terribly lost for words. Enter the wormholes. Ah, here comes the answer. So far, the calculations presume the ADS-CFT duality is still the world, which is an important test case but ultimately somewhat contrived. The next step is to consider black holes more generally. The researchers drew on a concept that Richard Feynman had developed in the 1940s. Known as the path integral, is the mathematical expression of a core quantum mechanical principle. Anything that can happen does happen. In quantum physics, a particle going from point A to point B takes all possible paths, which are combined in a wave sum. That's why it's called a path integral. The highest wave path is generally the one you'd expect from ordinary classical physics, but not always. If the waves change, the particle can abruptly lurch from one path to another, undergoing a transition that would be possible in old-fashioned physics. The path integral worked so well for particle motion that theorists in the 1950s proposed it as a quantum theory of gravity. That meant replacing a single space-time geometry with a mirage of possible shapes. To us, space-time appears to have a single, well-defined shape. Near the Earth, it is curved just enough that objects don't orbit the center of our planet. For example, but in quantum gravity, other shapes, including much curvier ones, are latent, and they can make up an appearance under the right circumstances, like different universes. Feynman himself took up this idea in the 60s, and Hawking championed it in the 70s and 80s. But even their considerable genius struggled with how to execute the gravitational path integral, as physicists set it aside in favor of other approaches to quantum gravity. We never really knew how to define exactly what it is, and guess what? We still don't. The John Presko of the California Institute of Technology, Caltech. For starters, what are all possible shapes? For Hawking, that meant all topologies. Space-time might knot itself into a donut or pretzel-like shapes. The extra connectivity creates tunnels or wormholes between otherwise far-flung places and moments. These cover different types. Elkingham, Kelly, Calabi, well, manifolds. Extension for each universe. Different shapes. Spatial wormholes are like the portals, the realms of science fiction writers, linking one star system to another. So-called space-time wormholes are little universes spun off our own that reunite with sometime later. But it's great way of looking like that'll link the multiverse or omniverse of tree. Or like branches of that. Astronomers have never seen either type. The general relativity permits these structures, and the theory of a good track record of making seemingly bizarre predictions of black holes and gravitational waves were later vindicated. Now, everyone agreed with Hawking that these exotic shapes belong in the mix, but the researchers doing the new analyses of black holes adopted the idea provisionally. We couldn't realistically consider all possible topologies, which are literally uncountable. We looked only at those that were most important to evaporating black hole. These are known for mathematical reasons as saddle points, that they look like fairly placid geometries. In the end, the team did actually perform the full summation of shapes, which is beyond them. They used a path integral mostly in the vehicle to identify the saddle points. The next step after applying the path integral to the black hole and its radiation was to calculate the entanglement entropy. This quantity is defined as the logarithm of a matrix. An array of numbers. The calculation is difficult in the best of times. But in this case, the physicists did actually have the matrix, which would have required reevaluating the path integral. When you have to perform an operation they couldn't do on a quantity, they didn't know. For that, they must drop another mathematical trick. So they have to do this on evaluate the path integral, but they don't know how to do it since they don't know the quantity. They notice that entropy doesn't require knowledge of the full matrix. They could instead imagine performing a repeated series of measurements on the black hole, and then combining those measurements in a way that retains the knowledge they need. This so-called replica trick goes back to the study of magnets in the 70s, and was first applied to gravity in 2013. So basically, they're going to measure the black hole several times and combine those measurements in a way that would help them keep the knowledge they need. One of the authors of the new work, Tom Hartman of Cornell, compared the replica trick to checking whether a coin is fair. Normally, you toss it many times and see whether it lands on each side with 50-50 probability. Of course, for some reason, you can't do that. So instead, you toss two identical coins. The replicas. And note how often we land on the same side. If this happens half the time, coins are fair. Even though you still don't know the individual probabilities, you can make a basic judgment about randomness. This is analogous to not knowing the full matrix of the black hole, yet still evaluating its entropy. Trick though it is, it has real physics in it. The gravitational path integral doesn't distinguish replicas from a real black hole. It takes them literally. This activates some of the latent topologies that the gravitational path integral includes. The result is a new saddle point containing multiple black holes, linked by space-time wormholes. So you have replica black holes and replica wormholes. It competes for influence with the regular geometry of a single black hole surrounded by a mist of Hawking radiation. Wormholes and the single black hole are inversely weighed by basically how much kind of the entropy they have. Wormholes have a lot, so they receive a lower weight. And are thus unimportant at first. But their entropy decreases, whereas that of the Hawking radiation keeps climbing. Basically, the wormhole is the vehicle that sends the entropy to the radiation. Eventually, the wormholes become the dominant of the field, and they take over the dynamics of the black hole. The shift from one geometry to the other is impossible in classical general relativity. It is an inherently quantum process. The extra geometric configuration and the transition process that access it are the two main discoveries of the analysis. In November 2019, two teams of physicists known as the West Coast and East Coast groups were geographical affiliations. Most of their work showed that this trick allows them to reproduce the page curve. In this way, they confirmed that the radiation spirits away the information content of whatever falls into the black hole. String theory needed to be true. Even the staunch critical string theory can get on board with the gravitational path integral. Still, as sophisticated as the analysis is, it doesn't yet say how the information makes its getaway. The construction of spacetime, at least calculations of the radiation and origin information. Somehow by measuring this, you should be able to learn what fell into the black hole, but how? Theorists in the West Coast group imagined sending the radiation into a quantum computer. After all, the computer simulation is itself a physical system. A quantum simulation, in particular, is not altogether different from what it is simulating. So there's the connection between the quantum simulation and what is being simulated. The physicist imagines collecting all the radiation, feeding it into a massive quantum computer, and running a full simulation of the black hole. All the radiation from the black hole going into the computer, running a full simulation of the black hole. And that led to a remarkable twist in the story. Because the radiation is highly entangled with the black hole itself. The quantum computer, too, becomes highly entangled with the hole. Within the simulation, the entanglement translates into geometrical link between the simulated black hole and the original. Wow. Put simply, the two are connected by a wormhole. Wow. It's like the black hole is directly taking over the computer and communicating to us. There's the physical black hole, and then there's a simulated one in the quantum computer. And there can be a replica wormhole connecting those. So Douglas Stanford, a theoretical physicist at Stanford, and a member of the West Coast team. How appropriate. The idea is an example of a proposal by Malvesina and Leonard Susskind of Stanford in 2013. That quantum entanglement can be thought of as a wormhole, or fractal. The wormhole, in turn, provides a secret tunnel through which information can escape the interior. Theorists have been intensely debating how literally to take all these wormholes. The wormholes are so deeply buried in the equations that their connection to reality seems tenuous. Yet they do have tangible consequences. It's hard to answer what's physical and what's unphysical, said Roger Bacharach, a physicist at Stanford, because there's something clearly right about these wormholes. But rather than think of the wormholes as actual portals sitting out there in the universe, Bacharach and others speculate that they are a sign of new, non-local physics. By connecting two distant locations, wormholes allow occurrences at one place to affect a distant place directly, without a particle force or other influence having to cross the intervening distance. This is an instance of what physicists call non-locality. Basically, everything is connected. Even things that are untouchable connected. There's a lot of implications, especially for quantum line theory as well. It seems to suggest that you could have non-local effects. Like Henry said, that the black hole calculations, the island and the radiation are one system, seen in two places, which amounts to a failure of the concept of place. There's no such thing as everything together. We've always known that some kind of non-local effects have to be involved with gravity. And this is one of them, Bacharach said. Things you thought were independent are not really independent. Yes, they're connected. At first glance, this is very surprising. Einstein constructed general relativity with the express purpose of eliminating non-locality from physics. Gravity does not reach out across space instantly. It has to propagate from one place to another at finite speed, like any other interaction in nature. But over the decades, it has dawned on physicists that the symmetries on which relativity is based create a new breed of non-local effects. This past February, Norolf and Henry Maxfield also in Santa Barbara studied the non-locality implied by the new black hole calculations. They found that the symmetries of relativity have even more extensive effects than commonly supposed, which may give space-time the hollow rose quality seen in the black hole analyses. All this reinforces many physicists' hunch that space-time is not the root level of nature, but instead emerges from some underlying mechanism that is not spatial or temporal. Many, that was the main lesson of the ABS-CFT duality. The new calculations say much the same thing, but without committing to the duality or the string theory, or holographic. It is holographic principle all the way. Wormholes crop up because they are the only language the path integral can use to convey that space is breaking down. They are geometry's way of saying the universe is ultimately non-geometric. The end of the beginning. Physicists not involved in the work, or even in string theory, say they are impressed, if duly skeptical. Hats off to them, since those calculations are highly non-trivial, said Daniel already of the Ludwig Maximilian Institute of Munich. but some feel uneasy about the tottering pile of idealizations used in the analyses, such as the restriction of the universe to less than three spatial dimensions. Well, can't have everything. The previous wave of excitement over the past interval of the 80s, driven by Hawking's work, fizzled out, with project with theories for unearthing the accumulation of approximations. Are today's physicists falling into the same trap? I see people make the same hand-waving arguments that were made 30 years ago, said René Rowe of Radboud University in the Netherlands, an expert on the gravitational path integral. He has argued that wormholes need to be expressly forbidden if the integral is to get sensible results. Skeptics also worry that the authors have overinterpreted the replica trick. But supposing that replicas can be connected gravitationally, the authors go beyond past indications of the behavior. They are postulating that all geometries connecting different replicas are around, and it's not clear how that fits into the framework of quantum rules. Steve Giddings of Central Opera. Given the uncertainties of the calculation, some are unconvinced that a solution is available within semi-classical theory. There is no good choice if you restrict to quantum mechanics and gravity, Porter said. He has championed models in which stringy effects prevent black holes from forming in the first place. But the upshot is broadly similar. Space-time undergoes a phase transition to a very different structure. Skepticism is warranted if for no other reason than because the recent work is complicated and wrong. It will take time for physicists to digest it and either find the fatal flaw in the arguments or become convinced that they work. After all, even the physicists behind the effort still expect to resolve the information paradox without a full quantum theory of gravity. Indeed, they thought the paradox was their fulcrum for crying out that more detailed theory. If you had asked me 2 years ago, I would have said the page curve that's a long way away. I go hard so. We're going to need some kind of deeper understanding of quantum gravity. Okay, here are some of the research that went into this. But assuming that the new calculations stand up to scrutiny, do they in fact close the door on the black hole information paradox? The recent work shows exactly how to calculate the page curve, which in turn reveals that information gets out of black holes. So it would seem as though the information paradox has been overcome. The theory of black holes no longer contains the logical contradiction that makes it paradoxical. And in terms of making sense of black holes, this is at most the end of the beginning. Here we still haven't mapped the step-by-step process where that information gets out. You can now compute the page curve, and I don't know why, said Raphael Bosso at Berkeley. Astronauts who asked whether they could get out of a black hole, physicists could answer sure. When the astronauts asked how to do it, the describing reply will be no clue. Now to the research. The entropy of a bulk quantum field, or the entropy of bulk quantum fields is the entanglement wedge of an evaporating black hole. Bulk quantum fields are often said to be attribute the generalized entropy A over 4Gn plus asphalt only as O sub 1. Nonetheless, in the context of evaporating black holes, O1 divided by Gn gradients of asphalt can arise due to large boosts, including a quantum extremal surface far from any classical extremal surface. We examine the effect of such 12 quantum effects and quantum extremal surface QESs, and the resulting entanglement works in a simple two-boundary 2D bulk system defined by Jackie-Teitelbaum gravity coupled to a 1 plus 1 CFT. Turning on a coupling between one boundary and a further external auxiliary system which functions as a heat signal allows a two-sided, otherwise external black hole to evaporate on one side. We find a generalized entropy of the QES to behave as expected, from general considerations of unitarity and in particular that ingoing information disappears from the entanglement wedge. After a scattering time, beta over 2 pi, natural log delta S plus O sub 1, in accordance with expectations for holographic implementations of the Higgs-Presto protocol. We also find an interesting QES phase transition at what one might call the page time log process. That's the vertex of the inverted V. Okay, here's the next one. Islands and Schwarzschild black holes. We turn the page curve for asymptotically flat internal Schwarzschild black holes with 4 and higher space-time dimensions. Before the page time, the entanglement entropy goes linearly in time. After the page time, after the vertex of the inverted V, the entanglement entropy of a given region outside the black hole is largely modified by the emergence of an island, which extends to the outer vicinity of the event horizon. As a result, it remains a constant value which reproduces the Beckett-Steven quantum entropy. Consistent with the finiteness of the von Neumann entropy for internal black hole. Okay, so that region outside the black hole, the entanglement entropy there is constant. But inside the black hole it's less, because the particles inside the black hole no longer are part of the black hole since they could have developed on the quantum extremal surface. So that's the island of the radiation, but not part of the black hole. But not part of the entanglement entropy either. Ratio. Except that the outside remains constant, and the inside it gets less, and that effect is less. Forward more, where it was increasing in both places. Okay, here we go. Transcending the ensemble. Data universes, space-time wormholes, and the order and disorder of black hole information. In the 80s, work by Coleman and McGinnings and Schrödinger linked the physics of space-time wormholes to data universes and an ensemble of theories. We revisit such ideas with features associated with the negative cosmological constant, so it's anti-distance space, and asymptotically ADS boundaries, suspended the results. Introduce a change of perspective and connect with recent replica wormhole discussions of the page curve. A key new feature is an emphasis on the role of null states. We explore the structure and detail in simple topological models of the bulk that allow us to compute the full spectrum of associated boundary theories. The dimension of the asymptotically ADS Hilbert space turned out to become a random variable Z, whose value can be left with the naive number K of independent states in your theory. If K is greater than Z, the consistency arises from an exact degeneracy in the inner product defined by the gravitational path integral, so that many a priori independent states differ only by a null state. We argue that a similar property must hold in any consistent gravitational path integral. We also comment on other aspects of extrapolations to more complicated models and on possible implications For the black hole information problem, if the individual members of the above are problem. Okay. Alright, so let's get further into this. Okay, so there's actually more to this story. I'm gonna update in the next section, section 52. The reason being that I need to assess how much this information is due so that I can actually report on it. Okay, so black hole information paradox will continue in part 2. Okay, so we're going to now talk with one of the researchers who developed the new theory of resolving the black hole information paradox. This one is about Meta Engelhart, and there's an interesting avenue of new research that are going to go with this. So let's start at the beginning. In 1974, Stephen Hawking calculated that black holes sequence die with random quantum jitter on the spherical outer boundary, or event horizon. The black hole will cause the hole to radiate particles and slowly shrink to nothing. Any record of the star whose violent contraction formed the black hole, and whatever else got swallowed up after, then seemed to be permanently lost. Hawking's calculation posed a paradox, the infamous black hole information paradox, that has motivated research in fundamental physics ever since. On the one hand, quantum mechanics, the rule book for particles, says that information about particles' past states gets carried forward as we evolve. The bedrock principle called unitarity. When black holes take their cues from general relativity, the theory that states of time form a bending fabric and gravity is the fabric's curves. Hawking had tried to apply quantum mechanics to particles near a black hole's periphery, apply unitarity, break down. So, the evaporating black holes will destroy information. Even unitarity is not a true principle of nature. Nor does information escape from the black hole evaporates. Solving the information paradox quickly came to be seen as a route for discovering the true quantum theory of gravity. Its general relativity approximates well everywhere, except black holes. For the past 2 years, a network of quantum gravity theorists, mostly millennials, has made enormous progress on the Hawking's paradox. One of the leading researchers is Netta Engelhardt, a 32-year-old theoretical physicist at the Massachusetts Institute of Technology. She and her colleagues have completed a new calculation that corrects Hawking's 1974 formula. This indicates that information does in fact escape black holes via their radiation. She and Aaron Wall identified an invisible surface that lies inside a black hole's event horizon, called the quantum extremal surface. In 2019, Engelhardt and others showed that the surface keeps a cozy amount of information that has radiated away from the black hole, evolving over the hole's lifetime exactly as expected if information escapes. Engelhardt received a 2021 New Horizons in Physics Prize for calculating the quantum information content of a black hole and its radiation. Anna O'Leary of the Institute of Advanced Studies, a frequent collaborator, noted her deeply rooted intuition for the intricate workings of gravity, particularly the discovery of quantum extremal surfaces. Engelhardt set her sights on quantum gravity when she was 9 years old. She moved to Boston from Israel that year with the family, and not knowing any English, read every book in Hebrew she could find in her house. The last was Hawking's A Brief History of Time. What that book did for me was trigger a desire to understand the fundamental building blocks of the universe, she said. From then on, I was sort of finding my own way, watching different popular science videos and asking questions of anybody who might have the answers, and narrowing down what I wanted to work on. She ultimately found her way to Hawking's paradox. The Quantum magazine caught up with Engelhardt in a recent video call. She emphasized that the full solution to the paradox and the quantum theory of gravity is a work in progress. We discussed that progress, which centrally involves the concept of entropy and the search for a reverse algorithm that would allow someone to reconstruct a black hole's past. The conversation has been condensed and edited for clarity. Would you say that you and your colleagues have solved the black hole information paradox? Not yet. We've made a lot of progress towards a resolution. That's part of what makes the field so exciting. We're moving forward, and we're not doing it so slowly either. But there's still a lot that we have to uncover and understand. Could you summarize what you have figured out so far? Certainly. Along the way, there have been a number of very important developments. One I will mention is the 1993 paper by Don Page. Page said, suppose that information is conserved. Then the entropy of everything outside of a black hole starts out at some value, increases, and has to go back down to the original value once the black hole has evaporated altogether. Whereas Hawking's calculation predicts that the entropy increases, and once the black hole is evaporated completely, it just plateaus at some value, and that's it. The Page curve. When a black hole releases radiation, the radiation of the black hole should be quantum mechanically linked, entangled. The total amount of connection is called the entanglement entropy. According to Stephen Hawking's original calculations, this quantity keeps rising until the black hole dies. But if the information gets out, the entanglement entropy should instead follow the Page curve, which is the inverted V. So the question became, which entropy curve is right? Normally, entropy is a number of possible or distinguishable configurations of a system. What's the best way to understand entropy in this black hole context? can think of this entropy as ignorance of the state of affairs in the black hole interior. The more possibilities there are for what could be going on in the black hole interior, the more ignorant you will be about which configuration this system is in. So this entropy measures ignorance. Page's discovery was that if you assume that the evolution of the universe doesn't lose information, then if you start out with zero ignorance about the universe before a black hole forms, eventually you're going to end up with zero ignorance once the black hole is gone. Since all the information that went in has come back out. In conflict with what Hawking derived, which will then eventually end up with ignorance. So, information level entropy. The peak of the entropy curve is also the beta of the information curve. In other words, you start out with maximum information and you end up with maximum information with a minimum in between, which is the inverted V. So the inverted V for entropy would actually be the actual V for information. You characterize Page's insight and all other work on the information paradox prior to 2019 as understanding the problem better. What happened in 2019? The activity that started in 2019 is a step towards actually resolving the problem. The two papers that kicked this off were work by myself, Ahmed Almiri, Don Morrow, and Henry Maxfield, and in parallel, the second paper, which came out at the same time, by Jeff Pennington. We submitted our papers on the same day and coordinated because we knew we were both on to the same thing. The idea was to calculate the entropy in a different way. This is where Don Page's calculation is very important for us. If we use Hawking's method ending assumptions, we get a formula for the entropy which is not consistent with unitarity. And then we want to understand how we could possibly do a calculation that would give us the curve of the entropy that Page proposed, which goes up and then comes back down. And for this, we relied on a proposal that Alan Wall and I gave in 2014, the quantum extremal surface proposal, which essentially states that the so-called quantum corrected area of a certain surface inside the black hole is what contributes and what computes the entropy. We said that maybe that's a way to do the quantum gravity calculation that gives us a unitary result. And I will say it was a shot in the dark. Sometimes the bad shots are. When did you realize that it worked? This entire time is a bit of a day of my life. It was so exciting. I think I slept maybe 2 hours a night for weeks. The calculation came together over a period of 3 weeks. I want to say, I was at Princeton at the time. We had a meeting on campus. We had just had a meeting on campus. I have a very distinct memory of driving home, and I was thinking to myself, wow, this could be it. The crux of the matter was, there's more than one quantum extremal surface in the problem. There's one quantum extremal surface that gives you the wrong answer, the Hawking answer. To correctly calculate the entropy, you have to pick the right one. And the right one is the one with the smallest quantum corrected area. It's always the one with the smallest quantum corrected area. And so, what was really exciting, I think the moment we realized this might really actually work out, is when we found out exactly at the time that the entropy curve needs to turn over. Go from increasing entropy to decreasing, the other side of the inverted V. Here's a jump. At that time, the quantum extremal surface with the smallest quantum corrected area goes from being the surface that would give you Hawking's answer to a new and unexpected one. And that one we reduce with the Page curve. What are these quantum extremal surfaces exactly? Let me try to intuit a little bit what a classical non-quantum extremal surface feels like. Let me begin with just a sphere. Imagine that you place a light bulb inside of it, and you follow the light rays as they move outward through the sphere. As the light rays get further and further away from the light bulb, the area of the spheres that they pass, we will be getting larger and larger. We say that the cross-sectional area of the light rays is getting larger. That's an intuition that works really well in approximately flat space where we live. But when you consider very curved space, time like you find inside a black hole, what can happen is that even though you're firing your light rays outward from the light bulb and you're looking at spheres that are progressively further away from the light bulb, the cross-sectional area is actually shrinking. Oh, that's because we know with gravity. And this is because space-time is very violently curved. So more curved the further away you get. It's something that we call focusing of light rays, and it's a very fundamental concept in gravity and general relativity. The extremal surface saddles this line between a very violent situation where the area is decreasing and a normal situation where the area is increasing. Oh, it's like a phase transition. The area of the surface is neither increasing nor decreasing, so intuitively you can think of an extremal surface as kind of like right at the cusp where you would expect strong curvature to start kicking in. A quantum extremal surface is the same idea. But instead of area, now you're looking at quantum corrected area. This is a set of area of entropy, which is either increasing or decreasing. What What does the quantum extremely surface mean? What's the difference between things that are inside versus outside? Recall that when the page curve turns over, we expect that our ignorance of what the black hole contains starts to decrease, as we have access to more and more of its radiation. So the radiation emitted by the hole will start to learn about the black hole interior. Quantum extremely surface that divides the space-time into everything inside the surface, the radiation can already decode. Oh, because it's already entangled. Not part of the hole anymore. Everything outside of it is what remains hidden in the black hole system. What's not contained in the information of the radiation. So everything inside the quantum extremely surface is already been decoded because it's already entangled with the radiation outside. Everything inside, or everything outside, has not yet been entangled with the radiation outside, so it's still hidden. So it's the inside stuff that's entangled, the outside stuff that's not. As the black hole emits more radiation, the quantum extremely surface moves outward and encompasses an ever larger volume of the black hole interior. By the time the black hole evaporates altogether, the radiation has been able to decode everything that way. So the quantum extremely surface is getting larger and moving outward towards the event horizon. By the time the black hole evaporates, they are one and the same, and all the information has been decoded and entangled. The black hole is not entangled in the cloud, but all the information is already decoded. Now we have an explicit calculation that gives us a unitary answer. That gives us so many tools to start asking questions that we could never ask before. Like, where does this formula come from? What does it mean about what type of theory quantum gravity is? Also, what is the mechanism in quantum gravity that restores unitarity? It has something to do with the quantum extremely surface formula. Most of the justification for the quantum extremely surface formula comes from studying black holes in anti-de Sitter space, ADS, saddle-shaped space with an outer boundary, whereas our universe has approximately flat space, that no boundary, or so we think. Why should we think that these calculations apply to our universe? First, we can't really get around the fact that our universe contains both quantum mechanics and gravity. It contains black holes. So our understanding of the universe is going to be incomplete until we have a description of what happens inside a black hole. The information problem is such a difficult problem to solve that any progress, whether it's in a toy model or not, we make progress is making progress towards understanding phenomena that happen in our universe. Now, at a more technical level, quantum extreme surfaces can be computed in different kinds of spacetime. Including flat space like in our universe. And in fact, there already have been papers written on the behavior of quantum extreme surfaces within different kinds of spacetimes and what types of entropy codes they would give rise to. We have a very firm interpretation of the quantum extreme surfaces in ADS space. We can extrapolate and say that in flat space there exists some interpretation of the quantum extreme surface which is analogous, and I think that's probably true. It has many nice properties and looks like it's the right thing. We get really interesting behavior, and we expect to get unitarity as well. So yes, we do expect that this phenomenon does translate, although the interpretation is going to be harder. You said at the beginning of our conversation that we don't know the solution to the information paradox yet. Can you explain what a solution looks like? A full resolution of the information paradox would have to tell us exactly how the black hole information comes out. If I'm an observer that's sitting outside of a black hole and I have extremely sophisticated technology at all the time in the world, a quantum computer taking incredibly sophisticated measurements. All the radiation of the black hole. What does it take for me to actually decode the radiation to reconstruct, for instance, the star that collapsed and formed the black hole? What process do I need to put my quantum computer through? We need to answer that question. So you want to find the reverse algorithm that unscrambles the information in the radiation. What's the connection between that algorithm and quantum gravity? This algorithm that decodes the Hawking radiation is coming from the process in which quantum gravity encodes the radiation as it evaporates at the black hole horizon. The emergence of the black hole interior from quantum gravity and the dynamics from the black hole interior. The experience of an object that falls into the black hole. All of that is encoded in this reverse algorithm that quantum gravity has to spit out. All of those are tied up in the question of how does the information get encoded in the Hawking radiation. You've lately been writing papers about something called a Python bunch. What's that? It's one thing to ask, how can you decode the Hawking radiation? You also might ask, how complex is the task of decoding the Hawking's radiation? And as it turns out, extremely complex. So maybe the difference between Hawking's calculation and the quantum extreme surface calculation that gives unitarity is that Hawking's calculation is just dropping the high complexity operations. To understand the complexity geometrically. And in 2019, there was a paper by some of my colleagues that proposed that whenever you have more than one quantum extremal surface, the one that would be wrong for the entropy can be used to calculate the complexity of decoding the black hole radiation. Why that's the way the Hawking calculates. That keeps going higher. The two quantum extremal surfaces can be thought of as a sort of constrictions in the space-time geometry. And those of us who have read the complete text of an could see an elephant inside a python, and so it became known as a python sludge. Although python can't eat an elephant, but that's the way about it. We propose that multiple quantum extremal surfaces are the exclusive source of high complexity. And these two papers that you're referring to are essentially an argument for the strong Python wedge proposal. That is very insightful for us because it identifies the part of geometry that Hawking's calculation knows about, and part of the geometry that Hawking's calculation doesn't know about. It's working towards putting his and our calculations in the same language, so that we know why one is right and the other is wrong. Where would you say we currently stand in our effort to understand the nature of quantum gravity, the quantum nature of gravity? I like to think of this as a puzzle where we have all the edge pieces and we're missing the center. We have many different insights about quantum gravity. There are many ways in which people are trying to understand it. Some by constraining it, what are things that it can't do, some by trying to construct aspects of it, things that it must do. My personal preferred approach is more to do with the information paradox, because it's so pivotal. It's such an acute problem. It's clearly telling us, here's where you messed up. And to me that says, here's a place where we can begin to fix our pillars, one of which must be wrong, of our understanding of quantum gravity. So that's that. And I'm going to go through the three research papers that disagree. Entanglement wedge reconstruction of the information paradox. When observing boundary conditions are used to evaporate a black hole with ADS-CFT, we show that there is a phase transition at the location of the quantum Taglioni surface. That would be inverted. The vertex would be inverted B. At precisely the page time. The new RT surface lies slightly inside the event horizon of the quantum scalar surface. At the infalling time, approximately the scrambling time, theta divided by 2 pi longer than S BH black hole into the past, size of the black hole. We can immediately derive the page curve using the Y times Leakey formula and the Hayden-Presto decoding criterion using entanglement wedge reconstruction. Because part of the interior is now encoded in the early Hawking radiation. The decreasing entanglement entropy of the black hole is exactly consistent with the semi-classical bulk entanglement of the late-time Hawking modes, despite the absence of a firewall. By studying the entanglement wedge of highly mixed states, we can understand the state dependence of the interior reconstructions. A crucial role is played by the existence of tiny, non-perturbable errors in entanglement wedge reconstruction. Directly after the page time, interior operators can only be reconstructed from the Hawking radiation if the initial state of the black hole is known. As the black hole continues to evaporate, reconstructions become possible that simultaneously work for a large class of initial states. And that's where the curve is going down. And it should be going down, information going down. Using similar techniques, we generalize Hayden-Presto to show how the amount of Hawking radiation required to construct a large diary thrown into the black hole depends on both the energy and the entropy of the diary. Finally, we argue that before the evaporation begins, a single independent interior reconstruction exists. Single state independent interior reconstruction exists for any cone space or microstates, with entropy strictly less than the Bekenstein Hawking entropy. And shown that this is sufficient state dependence to avoid the ANPSS typical state firewall paradox. The Python's lunch. Geometric obstructions to decoding Hawking's radiation. According to Harlow and Hayden, the task of distilling information out of Hawking radiation appears to be computationally hard, despite the fact that the quantum state of the black hole and its radiation is relatively uncomplex. We trace this computational difficulty to geometric obstruction. The Einstein-Rosenberg wormhole connecting the black hole and its radiation. inspired by tensor network models routing it. We conjecture a precise formula relating the computational hardness of distilling information to geometric properties of the wormhole, specifically to the exponential of the difference in generalized entropies between the two non-minimal quantum extreme surfaces that constitute the obstruction of two non-minimal quantum extreme surfaces. Due to its shape, we call this obstruction the Python lunch, an analogy to the reptile's postprandial bulge. Basically, there are two quantum extreme surfaces, the Hawking one, the page one which is for the entropy, the Hawking one which measures the difficulty of the computation, and the wormhole connection between the particles on the inside of the black hole versus the Hawking radiation of the black hole together. Alright, here's the last one. Finding pythons in unexpected places. We argue that novel, highly non-classical quantum extremal surfaces play a crucial role in reconstructing the black hole interior, even for isolated, single-sided, non-evaporating black holes. That is, with no auxiliary reservoir. Specifically, any cone subspace, the interior outgoing the modes can be excited. Will have a quantum extremal surface in its maximally mixed state. We argue that as a result, reconstruction of interior outgoing modes is always exponentially complex. Our construction provides evidence in favor of a strong Python lunch proposal that non-minimal quantum extremal surfaces have the exclusive source of exponential complexity in the holographic dictionary. The Hawking quantum extremal surface. Minimal. The other one's a bit more painful. We also comment on the relevance of these quantum extremal surfaces to the geometrization of state dependence and the typicality arguments for firewalls. Okay. And those are the three papers. Alright. So, that's part 52. There's probably some more that I need to add. I'll do that a little bit later. But we digest all this magnificent new information about the black hole information paradox being close to being solved, and all the attendant discoveries in quantum gravity. This is a great time to be learning these things as new discoveries are being made quickly and clearly. Okay, I will see you later. This is part 52 of Origin SE. Okay, this is part 53. We're continuing with the black hole information paradox being resolved. We're close to that. Very interesting. When cosmic hard drives, black holes have trillions of data into compact spaces. But Emerson Stephen Hawking calculated in 1974 that the dense meters of extreme gravity give off heat and fade away. Fade and their stored information as quantum physicists. The problem is that The laws of quantum mechanics insist that information about the past is never lost, including the record of whatever fell into a black hole. But Hawking's calculation contradicted this. He applied both quantum mechanics and Albert Einstein's theory of gravity, the space around the black hole, and found that quantum jitters cause the black hole to emit radiation that's perfectly random. As this happens, the black hole shrinks and eventually disappears. So does all the information apparently. But does this information disappear with it? Maybe quantum mechanics is wrong, or does the problem lie with Einstein's theory? Or Hawking's theory? Of course, choose many physicists back in the quantum world and suspect that information somehow escapes in the black hole's radiation, which in that case isn't random after all. Figuring out how the information gets out should point the way past Einstein's theory to a more complete quantum theory of gravity. Yet after 45 years of grappling with this black hole information paradox, no one has confronted the alleged misstep of Hawking's calculation. Now, though, several noted black hole physicists think they may be closing in on the solution. Not even the researchers themselves fully grasp the physical implication of the math they explore in a recent paper. But in the abstract mathematical thread, they and others see the outlines of a bridge, the black hole's interior, and a escape route for traveling. They locate this hidden path using an imperfectly understood technique for spying on a black hole in a higher dimension. Reversible results. It's magic, said Albert Almir, a physicist at the Institute of Advanced Study at Princeton University, who co-authored the recent paper. We know how to prove that the shift in perspective works, he said. But we don't have a complete understanding of why this is happening. Holography. Holographic principle. Rafael Bosa, a physicist at the University of California, Berkeley, and an expert on the information paradox, studying the new work. I find it interesting enough that I'm working really hard to understand. The dimension hopping technique that's key to the new development is known as holography. Just like a credit card hologram that pops out from a spot sticker, a system like a black hole can be viewed in two equivalent ways. There is a familiar view of a black hole as a volume of space, in which gravity is so strong and the fabric of space-time bends so steeply inward that not even light can climb. Alternatively, the black hole can be thought of as a holographic projection from a flat system of quantum particles that remain gravity-free. Following the discovery of this duality by Juan Malvicina, physicists at IAS in 1997, physicists have peered at many mysteries from these complementary angles. They're now using the holographic approach to try and track the flow of information through a black hole. First, all papers that appear in the analyze how black holes' information content changes as the object ages. In one of the papers, Almieri and co-authors considered a simplified gravitational black hole. Two-dimensional. That's equivalent to a one-dimensional system of quantum particles. We found that at first, as the black hole gobbles up matter and gets bigger, its information content increases. But then, in its old age, and radiation starts spitting data back out, its information content decreases. Diverging from Hawking's description. The inverted V. Jeffrey Pennington of Stanford intimately came to similar conclusions. We first found a new way to reproduce ultimate wisdom that information should safely escape black holes. But to stop short of explaining how it does so, or where Hawking's math went wrong. The latest paper posted online in late August went further, offering a new way to think about Hawking's math. Along first usually walked out a one-way street from a gravity-filled volume to a quantum flatland, where the math is easier. But in this new work, Almieri, Malvicina, and their IAS collaborators Raghu Maharaj and Ying Zhao tried exploring both ways. So, gravity to quantum and from quantum back to gravity. They took a 2D black hole and separately considered its two elements, the matter inside it and the gravity produced by that matter. As before, we viewed the 2D gravity as a hologram of 1D quantum particles. Holographic principle. But they treated the black hole's matter like the flat part of a second hologram, letting these 2D quantum particles pop into a 3D image. So basically going from 2D to 1D on one hand with gravity, and with the particles going from 2D to 3D, the other direction. This strategy created inception-like hologram within a hologram. Look like one black hole within the other black hole. Basically, these are quantumly connected. This is like the boundary of another universe to a 3D universe. So we got this 2D universe sandwich between a 1D and a 3D hologram. Okay. Seemed like it was a real crazy thing, Albert said. But we took a chance. While information appeared trapped in the black hole's interior in 2D, the researchers found that after the hologram popped off the page, portions of the black hole interior became geometrically linked portions of the exterior. Finally, improved for information. This is more well identified. Contemplating outgoing black hole radiation, they was random with passive astronauts, doing simple experiments. Albert said the study would reveal some latent information. The outcome many have been hoping for. The holographic connection between the black hole's interior and the exterior, according to old Hutch, when considering the two together, should somehow resolve the information paradox. They are providing very significant new evidence in favor of that rule pending consent. But experts stress that while the high-dimensional bridge, the wormhole, may let the information out, the detailed account of how it is encoded in the radiation is still lacking. This is the beginning of a theoretical understanding of what's going on in terms of radiation, said Ben Engelhardt, physicist at MIT, who worked with Algeria in the main publication. But it's not an operational description for how to extract the information. The 3D view also helps clarify why 2D black holes eventually diverge from Hawking's calculation. The theorists trace the changes in the information context of the black hole by measuring the areas of related geometric surfaces in the 3D hologram. The area of the smallest subsurface gives the information content. QGS, the inner QGS. But as this surface grows, the secondary one eventually replaces it. That's the smallest. Oh, this is not the information. This is the Hawking QGS. The second one, the smallest one, is the page QGS. Continuing to track the first surface reproduces Hawking's error. But switching to the second one corrects the math and showing that the information contained in the black hole starts to drop. So that seems what it is. So the first surface, the bigger one, is the one that shows how complex decoding. The second surface is the boundary between the radiation that's already been converted and what's yet left to convert. The whole particles that have been converted to radiation, what's left to convert. That's the smaller. And what's that one coincides with the event horizon. The black hole has evaporated completely and all the information is out. It converts to radiation. All the particles have been converted to radiation, all the information is out. But this way, the hologram within a hologram gives the desired answer. The question of what happens to a 2D black hole's information. Most experts assume that if the reasoning is correct, it should carry over to higher dimensional black holes like those in our universe. A common concern, however, is that the authors might be reading too much meaning into this abstract calculation. John Baralt, a physicist at the University of California, said the farmer who worked on the strict paper with Almiri Engelhardt and Henry Maxfield praised the new work as a concrete model demonstrating the earlier paper's claims. However, Baralt wonders that holography may not be a why the guide as Almiri and Malvicino hope. It's possible to hop between dimensions on many different paths. Many different worlds. The route found in the new paper seems to work, but there are also cautions that other holographic constructions might disagree. For this reason, he said, we'd all like to be able to do something intrinsic to the 3D theory without invoking holography as a magic black box. Indeed, in ongoing work, Almiri's team and a number of other groups are pursuing a more grounded description that they hope will reach the same conclusions as the hologram proved without leaning on the crutch of the extra dimension. Even if the fancy holography trick don't stand, black hole researchers express excitement that Hawking's information paradox is able to transport them to the boundaries of known physics, literally. That says here be dragons, the quantum gravity theory that we're searching for, dragons are a lot closer than we thought. Okay, so let me read this one piece of research to begin with this. Page curve of Hawking radiation from semi-classical gravity. Page curve of Hawking radiation from semi-classical geometry. We consider a gravity theory coupled to matter, where matter has a higher dimensional holographic tool. In such a theory, finding quantum extremal surfaces becomes equivalent to finding the RT divided by HRT surfaces in the higher dimensional theory. Using this, we can see the ecstasy of Hawking radiation and argue that it follows the page curve, as this for recent computations of the entropy and entanglement wedges of the old black holes. The higher dimensional geometry connects the radiation to the black hole theory. Instead of ER equals EPR. There we go. Holographic theory. the black hole interior then becomes part of the entanglement wedge of the radiation. Inspired by this, he proposed a new rule for computing the entropy of quantum systems entangled with gravitational systems, which involves searching for islands in determining the entanglement wedge. Okay. Okay, so this will be continued in part 54 or 48. Set it up for now. I'll be back in a little bit for part 54. Very interesting. So now we're talking about string theory of black holes and a strange superconductor. Part 54. Origin and see. Strange properties of superconducting materials are complex. Bismuth, strontium, calcium, copper oxide is shown here, which cannot be described by known quantum mechanical methods. They correspond to properties of black holes in higher dimensions. According to modern quantum theory, energy fields permeate the universe. And points of energy in these fields, called particles, when they are plate-like, and waves when they are diffused. So, as the building blocks of matter and forces. What new findings suggest is the wave particle picture, although it's only a superficial view of nature's constituents. Each energy field pervading space is thought of as the surface of a pond, and waves of particles are the turbulence on that surface. And the new evidence strengthens the argument that a vibrant hidden world lies beneath. For decades, surface level description of the subatomic world has been sufficient to make accurate calculations about most physical phenomena. recently a great class of matter that defies description by known quantum mechanical methods, as well as physicists into the depths below. I've grown up as a physicist, just living on that flatland, in a 2D space. A super academic physics professor at Harvard University who studied these strange forms of matter. There was a whole new dimension to explore, he said, and you could think of the particles as just ending on that surface. All the strange forms of matter, cuprates, copper, including metals, and exhibit a property called high temperature superconductivity, may be the strangest. In a new research published online June 24th, in the Journal of High Energy Physics, physicists at the University of California, Santa Barbara, explored the future phenomena that they claim are connected to the perplexing surface level behavior of cuprates. By focusing their calculations on the underlying environment, the researchers derived a formula for the conductivity of cuprates that was previously known only from experiments. The amazing thing is that you start with the theory, and out you get the conductivity of these strange superconductors. You're not involved with the work. The results demonstrate the evidence of the new way of looking at nature's building blocks is real and that it is strikingly literal. And again, that is a theorem of physicists at Leiden University, full of the Netherlands. Therefore, the results could be seen as an unusual indirect kind of evidence for string theory, according to the frameworks that weaves together quantum mechanics and gravity. It is mathematically elegant or profoundly explanatory, as it is unproven. It is really questioned about the nature of dark matter, the mysterious substance thought to constitute 84% of the mass of the universe. Search for a theory of everything that mathematically describes all of nature. Researchers say the findings could have sweeping implications. There is a realistic chance that we will make enormous progress in fundamental physics in the next couple of years at it. So it's moving very, very quickly. Below the surface, its waves of particles are like the turbulence on the surface of a pond. The connection between that turbulence and events in the interior of the pod were first described by a mathematical principle discovered in 1997 in a landmark paper, Juan Bautista, the physicist at Harvard University now Institute for Advanced Studies showed that events take place in a 3D region of space mathematically corresponds to very different events taking place on that region's 2D boundary. Events in 4D also correspond to events in 3D, 5D to 4D, and so on. So basically, B equals B plus 1. Consider the 3D interior and 2D surface of the metaphoric pod. For the correspondence to work, the interior must be mathematically described on string theory, in which electrons, photons, gravitons, and the rest of nature's building blocks are invisibly one-dimensional lines or strings. We take from 3 to 2 and now we're going to 1. Mass and other macroscopic properties correspond to the string vibrations. The interactions between different kinds of matter and forces come from the way strings split and connect. The strings live inside the pod. Now imagine that the 2D surface of the pod is described by quantum mechanics. So string theory, the 3D and 2D is quantum mechanics. Particles are the splashes on the surface and waves are the cascading ripples from those splashes. On the surface of this imaginary pod, there is no gravity. Gravity of 0 degrees of freedom. Falmousy's discovery, known as the holographic duality, showed that events in the interior region involve gravity and are described by string theory are mathematically translatable to events on the surface, or gravity-free and described by quantum particle theory. Holographic duality discovered in 1997 by Juan Balmaceda says that events inside a region of space that involve gravity and are described by string theory are mathematically equivalent to events on the surface of that region that involve particles that are gravity-free and are described by quantum mechanics. To understand this relationship, the crucial aspect is where the gravity theory is easy, when the gravity theory is easy to analyze. To understand this relationship, the crucial aspect is when the gravity theory is easy to analyze, so the particles of the boundary, the planet analogy on the surface, they're actually very strongly with each other. Well, let's do this next. Easy to analyze for the particle patrolling the surface. The converse is also true. When the particles are calm on the surface, they not move much, as they are in most forms of matter. But in the situation with the pod, picture work is extremely complicated. Okay, so there's one dominant force out there. The contrast is what makes the ground useful, as one goes higher, the other gets lower, and vice versa. The stage class of materials that includes the couplings belongs in the first category. Oh. So that is simple inside, extremely complex outside. Experiments suggest that particles in these materials interact so strongly with one another that they lose their individuality. So, comment the surface, strongly agrees. So, it is strongly at the surface and calm underneath. They lost their individuality. Physicists say the particles are strongly correlated. The wavy ripples corresponding to each overlap. Wavy ripples corresponding to each overlap so much that a kind of swarm effect is believed to occur. Strongly correlated matter can behave in diverse and unexpected ways that are difficult or in some cases impossible to describe with known quantum mechanical methods, says Sean Hartnell, a physics professor at Stanford. You need a different way of looking at them than starting from single particle descriptions. He said, you don't try to explain the ocean in terms of individual water molecules. Honestly, there's building blocks to the world. The strongly correlated matter is thought of as living on the 2D surface of a pond. The holographic duality suggests that the extreme turbulence on that surface is mathematically equivalent to still water at the interior. Okay, so extremely on the surface, still underneath the interior. The opposite of how it normally is. Physicists can get surface level behavior by studying the parallel, but much simpler situation law. You can compute things in that tranquil world, David said. But the mathematical components of the holographic duality, certain strongly correlated matter in 2D corresponds in 3D to a black hole. An infinitely dense object with an inescapable gravitational pull which is mathematically simple. Okay, not simple on the bottom, but still destructive. It doesn't destroy information. It converts it to another form. Phase transition. These very complicated quantum mechanical collective effects are beautifully captured by black hole physics. But getting yet, said Hoglu, an associate professor of physics at MIT. For strongly correlated systems, if you put an electron into the system, it will immediately disappear. You can no longer track it. It's like an object falling into a black hole. So, if a strongly correlated at the surface, the electron will come. Superconductive model. Increasingly over the past decade, studied the black hole equivalents of strongly correlated forms of matter have yielded groundbreaking results, such as a new equation for the viscosity of strongly interacting fluids. And a better graph of interactions between quarks and gluons, which are particles found in the nuclei of atoms. Which form the protons and neutrons. Now, Gary Horowitz, theorist at UC Santa Barbara, and George Satchels, a postdoctoral researcher at Horowitz's group, have applied the holographic duality to couplings. They derived a formula for the conductivity of the metals, which are approximately 2D. Studying related properties of what may be their counterpart in 3D, an electrically charged, peculiarly shaped black hole. A model of strange materials called couplings and peculiarly shaped black holes in higher dimensions. The work of numerical virtuosity. A coupling swarm of strongly correlated electrons used to affix lattice of atoms. Modeling the metals with the holographic duality therefore required working the equivalent of a lattice with the structure of the corresponding black hole. By giving it a corrugated outer surface or horizon. But it comes to playing ball with black holes, you need Gary Harowitz. We created a formula for the conductivity of couplings. Horowitz and Santos had to study how light would interact with the complicated horizon of the black hole. The equations were too thorny to solve exactly, so they found approximate solutions using a computer. In their first paper, detailing this approach, co-authors at Cambridge University physics professor David Thomas published in July 2012 Journal of High Energy Physics. We derived a formula that matched the conductivity of couplings at high temperatures in response to an alternating current. In the new work, we extended the calculation down to the temperature range in which couplings become superconductive, or conduct electricity with low resistance, but again found a close match with experimental measurements of real couplings. The amazing being that the simple gravity model is able to reproduce any feature of a real material. Horowitz said, so this is encouraging us to think harder. The accuracy of Horowitz's Santos method breaks down in some significant cases. But that's for alternating currents at extremely high frequencies. One version. But Shane said that considering how simple the coordinated black hole model is, couldn't have worked any better. The fact is that considering how simple the corrugated black hole model is, it couldn't have worked any better. Incorporating more of the microscopic details of couplings into the structure of the black hole will probably deepen their congruence as well, he said. Hartnell, who recently used holographic duality to model metal, insulator transitions. Base voltage. In strongly correlated materials, hopes to build on the results by solving Horowitz Santos equations exactly. They have an input and an output. We'd like to decompress it and understand the critical steps in between. He said, doing so would reveal where the conductivity formula originates in the black hole environment, providing more insight about the corresponding forces at play inside couplings. A new duality. Understanding the physics of couplings could have an important practical application. Most metals start to superconduct when their temperature drops close to absolute zero. But for some reason not completely understood, couplings exhibit superconductivity at much more accessible temperatures. Making them useful for devices ranging from high-power electrical cables to ship propulsion motors. Couplings are brittle and expensive. However, engineering better versions by tweaking their properties could lead to dramatic improvements in a range of technologies. Medically levitating vehicles, timeline, and other devices to more efficient power grids. Very important. There's also the potential for advancing fundamental physics. If the holographic duality yields increasingly accurate predictions about the behavior of couplings and other strongly correlated materials, these materials can be conceived and essentially be black holes in higher dimensions. If we had a model which reproduced all the features of a material, it could be viewed as a theory of it. A very unusual kind of theory, full of information. But given the duality, it's equivalent to any theory you would produce on the boundary with the usual particles. And it might just be a lot simpler using on the boundary for the Horowitz. Holographic duality echoes the wave-particle duality that led to the development of quantum mechanics. In the early 1900s, light, which was previously thought to be a wave, seemed perplexing in some experiments unless it was treated as particles. And electrons thought to be particles sometimes didn't make sense unless they were conceived as waves. Wave-particle duality was what first proposed a big surprise, because these were two seemingly different concepts, and we learned that they are the same thing. Oh, what's up? The holographic duality is more sophisticated, but it has that same feature, he said. You have two very different seeming objects, boundary and bulk, that turned out to be completely equivalent. Either rendered surface or horizon of a black hole that was used to do research as a model for materials or a model of materials called couplings. The observations of the horizon correspond to the periodic lattice of atoms inside couplings. But how does the holographic duality factor into our understanding of nature? Are the one-dimensional strings in the pod analogy real? Not necessarily, so to say. In fact, the strings that were factored into Horowitz and Santos' calculations of the properties of the black hole they used as a model of couplings. But the findings do give physicists a sense that all these theories that we thought were different are actually all related. Alcacino said. It shows that string theory is not disconnected from the rest of physics. String theory may simply be the best mathematical language for grappling with certain aspects of reality. The physicist interviewed for this article said. Physics was traditionally reductionist. It wants to treat something complicated and find out what the building blocks are. I'll explain. The point is, there is not a unique way to do that. In some cases, electrons can be the building blocks, but in others, the collective excitations of electrons are playing a more fundamental role in every of the individual electrons. We are trying to find the right building block to describe these strange phases of matter, he said. And they might be strings in one higher dimension. as physicists interpret what it means that particles in a strange brittle metal mathematically correspond to strings of a peculiar black hole that exists, at least theoretically, in a higher dimension. The holographic duality enables them to think differently about the mysteries and the laboratories that etc. But perhaps it's not only about thinking differently, it's about seeing the real, beautiful facts. Wow, that was pretty good. Okay, so that was... How many did I get? I think I did 4. 1, 2, 3, 4. Yeah. 1, 2, 3, 4. Okay. Alright, so 4, so it's not 54. And we're going to continue to our letter page today. So part 55, our Bible part 4, over and out. Hi all. So last night we covered that the black hole information paradox is just about solved. And the way it was solved was by an ingenious group of researchers at MIT and at Stanford. What we did was show that the inside of a black hole actually divides into 2 parts. And that second part, the quantum extremal surface, takes the information of particles in the black hole and converts it to information which then gets transferred outside as radiation, out of which the encrypted information can be built up back to what originally fell into the black hole. There's actually 2 of these QESs inside the black hole. One is the traditional Hawking one, which is the original one, which does not solve for the amount of entropy in the system, but what it does show is how difficult it is to construct what's into the black hole back to its original form, with decrypting the information. The second one that has the page curve, the upside down V, that shows us the actual entropy graph. It is like where the entropy goes up to the midpoint of the life of the black hole, and then it goes back down again. And the information is restored back to its original form when the black hole dies. That's when the page coincides with the event horizon of the black hole, because that's the one that's slowly growing, reaching out towards the horizon. And once it coincides with it, that's the end of the life of the black hole, and all the information that fell in from the very beginning to the black hole's death is restored once again. As long as you can decrypt that information, and for that you use the quantum. Okay, so now we are going to talk about one last quest for space-time out of quantum particles. For over 2 decades, physicists have pondered how the fabric of space-time may emerge from some kind of quantum entanglement. Stanford University experiment is quantum particles entangled in a tree-like structure correspond to various configurations of space-time. The prospects for directly testing a theory of quantum gravity are poor, to put it mildly. To build the ultra-fine Planck scale, where quantum gravitational effects appear, you would need a particle accelerator as big as the Milky Way galaxy. Likewise, black holes hold singularities that are governed by quantum gravity, but no black holes are particularly close by. And even if they were, we could never hope to see what's inside. Quantum gravity was also at work in the first moments of the Big Bang. Direct signals from that era are long gone, leaving us to decipher subtle clues that first appeared hundreds of thousands of years later. But in a small lab, just outside Palo Alto, the Stanford University professor Monica Schuyler-Smith and her team are trying a different way to test quantum gravity, without black holes or galaxy-sized particle accelerators. Physicists have been suggesting for over a decade that gravity, and even space-time itself, may emerge from a strange quantum connection called entanglement. Schuyler-Smith and her collaborators are reverse engineering the process. By engineering highly entangled quantum systems, in a tabletop experiment, Schuyler-Smith hopes to produce something that looks and acts like the warped space-time predicted by Albert Einstein's theory of general relativity. In a paper posted in June, their team announced their first experimental step along this route. A system of atoms trapped by light, with connections made to order. Finely controlled with magnetic fields. When tuned in the right way, long-distance correlations in this system describe a tree-like geometry, similar to one seen in simple models of emergent space-time. Schuyler-Smith and her colleagues hopes to build on this work, the analogs to more complex geometries, including those of black holes. In the absence of new data from particle physics or cosmology, data that shows that could continue indefinitely, this can be the most promising route for putting the latest ideas about quantum gravity to the test. Carol with perfect predictions. For 5 decades, the prevailing theory of particle physics, the standard model, is that with almost nothing, to the endless frustration of particle physicists. The problem lies in the fact that the standard model, despite its success, is clearly incomplete. It doesn't include gravity, despite the long search for a theory of quantum gravity to replace general relativity. Nor can it explain dark matter or dark energy, which account for 95% of all the stuff in the universe. The standard model also has trouble with the fact that neutrinos have mass. Solar particle physics phenomenon it has failed to predict. Moreover, the standard model itself dictates that beyond a certain threshold of high energy, when closely related to the Planck scale, it almost certainly fails. Physicists are desperate for puzzling experimental data that might help to guide them as they build the standard model's replacement. String theory is still the leading candidate to replace the standard model, has often been accused of being untestable. But one of the strangest features of string theory suggests a way to test some ideas about quantum gravity that don't require practical feats of galactic architecture. String theory is filled with duality, relations between different physical systems that share the same mathematical structure. Perhaps the most surprising and consequential of these dualities is the connection between a type of quantum theory in 4 dimensions without gravity, known as a conformal field theory, CFT, and a particular kind of 5-dimensional spacetime with gravity, known as anti-de Sitter space, ADS. Its ADS CFT correspondence, as its name was first discovered in 1997 by physicist Juan Malvicino, now at the Institute for Advanced Studies. Because the CFT has one fewer dimension than the ADS space, the former can be thought of as lying on the surface of the latter, in other words, the holographic principle, like the 2-dimensional skin of a 3-dimensional apple. With the quantum theory on the surface, still fully captures all the features of the volume inside. As if you could tell everything about the interior of an apple just by looking at its skin. This is an example of what physicists call holography, a lower dimensional space giving rise to a higher dimensional space, like a flat hologram producing a 3D image. In the ADS-CFT correspondence, the interior of bulk space emerges from relationships between the quantum components on the surface. Specifically, the geometry of the bulk space is built from entanglement, which quantum connections that infamously troubled Einstein. Neighboring regions of the bulk correspond to highly entangled portions of the surface. Distant regions of the bulk correspond to less entangled parts of the surface. The surface has a simple and orderly set of entanglement relations. The corresponding bulk space is empty. If the surface is chaotic, with all its parts entangled with all the others, the bulk will form a black hole. The ADS-CFT correspondence is a deep and fruitful insight into the connections between quantum physics and general relativity, but doesn't actually describe the world we live in. Our universe isn't a 5-dimensional anti-de Sitter space. It's an expanding 4-dimensional space with flat geometry. So over the past few years, researchers have proposed another approach. Rather than starting from the bulk of the universe, and looking for the kind of quantum entanglement pattern that could produce it, we can go the other way. Perhaps experimenters could build systems with interesting entanglements, like the CFT on the surface, and search for any analogs to space-time geometry and gravity that emerge. That's easier said than done. It's not yet possible to build a system like any of the strongly interacting quantum systems known to have gravitational duals. The fields have only mapped out a small fraction of possible systems. Many others are too complex to study theoretically with existing mathematical tools. See if any of those systems actually yield some kind of space-time geometry. The only option is to physically construct them in the lab and see if they also have gravitational fields. These experimental constructions might help us discover such systems anonymously. There might be simpler systems than the ones we know about. So quantum gravity fields have turned to experts in building and controlling entanglement in quantum systems, like Schlier-Smith and her team. Quantum gravity meets cold atoms. There's something really elegant about the theory of quantum mechanics that have always dwelt such Schlier-Smith. If you go into the lab, you'll see there's cables all over the place, and all kinds of electronics we have to build in vacuum systems. It's fancy looking hardware. But at the end of the day, you can make a system that is clean and controlled in such a way that it does nicely map onto this sort of elegant theory that you can write down on paper. This messy elegance has been a hallmark of Schlier-Smith's work since her graduate days at MIT, where she used to use light to coax collections of atoms into particular entangled states. Demonstrating how to use these quantum systems to build more precise atomic clocks. After MIT, she spent a few years at the Max Planck Institute of Quantum Optics in Garching, Germany. Before landing at Stanford in 2013. A couple of years later, Brian Sundell, a theoretical physicist, then at Stanford working on string theory, quantum gravity, and other related subjects, reached out to her with an unusual question. I wrote her an email saying basically, can you reverse time in your lab? Said Kendall, and she said yes. And so we started talking. Swingle wanted to reverse time in order to study black holes and a quantum phenomenon known as scrambling. In quantum scrambling, information about quantum system state is rapidly dispersed across a larger system, making it very hard to recover the original information. Black holes are very good scramblers of information, said Swingle. They hide information very well. When an object is dropped into a black hole, information about that object is rapidly hidden from the rest of the universe. Understanding how black holes obscure information about the objects that fall into them, and whether that information is merely hidden or actually destroyed, has been a major focus of theoretical physics since the 1970s. Maybe 80 of CFT corresponds to black hole in the bulk, corresponds to a dense web of entanglement at the surface that scrambles incoming information very quickly. Swingle wanted to know what a fast scrambling quantum system would look like in the lab. Realized that in order to confirm scrambling was taking place as rapidly as possible, researchers would need to tightly control the quantum system in question. With the ability to perfectly reverse all interactions. Sort of obvious way to do it requires the ability to effectively fast forward and rewind the system, said Swingle. And that's not something we can do in an everyday kind of experiment. A single move Schlier-Smith's lab might be able to control the entanglement between atoms carefully enough to perfectly reverse all of their interactions and the time we're running backwards. If you have this nice, isolated, well-controlled, co-engineered quantum many-body system, then maybe you have a chance at something. So Swingle reached out to Schlier-Smith and told her what he wanted to do. He explained to her that this conjecture, that this process of scrambling, there's a fundamental speed limit to how fast that can happen, said Schlier-Smith. And that if you could build a quantum system in the lab that scrambles at this fundamental speed limit, then maybe that would be some kind of analog of a black hole. The conversations continued, and in 2016, Swingle and Schwarzman co-authored a paper along with Patrick Hayden, another theorist at Stanford, and Gregory Benson, one of Schwarzman's graduate students at the time, outlining the feasible method for creating and coding fast quantum scrambling in the lab. That work left Schwarzman contemplating other quantum gravitational that her lab could investigate. That made me think maybe these are actually good platforms for being able to realize total models of quantum gravity that are hard to realize by other means. He said she started to consider a setup where pairs of atoms would be entangled together, and then each pair would itself be entangled with another pair, and so on, forming a kind of tree. It seems kind of far-fetched to actually do it, but at least I could assert the regular paper how we would design a system where you can do that, he said. She wasn't sure if it actually corresponded to any known model of quantum gravity. Intense and affable, Schwarzman has an infectious enthusiasm for her work. As her student Benson discovered, he had started his doctoral work at Stanford in theoretical physics. Schwarzman managed to pull him into a group anyhow. Sort of convinced him to do experiments, you recall, but he maintained an interest in theory as well. I'd like to chat with theorists around the department. He discussed her new ideas with Benson, who discussed it with John Hartnell, another theorist at Stanford. Hartnell, in turn, a matchmaker, connecting Schwarzman with Benson with Stephen Rupser, who was at Princeton University. Rupser later died in a rock climbing accident. At the time, Rupser was working on a twist on the ABS-CFT correspondence. Rather than using the familiar kind of numbers that physicists generally use, he was using instead of alternative number system known as the p-adic numbers. The key distinction between the p-adics and ordinary real numbers is the way the size of the number is defined. In p-adics, the number size is determined by its prime factors. There is a p-adic number system for each prime number. 2 addicts, 3 addicts, or 5 addicts, and so on. In each p-addict number system, the more factors p the number has, the smaller that number. So it's the inverse relationship. So, for example, in the 2 addicts, 44 is much closer to 0 than it is to 45. 44 has 2 factors of 2, while 45 doesn't have any. But in the 3 addicts, it's the reverse. 45 is closer to 0 than to 44. Because 45 has 2 factors of 3. Each p-adic number system can also be separated or represented as a kind of tree. With each branch containing numbers that all have the same number factors p. Using p-adics, Webster and others have discovered a remarkable fact about the A, B, and C and T correspondence. If you rewrite the surface theory using the p-adic numbers rather than the reals, the bulb is replaced with a kind of infinite tree. Specifically, it's a tree with infinite branches packed into a finite space. Resembling the structure of the p-adic numbers themselves. The p-adics, Webster wrote, are naturally holographic. Basically, the bulk has the echo of the branches on the boundary. The structure of p-adic numbers that Webster told me about reminded me of the way Monica's atoms interacted with each other. Said Martineau, so I put them in touch. Goodso co-authored a paper in 2019 with Clear, Smith, Benson, and others. The paper, the chief described how to get something resembling the p-adic tree to emerge from entangled atoms in an actual lab. With the plan in hand, Clear, Smith, and her team got to work. Closing space-time in the lab. Peter Smith's lab at Stanford is a dense forest of mirrors, lenses, and fiber optic cables that surround the vacuum chamber. At the center of the room. In that vacuum chamber, 18 tiny collections of rubidium atoms, about 10,000 to a group, are arranged in a line at crude phenomenally low temperatures, fraction of a degree above absolute zero. Especially tuned laser and a magnetic field that increase one end of the chamber to the other. Allow the experimenters to choose which groups of atoms become correlated with each other. Using the lab set of Peter Smith and the research group were able to get two groups of atoms at the ends of the line, just as correlated as neighboring groups were in the middle of the line. Connecting the ends and turning the line into a circle of correlation. Then they post a collection of atoms into a tree-like structure. All of this was accomplished without moving the atoms at all. The correlation geometry was wholly disconnected from the actual spatial geometry of the atoms. While the tree structure formed by the interacting atoms in Peter lab able to full-blown realization of P-atom ADOC with T, it's the first step towards holography in the laboratory. That's needed. Obviously, the originator of the ADOC correspondence agrees. I'm very excited about this, he said. Our subject has been always very theoretical, and so this contact experiment will probably raise more questions. Hayden sees this as the way of the future. Instead of trying to understand the emergence of space-time in our universe, let's actually just make toy universes in the lab. And study the emergence of space-time there, he said. And that sounds like a crazy thing to do, right? Like, kind of mad science is kind of crazy, right? But I think it really is likely to be easier to do than to directly test quantum gravity. Here's what also optimistic about the future. We're still at the stage of getting more and more control, characterizing the quantum states that we have. But I would love to get to that point where we don't know what will happen. She said, and maybe we measure the correlations in the system, and we learn that there's a geometric description from holographic description that we didn't know was there. That would be cool. Yes, indeed. Programmable interactions in emergent geometry in anatomical ways in conversion sources. Interactions govern the flow of information and the formation of correlations in quantum systems dictating the stages of matter, the nature of the forms and the types generated in the lab. Typical interactions delay or typical interactions decay with distance and thus produce a network of connectivity governed by geometry. For example, by the crystal structure of a material or the trapping sites of atoms. Here's quantum simulator. However, many enriching applications of quantum simulation computation require richer complex, including non-local interactions, which normally feature in mapping for hard optimization processes. Mappings of hard optimization problems onto frustrated spin systems, modeling information scrambling in black holes, clearly from the realization of programmable non-local interaction in an array of atomic ensembles. Within the optical cavity, where photons carry information like crystal atomic states, by programming the distance dependence of interactions. We access effective geometry, where the dimensionality, topology, and metric are entirely distinct from the physical arrangement of atoms. As an example, we engineer an anti-parabolic triangular ladder in Mobius strips with fine-tuning interaction. And true geometry inspired by concepts of quantum gravity. A tree graph constitutes a total model of holographic duality, where the quantum systems may be viewed as lying on the boundary of a higher dimensional geometry that emerges from measured strict correlations. Our work opens broader prospects for simulating first trillion magnets in topological spaces, investigating quantum optimization algorithms and taking new entangled resource states for existing and computation. Measuring the scramble of quantum information. We provide a protocol to measure out-of-time order correlation functions. These correlation functions are of theoretical interest for for diagnosing the scrambling of quantum information in black holes and strongly interacting quantum systems. So, measuring the required echo time sequence